An individual works on a laptop while a large screen shows on a wall. Figure 14. 1. As technology has advanced, the digital platforms that evolved make it challenging to optimize user experience while protecting society and the planet. Credit modification of 140,218 NXX 999002 by Sean Miller, U.S. Army Engineer Research and Development Center, Public Domain. Chapter Outline 14. 1. Cyber Resources Management Frameworks. 14. 2. Cybersecurity Deep Dive. 14. 3. Governing the use of cyber resources. The broad-scale adoption of cyber resources faces challenges in ensuring underlying solutions, qualities, e.g., security, performance, reliability, and responsible use, e.g. Focus on sustainability, ethics, and professionalism by current and upcoming generations. TechWorks is a fictional startup company fully committed to leveraging innovative technologies as part of its repeatable business model and as a business growth facilitator. The company faces the various challenges discussed in this chapter. In particular, TechWorks' ability to successfully define, measure, and enforce cyber resource quality requirements and cyber computing governance mechanisms has a profound effect on the company's operational excellence and provides a competitive edge for the innovative solutions that TechWorks develops. To demonstrate the aforementioned challenges and how to address them, this chapter first describes the approaches used to define and measure the quality of cyber resources. It then focuses on the evolving aspects of cybersecurity assurance, which protects its solutions against undesirable use. Lastly, this chapter delves into global governance mechanisms, e.g., responsible computing, that regulate the use of cyber resources to protect our current and future generations and the planet. Learning objectives. By the end of this section, you will be able to describe cyber resources quality requirements, analyze various frameworks developed over time to manage cyber resources, identify specific cyber resources qualities such as cybersecurity, explain the growing challenges that are faced by innovative web solutions, analyze cloud cyber resource implementation strategies, describe the metaverse ecosystem and its cyber resource challenges. The cyber qualifier typically applies to anything related to computers or information technology. Cyber resources include cyber platforms, solutions, processes, policies, and procedures or guidelines required. Cyber resources store, process, and manage data and other assets electronically and make them available via networks. Cyber resources must be evaluated in a world heavily inundated with computers to ensure they conform to best practices and meet certain quality requirements. The qualities expected from cyber resources include security, safety, performance, usability, reliability, and autonomy. These qualities apply to the various architectural components of cyber resources, including business, application, data, and the pyramid of knowledge layers above data, including information and knowledge and infrastructure components. Cyber resources qualities are typically paired with one another and enhanced to optimize user experience. For example, technology solutions that leverage front-end interaction must be usable and ensure safety in various forms, e.g., data protection and user safety. While cybersecurity is meant to ensure the quality of an organization's cyber resources, it also calls for a specific cyber resource that encompasses the policies, procedures, technology, and other tools, including people, that organizations rely on to protect their computer systems and technological environments from digital threats. Regarding cybersecurity, organizations typically implement an information security policy, ISP, that outlines security practices for employees and systems. Since organizations' assets are not always information-centric, the ISP policy applies to all organizational architectural components, including its business, applications, data, and associated pyramid of knowledge layers and infrastructure. For example, the ISP policy details how the various infrastructure components are evaluated and outlines how the organization's information is secured. An ISP policy typically includes safety procedures and best performance practices, but it does not handhold workers through their jobs by telling employees how to maintain safety and perform within their role. To help manage the development of cyber resources architectures that abide by specific requirements, organizations typically choose a specific framework or a technical reference model, TRM, that details the technologies and standards that should be used to develop systems and deliver services. Analyzing frameworks, which can be complete or incomplete, helps determine which TRM applies to an organization's needs. However, most TRMs and related frameworks briefly outline procedures or system structures capabilities. It then becomes the responsibility of the workers to determine how to best adapt the framework to their company's needs. In adopting these TRMs and frameworks, computer scientists need to take a proactive approach to enhance the overall quality of cyber resources, including cybersecurity. In 2012, a reference model and associated framework, referred to as the Open Group Architecture Framework, TOGAF, TRM, was created to help users develop architectures based on their specific requirements. It champions a layered and componentized architecture that can be leveraged to develop specialized domain and industry architectures for infrastructure and business applications. It also provides a set of qualities that these specialized architectures and the applications that use them must fulfill. Link to learning. Read this TOGAF series guide on the TOGAF reference model from the Open Group for more information about TOGAF, including a diagram that shows the technical reference model in detail. The TOGAF reference model shows the service categories that may apply to an information system. Not all architectures will include all of these services. TOGAF users should select services based on their specific requirements to build an architecture. This framework was created and designed to be customized for each organization, resulting in a more secure design framework. The TRM analyzes business information systems, including application software, platforms, and communication infrastructures. The TRM assumes that all software and applications are running on the internet. The original intention of the model was to create a taxonomy of vocabulary and standards that could be used to evaluate business and infrastructure applications. The different qualities within the TRM were meant to break an organization's infrastructure into manageable segments. These segments could then be evaluated for cyber resource quality and implementation needs. This model tried to establish easy interoperability, allowing two or more computers or processes to work together for infrastructure applications while providing the versatility to analyze business applications. This TRM is vastly applicable to modern systems, but newer TRMs have been created to handle cloud and other infrastructure areas. While optimizing the quality of cloud-based solutions, smart ecosystems, and super society solutions is proving to be quite difficult, these solutions are also opening the door to current and future challenges in computing, including sustainability, ethics, and professionalism. This has led to the creation of the Responsible Computing movement as an IBM Academy of Technology (AUT) initiative in early 2020. Subsequently, in May 2022, the Object Management Group (OMG) created the Responsible Computing Consortium with IBM and Dell as founding members. This led to the creation of the Responsible Computing Framework, Figure 14.2 and Figure 14.3. Illustration of Responsible Computing Framework includes organization, theme, and sponsor perspectives. It also includes circularity, privacy, climate, ethics, diversity, openness, inclusion, sustainability. Figure 14. 2. The various perspectives of the responsible computing approach include organization, theme, and sponsor. Attribution. Copyright Rice University, OpenStax under CC by 4.0 license. Illustration of responsible computing provider. Domains responsible data center, responsible infrastructure, and responsible code, more directed to technology aspects. Domains responsible data usage, responsible systems, and responsible impact, more directed to social aspects. Figure 14. 3. The Responsible Computing Framework helps organizations regulate the use of cyber resources to protect our current and future generations and the planet. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Responsible computing is a comprehensive approach tackling present and future computing challenges. It emphasizes both systematic design and soft skills crucial in the industry. Developers are urged to anticipate potential harm from their work, emphasizing secure coding and adversarial systems development. These frameworks and styles target various enterprise business platforms. Traditional architectural styles like OMA and SOA are generic models that can be applied to the TOGAF. The OMA focuses on creating and assembling components that can be used for information systems, including interfaces. At the same time, the SOA relates to the assembly of services that can be applied to the TOGAF TRM. Understanding the difference between OMA and SOA is crucial, especially for cyber-quality resources. Newer platforms require updated models and the adoption of older models with modifications to fit system needs. This realization becomes more critical as cyber ecosystems continuously change. These architectural styles offer vision, but are not core concepts of cyber resources. The OMA reference model, OMA-RM, Figure 14.4, was developed in the 1990s to detail communications with object request brokers and different services. It visualized interfaces and services before the need to control and protect web interfaces. Illustration of OMA reference model, object services, object request broker. Application objects, domain objects, common facilities. Figure 14. For this figure shows the OMA reference model developed in the 1990s to explain communications and interactions with object request brokers and different services. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. Different architectural styles cater to various project managerial styles, such as the waterfall model and the agile development style, refer to Chapter 9 Software Engineering. Each framework has its strengths and weaknesses, influencing the implementation and evaluation of cyber resource qualities, which significantly affects the information security policy. IT specialists must consider all cyber qualities, not just security. Best practices for quality and performance determine data storage methods, which can be automated to enhance cyber quality resources. Cyber resources qualities. Cyber resources address various cyber platforms and their functional and non-functional requirements, including software and hardware solutions for information systems. Well-designed platforms balance the requirements while analyzing the effect on the environment in which the systems will function. In systems engineering, quality attributes are non-functional requirements, also called architecture characteristics, used to evaluate the performance of a system. As development practices evolve, different terms and nomenclature are created. For example, abilities refer to the abilities of architectural properties. They can include system architecture trade-offs, which may not be visible to the user, but that ensure the architecture will perform as needed. Developers and enterprise architects are responsible for incorporating abilities into architecture. When developing information systems and quality management plans, the developer must analyze and create functional and non-functional requirements that are only measurable once a solution platform is built. Refer to Chapter 9 Software Engineering and Chapter 10 Enterprise and Solution Architectures Management. This guides the creation of large-scale horizontal platforms, such as the web mobile and cloud platforms, ensuring acceptable quality and security. Defining cyber resources qualities. Cyber resources qualities are developed and measured within software models. The ISO IEC 25010 standard, detailed in ISO IEC 25002, 20241, details different software quality models and abilities. This standard aims to provide guidelines for creating high-quality software and systems. A suite of ISO standards focuses on the quality of software and systems development, helping to identify quality characteristics that guide the development of functional and non-functional requirements. Additionally, frameworks like OMA-RM, OMA Guide, OMG, and TOGAF-TRM guide these requirements by creating a taxonomy of service qualities. This expands the implementation of the different abilities a system can sustain. Functional specifications can fall into categories, Table 14. 1. Categories definitions. Interoperability, the ability for two or more computer devices or processes to work together. Composability, the ability to incorporate services within applications. Scalability, the ability to enhance or retract system requirements for the number of users involved in the system. Evolvability, the ability to adapt the system to new standards and practices. Extensibility, the ability to modify the system to include new requirements or remove old requirements that are no longer needed. Tailorability, the ability to customize the system for the needs of the users or industry. Security, the ability to ensure safe use of the system. Reliability, the ability of the system to perform as needed, without failure and to specification. Adaptability, the ability to change or modify the current system to meet the needs of a different industry requirement. Survivability, the ability to survive an attack or disruption of service within a system. Affordability, the ability to create a system that is cost-efficient, not only monetarily, but also with resource usage. Maintainability, the ability for the system to be upkept. Understandability, the ability of the system to be used, also referred to as the learning curve. Performance, the ability to work within measurable standards and requirements. Quality of service, the ability to provide a solution to a problem or task in a way that most of the necessary user requirements are met. Real-time, the ability to operate the system within normal operational time. Nomadicity, the ability to work in a self-contained environment or the ability to move the system from location to location. When system location is a requirement. Table 14. 1. Categories of ILIDs. Defining system requirements into ILIDs makes it the developer's architect's responsibility to ensure system security. This may seem daunting, but any system can be broken down into functional and non-functional requirements. A TRM supports and sustains the ILIDs while ensuring that the information security policy can be enforced. To do this, the TRM focuses on 4 service qualities: availability, assurance, usability, and adaptability. Table 14. 2. Qualities components of the taxonomy: availability, locatability, manageability, performance, reliability, recoverability, serviceability. Assurance, credibility, integrity, security. Usability, ease of operation, international operations. Adaptability, extensibility, interoperability, portability, scalability. Table 14. 2. Service qualities of the TRM. These quality areas and the categories of ILIDs provide an avenue and direction for cyber resources, measuring cyber resources qualities. TOGAF recommends combining quantitative and qualitative methodologies to measure a system and provides several quality assessment techniques. The system's architect should create assessment plans to ensure all functional and non-functional requirements are met and tested, aligning with the framework. This methodology checks to see if the requirements are met and evaluates how well the requirements meet their objective. Other models, like the CIS Critical Controls 2, can be used to test compliance with policies and requirements. An important approach to testing resource qualities is to log tests performed and continually analyze system changes. This aids in assessing maintainability, survivability, and performance. The TOGAF architecture development model, ADAM 3, centers the requirements around the development process. Illustration of TOGAF ADM preliminary framework and principles. Arranged in a circle around requirements: architecture vision, business architecture, information systems architecture, technology architecture, opportunities and solutions, migration planning, implementation governance, architecture change management. Figure 14. 5. The TOGAF ADM is a standard to assist enterprises in identifying the steps of different activities and the inputs required to develop an architecture. Credit. Modification of TOGAF ADM by Stephen Marley/NASA/Sci, public domain. To assess the quality of a platform solution architecture, TOGAF recommends using a combination of quantitative and qualitative methods. Quantitative methods measure performance against quality attribute scenarios, while qualitative methods review the architecture against best practices, principles, standards, and guidelines. TOGAF provides several tools and techniques for quality assessment, including the following: architecture compliance review to check alignment with enterprise architecture standards and policies. Architecture maturity assessment to measure maturity level based on a predefined model or framework. Architecture capability assessment to measure an organization's capability to deliver and manage an architecture based on a predefined model or framework. Architecture trade-off analysis to compare and balance trade-offs between different quality attributes and design alternatives. To improve the quality of a platform solution architecture, TOGAF recommends a continuous improvement cycle. Plan, do, check, and act. In the plan step, define and agree on quality objectives, criteria, and metrics. In the do step, execute and document the quality activities, tasks, and responsibilities. The quality outcomes, results, and feedback are collected and analyzed in the check step. The quality issues, gaps, and opportunities are addressed and resolved in the act step. To ensure the acceptance and adoption of a platform solution architecture, TOGAF emphasizes quality communication. TOGAF provides various tools and techniques, such as architecture views, viewpoints, models, and documentation. Architecture views represent a subset of architecture, which focuses on a specific quality attribute or concern. Architecture viewpoints specify the conventions and rules for creating and using an architecture view, while architecture models are formal or informal descriptions of an aspect of the architecture. Lastly, architecture documentation collects artifacts that capture and convey information about architecture and decisions. Cyber resource measurement is a layered process. Remember that according to IBM's responsible development methodologies, quality assurance should be done during all development steps, not just at the end. Following these steps results in an incremental system with proper checks and controls for security purposes. Web and mobile solutions era. Web, mobile, and IoT solutions are used at a global scale today. We have built development models, created a TRM, and educated computer scientists to prioritize cyber resource qualities. We have set the stage for web and mobile platforms by emphasizing these qualities in development. The TRMs focus on usability, ease of operation, assurance, security, and adaptability has built a framework for responsible content development. Utilizing web-centric server-side coding, we have created more secure platforms that efficiently communicate through APIs. Scalability, extensibility, and flexibility of web platforms pose significant challenges for cyber quality. In the past, quality focused on ensuring that cyber solutions functioned as intended, but now it is also focused on security. Securing a web platform involves more than just the web front end. It also requires securing the server architecture, the physical locations of the servers, the cloud solutions, and interfaces. Many web platforms use third-party software plugins that rely on the proprietary software's security and quality. Poorly written code is easily exploitable, especially with the widely accessible tools to do so freely accessible on the World Wide Web, WWW, the Internet Information System that connects public websites and users. Web platforms have continuously changed in direction and architecture design. The architectural principles of the Internet stated in the Request for Comments, RFC, 1958 set forth by the Internet Engineering Task Force, IETF, in June 1996. For knowing that the Internet had to be able to change was a design principle. Anticipating that IP addresses would need to adapt or be replaced at some point because the number of devices would exceed the allotted number was a guiding principle that forced the Internet to be scalable and extensible. Quality of service and assurance security concerns drive the commercial Internet. Initially, the Internet's architecture was unregulated, and there was no mandate for IP address allocation or domain name services, DNS, from the Internet Architecture Board, IAB. Public Internet is now ubiquitous in most economic areas of the world. The increase in mobile platforms and the continuous need to be connected pushes the boundaries of cyber quality beyond the original architectural goals of the Internet. Performance and usability demands drive technology and the Internet to adapt and create new mediums easily adapted into scalable infrastructure. Open Web Platform Quality Challenges. The Open Web Platform, OWP, initiative was designed to offer royalty-free, open technologies for web platforms. Its goal was to provide a foundation of services and capabilities for developing web mobile applications, as illustrated in Figure 14. Using the OWP, everyone can implement a web or mobile solution without requiring approvals or license fees and maximizing usability and accessibility. Illustration of OWP application foundations: security and privacy, web design and development, device interaction, application lifecycle, media and real-time communications, performance and tuning. Usability and accessibility, services, Figure 14. The foundational characteristics of OWP solutions allow anyone to implement a web or mobile solution without licensing. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. The cyber qualities of these technologies are continuously evaluated. People want free web applications that are easy to use, have good performance, are secure, always an afterthought, are compatible with their current technology, and most of all, remain free and open to the public. Security plays a significant role in the adoption, and ease of use is often a struggle. The most straightforward security measure, restricting access to the system, is not feasible if companies want to interact with the world. Several companies like Meta use a limited functional interface called a walled garden approach, which limits openness and prevents users from accessing a platform. This approach goes against the spirit of OWP. Open web platforms like WordPress and Drupal provide user-friendly web design through drag-and-drop web page creation frameworks. However, updates to these technologies can break other areas or disrupt compatibility with other open web software packages. To mitigate this, people and companies are adopting the walled garden approach to web applications, limiting controls and plugins, and the developer can incorporate their own HTML security measures. The walled garden approach goes against the principles of the OWP. The concept of openness wants technology to be free and interoperable, giving individuals a subset of technologies and forcing them only to use those technologies diminishes the power and expansibility of the Internet. Modern web mobile solutions, quality challenges. The World Wide Web (WWW) demands 24/7 access as users expect constant availability. Companies like Amazon have set the bar for quality of service and how fast a product purchased on the web can be delivered to a residency. Smartphones and the IoT have provided new access models to services and goods. What challenges does this pose? Account management. Users have numerous online accounts, requiring unique, strong passwords for each. Research by ColorLib in May 2023 found that the average person has 100 accounts needing passwords, up from 70-80 in 2022. 6. This growth highlights the challenge of managing diverse and increasing technology. Workforce shortage. There is a shortage of qualified professionals. Higher education and companies like Microsoft, CompTIA, and Cisco provide certifications to prepare workers, but students without industry experience struggle to find suitable jobs, and entry-level positions are limited. Threat landscape. The rapid growth of web platforms and technology increases security challenges. The use of cloud technology and IoT devices introduces new vulnerabilities. Companies like Microsoft invest heavily in training programs and certifications, particularly for securing Azure web platforms. Modern walled garden platforms quality challenges. The main challenge for walled garden platforms is interoperability. For instance, WordPress offers more than 59,000 plugins. While these plugins allow for customization, only cosmetic changes are typically possible. This allows security to be maintained in a walled garden approach. Plugins are tested for security issues before being added to a library. However, using plugins in ways they were not intended can create vulnerabilities. Using plugins in untested ways goes against IBM's responsible coding practices. Then questions must be asked, such as who is responsible for the misuse, who is responsible for updating the plugins for newfound security issues, and lastly, who is responsible for removing outdated plugins whose functionality no longer works with the current technology. Using frameworks to assess the proper development of websites and content should be a requirement for web programmers. Insecure content puts users at risk. Security frameworks, plans, and walled garden approaches can enhance web platform security. However, this requires skilled developers and available resources. Cloud-centric solutions era. Cloud platforms rely on applications built for web and mobile platforms, similar to the Open Systems Interconnection (OSI) networking model. In this analogy, cloud-centric solutions are Layer 3, web programming, applications, and the WWW are Layer 2, and the Internet is Layer 1. Each layer has its security challenges. Cloud-centric solutions involve many different systems, software, and communication methods. Applying the TRM to this model highlights availability and assurance as major concerns, with adaptability being crucial with interoperability, scalability, portability, and extensibility. Usability is the biggest challenge. If users cannot use the product, then implementation will fail. Hardware issues present additional challenges beyond user interactions in the cloud-centric model. The OMG Cloud Working Group, CWG, addresses myths associated with cloud-centric solutions, focusing on scope and applicability, costs, security, availability, and management. The CWG advises maintaining a calm approach to solving cloud issues and warns against overselling cloud solutions because of the difficulties in implementation needs. Hardware virtualization quality challenges. Many cloud-centric implementations use hardware or software virtualization. Hardware virtualization challenges face compatibility issues and constant updates, often resulting in performance loss when implementing a virtualized approach for cost savings. Vendors like Amazon, Google, and Microsoft offer hardware virtualization options that typically improve efficiency, flexibility, scalability, and security. However, a big concern with virtualized cloud solutions is that the availability of resources comes with extra processes. Users needing to access their data and information must navigate the complex interfaces that provide walled approaches to web design. This limits functionality, and since many organizations decide to host their cloud solutions themselves, it leads to new challenges with regard to cost, assurance, data privacy, and security. When using virtualization solutions with the TRM, availability and manageability are key concerns for users. Poor performance and outdated hardware can lead to liability for an organization. Redundant systems are necessary for maintenance and upgrades because there are times when a system is vulnerable and not available. This is where virtualized solutions can help. It is easy to spin up a third instance of a cloud-centric virtualization and perform the needed hardware upgrades in the first backup system and then the production system. While the backup system is down for hardware upgrades, the virtualized backup covers any necessary security issues. Once the servers are upgraded, an entire image is copied from the main server onto the backup server. Then the backup server becomes the primary server with a virtualized backup solution, and the original main server can then be upgraded to become the new backup server. During this hardware update, the implementation of the TRM becomes important. Information must be kept available throughout the whole process. If the faulty hardware is left in the systems, then errors or crashes may occur. Then known vulnerabilities are identified in hardware configurations, and the process of hardware upgrades must be implemented. Virtualized solutions require constant monitoring. Network modeling virtual local area networks must always be monitored for load balancing. A virtual local area network, VLAN, is a tool to connect devices and nodes from various LANs. Storage calculations and estimations must be constantly performed to ensure upgrades keep ahead of any issues. Manageability and serviceability are constant challenges, including both hardware and human resources. Training workers in new software is costly and time-consuming, resulting in minimal opportunities to learn on the clock and possible security lapses. Security procedures are often ignored for the sake of time. As a result, many companies seek cloud-centric systems to avoid these issues. Container management platforms quality challenges. A container is a lightweight package that bundles together applications to form a solution to specific problems. When applying the TRM to containers, usability and ease of operation are major challenges for web mobile and cloud platforms. Containers simplify development, deployment, and management across complex environments, offering a quick solution for loading features without concerns about the operating system. With a container, the developer is limited to the operating system for which the package was developed. While this seems like a challenge, it provides security and adaptability. Containers are built for specific application purposes. They are often referred to as enterprise solution support containers. Kubernetes includes support for load balancing, rollout of patches, configuration management, and storage orchestration. Alternatives include Docker Swarm, Apache Mesos, and cloud solutions such as Azure Containers. Effective container management benefits from the TRM in several ways. The usability and ease of operation and the quality of web mobile platforms include several approaches that help the user and developer manage and build the system. Ease of setup. The management system provides a drag-and-drop system for scheduling, storage maintenance, and system monitoring. Enhanced administration. It simplifies IT management, allowing administrators to focus on other tasks. Automation. It automates any number of processes and does automatic load balancing. Continuous health checks, reporting, and logging are essential for container management and allow an admin to do their job efficiently. Change management. It keeps a detailed change log of the packages. This allows for troubleshooting issues arising from upgrades of older packages. Using the TRM to maintain alignment of the container management to the utilities is a large concern. Every aspect of the TRM can be applied to the container management platforms. It is recommended that when the TRM is used to evaluate the management systems, the developer thinks about incorporating an outside resource, like the CIS critical security controls, to help determine the level of compliance needed for the given control. Overall, container management can greatly assist an organization looking to speed up its development time and interoperability between systems. Cloud Big Data Analytics PaaS quality challenges. In our development pyramid, where cloud-centric platforms are at the top, Layer 3, cloud and big data analytics form an overarching umbrella. The process of analyzing that data to find correlations and trends that can be used for decision-making is called big data analytics. Incorporating the platform as a service, PaaS aspect for big data analytics provides a cloud-based development environment that can solve many development problems and provides methods to analyze and enhance system performance. A big challenge with data analytics from a TRM perspective is time. It takes time to properly analyze data collected to make informed business decisions. Big data only helps information management when data is converted into information on time. While cloud providers do their best to offer 24/7 customer service, issues arise when third parties and containers are introduced. The data may not be immediately available from the third-party vendors, or they may not want to share their data. Having clear agreements with third parties about what data will be shared and what data will not be available is important. A second challenge with big data solutions is collecting the wrong data. For instance, firewall log files might record timestamps of external IP address access attempts, but if the firewall doesn't account for IP4 to IP6 conversions, some IP address data could be lost. If the firewall only handles IP4 and the attacker uses IP6, the log files may be incorrectly formatted, resulting in incorrect or incomplete data analysis. A third challenge for data analysis and PAS is bandwidth. Proper data analysis requires large amounts of computing power and hardware, slowing network communications during data transmission. Storage is another issue, as analyzing multiple days of data requires additional storage locations, often leading to cloud storage and virtualized solutions. Companies like Google generate revenue by doing big data analysis and selling their findings to companies for marketing strategies. Managing over 1.8 billion Google accounts with a free 10 GB cloud storage drive necessitates virtualization and an extensive security plan. A service level agreement, SLA, must be established when customers enter into agreements with PaaS platforms. The SLA outlines the services that the platform provides. Companies can estimate growth and need for their organization using SLAs. However, SLAs are not covered in the TRM, and since they are not actual ilities, they may fail to include actionable items. This means that the SLAs are what-if actions. For example, if there is a data breach, this will happen, making the SLA reactive rather than proactive. The TRM aims to prevent issues before they arise. SLAs are criticized for lacking assurance and privacy protections, as data breaches can put user information at risk. This highlights the importance of trust, which, while not directly mentioned in the TRM, is addressed in many different ilities in implied ways. Trust in any service-providing system has a narrow margin for error. A trust relationship is established when consumers entrust their information to a company. To bolster this trust, companies should have information security policies detailing data security practices. However, exact methods should not be disclosed to prevent giving hackers helpful information. The trust relationship aims to make the consumer feel secure and therefore increase their ease of use with the system. This trust can be a valuable metric for measuring quality based on customer satisfaction. Cloud IoT PaaS quality challenges. Earlier, we compared technology to a 1-mile race, with IoT representing the last 10 steps. Every technological advancement has led to the IoT, as consumers want more power and faster access to information. They are dissatisfied when companies fail to provide information quickly and efficiently. Cloud IoT as a PaaS provides more challenges than this small section of the book can cover. To start, IoT's largest challenge is scalability. The rapid development of wearable devices, smart cars, appliances, and artificial intelligence suggests no end to this growth. Consequently, IoT scalability is increasingly challenging to manage. If scalability is out of control, then it is typically the case that security is out of control. Most TRM ilities encounter challenges with the IoT having a quality security plan for every possible third-party IoT device is not feasible, and it is sufficient to analyze the performance of the underlying Bluetooth and Wi-Fi technologies. Developing better and stronger ways to secure communications between devices would be an excellent first step. There will always be an issue with hackers capturing data transmitted wirelessly. The next challenge for IoT as a PaaS is storage. Where is all the captured data stored? Apple devices are stored in their iCloud, but other companies face security issues with stored data. Consider the data that is left behind on a device that is no longer in use. Best practices for disposing of computer hard drives and other storage devices don't always apply to IoT devices and smartphones. We created regulations like the General Data Protection Regulation, GDPR, and the California Consumer Privacy Act, CCPA, to address concerns arising from IoT storage situations. Interoperability is a major challenge with IoT devices, given the vast types of devices and communication methods. Securing biometric data is a constant concern, and hacking into home monitoring systems with IoT devices poses significant safety risks. Since most IoT devices rely on Wi-Fi, improving interoperability efforts and security in wireless communications is necessary. Cloud-centric services are another concern, as all IoT devices are part of cloud technology. Developing interfaces for IoT devices is also challenging due to the need to accommodate cultural and language differences. Cloud robotics PaaS quality challenges. Cloud robotics PaaS merges two challenging areas: cloud computing and robots. Robotics has faced development challenges, especially in natural language processing, to help robots perform actions and communicate with users. This is often seen as a futuristic world where robots handle daily operations, reducing the need for human labor. However, the high cost of robotics remains a barrier. AI continues to evolve, driving industries to use it to enhance production and services. We as humans must repurpose our skill sets to train the robots to do our work. Cloud robotics is the next step in the evolution of standard robotics. Traditionally, robots perform preloaded algorithms, making decisions based on predetermined outcomes. However, with cloud robotics platforms, robots use big data analysis to make more informed decisions. Leveraging the power of cloud data and rapid processing speeds, they can approach thinking to analyze a problem or a task. This is not to be confused with automation. Traditional automation involves robots replacing human jobs or tasks. Automation is a programmed response with limited inputs and decisions. Cloud robotics PaaS, in contrast, allows for more extensive inputs and a broader range of decisions. This enhances the robot's decision-making capabilities through advanced algorithms. The TRM has small applicability to robotics, with key considerations being security and connectivity. Robotic cameras and other devices need to transmit their data for processing, making connectivity to cloud platforms essential. Reliable high-speed data transmission is critical to cloud robotics, raising concerns about network outages. Robots might cease functioning without incoming data, and latency or corrupted data packets can impair operation. Cloud robotics shares many challenges with simple networking, but the issue is that robotics may have a more important role than a computing platform. If the robots are not getting the needed inputs, they may be unable to carry out the functional tasks. For example, suppose a robotic drone traveling over a mountain range loses communication while searching for lost hikers over a mountain range. In that case, it might crash without its ability to transmit and receive data. The drone cannot receive any flying commands and would plummet to the ground. Safety protocols are essential, such as hovering in place until communication is reestablished or the battery depletes. While these connectivity issues are not new, the context has shifted. Previously, this scenario would have involved a helicopter or airplane doing the search, but it is more costly to have a plane fly to search for lost hikers than a drone. Connectivity remains a persistent challenge for any system relying on remote communications. Industry 4, Metaverse Smart Ecosystems Era. The fourth industrial revolution, also referred to as Industry 4.0, is characterized by increasing automation and the employment of smart machines and smart factories. Insight obtained from data helps produce goods more efficiently and productively across the value chain. The term metaverse, which was coined in Neil Stephenson's 1992 novel, Snow Crash, has been used by Meta, the company that developed Facebook, to refer to a platform that applies augmented and virtual reality in a social media environment. However, the metaverse concept extends beyond social media and refers to the next generation of the web that will provide an immersive augmented virtual reality (AR/VR) interface and will leverage new technologies including AI, ML, IoT, blockchain, 3D models, and others. The metaverse will go beyond Web3 that already includes blockchain 2.0 capabilities on a decentralized internet. The metaverse is a hybrid cloud environment aiming to uphold the OWP principles. Software developed for the metaverse must ensure full interoperability and interactivity with all other platform software. These requirements significantly constrain the technology's ease of use and performance requirements. Incorporating virtual and augmented reality into the metaverse typically involves using an AR/VR headset to access a library of software programs, each offering a highly realistic user experience. To be part of the metaverse, software must adhere to these rules. 7. There is only one metaverse, and all people should have access to it. The metaverse exists beyond everyone's control and must be accessible at all times. The metaverse doesn't care about hardware. We must understand how metaverse solutions relate to the hybrid cloud environment and leverage the foundations set forth by OWP. New challenges for each one of the qualities arise as we go up in layers. For example, cloud security requires users to trust their cloud provider. The ecosystem resulting from the software developed to interact with the metaverse provides challenges for all cyberquality services. From a security perspective, users must know about privacy and data protection when using AR. Systems collect large amounts of data, and users need to understand what is being collected and where it is stored. For instance, self-driving vehicles use AR technology to navigate and store driving patterns and routes. If hacked, this data could reveal when a user is not home. Additionally, many self-driving cars store garage door information to automatically open doors when the vehicle is nearby, posing further security risks. The ecosystem should provide a plug-and-play mentality for all metaverse-associated technology. Without this, ease of use, performance, and reliability may suffer. Increasingly, people are integrating technology into their lifestyles, especially since the COVID-19 pandemic, with more online shopping and remote working. Virtual meeting rooms and advanced technology are replacing traditional office interactions. A work-from-home environment that is fully immersed in technology could be a way to provide lifelike meetings where 3D images and holograms of people sit at conference desks instead of flat-screen monitors. The technology performance, automation, and ease of use are at an all-time high. For this environment to become commonplace, trust in technology must increase. Companies must prioritize incorporating all cyber qualities to ensure high performance, automation, and ease of use. A large issue is creating content that is both interoperable and secure. The demand for VR worlds and platforms drives rapid production, often leading to unchecked vulnerabilities due to insufficient time and resources. This is particularly problematic in VR, where large multi-user dimensions are common. Data exchanged between entities has to happen seamlessly, but the whole system is at risk if one system is compromised. Since there is only one metaverse, a security vulnerability in any software on the platform puts the entire system at risk. A new risk that has emerged is addiction. Users may prefer the AR version of their environments, leading to a sensory deprivation effect in the real world that drives them toward AR and VR. This is particularly problematic for adolescents. Since the onset of the pandemic, increased AR/VR use has made younger users more susceptible to addictive behavior with these systems. 8. Smart ecosystems, 3D modeling platform quality challenges. Ecosystems that incorporate 3D modeling are faced with many different challenges. To apply the TOGAF reference model to the problem, all of the qualities of concern are as follows. Graphics and images. Cloud computing has provided a storage medium for graphics and images, but the quality of the images based on their resolution is challenging. For AR/VR platforms, the images need to be of high resolution, which leads to more storage and lower transmission rates. Data management. The pure amount of data to create 3D modeling is immense. The data collected for AR/VR to be successful requires more storage and memory within machines. The fastest internet connections are needed for data transmissions, and archival procedures must be implemented for the data system's lifetime. Data interchange. As with data management, data interchange struggles with the transmission speeds of large 3D models and the physical hardware found within the different AR/VR systems platforms. Since no complicated platforms are required, the data interchange must be universal. User interface. This is paired with graphics and images, but there is an aspect that is a different challenge. The ease of use is a challenge with 3D modeling. The user interface must be seamless for the AR/VR to work properly. The user must be able to interact with objects appropriately rendered, and the user interface must be lifelike. International operations. This area is a serious challenge with 3D modeling, and it comes in the form of symbolism and color coding. In different countries and different cultures, symbols have different meanings. With 3D modeling, where every country in the world is interacting with the metaverse, all software must be interoperable. Each country involved in the metaverse will have different data storage and security standards. Location and directory. Working with data management, location data, and directory information is always challenging. If two software development companies collaborate and create 3D models that hold user data or georecord, then storing that information is challenging for the system. Transaction processing. 3D modeling requires a large amount of object interaction. When objects are developed for 3D modeling, they are typically put into a setting or a landscape. Most objects interact with other objects, which is done through transaction processing. Security. the risks and challenges associated with security are some of the most difficult to identify and detect. Many companies are creating 3D models for other entities to use. These models are not always verified, and penetration testing is not always performed on each 3D model. If multiple 3D models are incorporated into different company systems, then the security concerns escalate. Security seems to be an afterthought based on performance and system requirements. Software engineering. This area of the TOGAF deals with skills in different 3D modeling software. Many HTML or scripting languages cannot do proper 3D rendering. Therefore, the software engineer needs special skills to develop the models correctly and with proper aesthetics for the platforms and worlds they will be used within. System and network management. The challenges are related to communications and interoperability. Since there is no requirement on what hardware or technology can be used to interface with the metaverse, network management is crucial. The communication needed to transfer 3D models between AR/VR nodes is important, and the system resources will be challenged to perform these transfers properly. The metaverse is not housed on one computer, and the bandwidth needed to transfer the large amounts of data needed for 3D modeling will always be challenging. The TOGAF and the TRM provide a good framework for analyzing most system challenges. Analyzing 3D modeling is similar to analyzing any resources needed for the metaverse. For instance, besides 3D modeling, there is a large language barrier in the metaverse, and each of the qualities of the TOGAF can also be used to analyze such barriers. Smart ecosystems, AR/VR platform quality challenges. Any ecosystem that houses AR/VR technologies will always struggle with ease-of-use issues. The TRM stresses that accessibility to any platform must be made easy. New technology introduced through the IoT presents challenges for AR/VR platform issues. The headsets needed for most AR/VR technology cannot be worn to walk around. They are usually meant to be worn safely away from obstacles the individual might encounter or trip over. This virtual platform may be easy to manipulate in the device, but the hardware is bulky and often clumsy. Wearing AR/VR gloves to interact with computer systems is a nice feature when the individual can use them fully. Using AR/VR technologies to assist individuals who have disabilities is a major reason to invent the technology and push the boundaries of the technology. Smart ecosystems, IoT platform quality challenges. IoT platform challenges are equal to that of cloud technologies. The main challenges are bandwidth, storage, and infrastructure. There is a need for bandwidth that is more significant than 5G technology for all communications. The use of fiber optic communication greatly increases the rate of data transfer, but many times, the network is left to backhaul the network. Backhauling the network directs traffic to a longer out-of-the-way route to perform load balancing on the network, help prioritize important data, and send the data to the most direct route. Using backhauling for data that are not as important as primary communication is a reasonable workaround for having poor network bandwidth. The infrastructure challenges are constantly being evaluated. The need to move all devices to the IP6 protocol in the TCP/IP network layer away from IP4 provides its challenges. The move to different IP settings is small compared to Internet Provider (ISP) issues. Many ISP providers share mediums, but many others install their networks. These independent networks do not communicate. Therefore, all information must go to large data centers, which can then be sent from there. This forces central offices and organizations to be formed to handle data warehousing. This introduces the challenge of central locations. To IoT, there needs to be enough data centers close enough to each other to have data transmitted quickly and without any transmission issues. Network and mobile device security always needs to be addressed. The attack vectors created by the IoT increase with every new device created. The biggest issue with data storage is the physical need required for the data storage. Data warehousing and data mining have become their distinct area of the industry. The sheer amount of data collected becomes unimaginable. The average person in North America has over 13 devices that have telecommunication needs. 9. It is reported that each household in the United States has over 8 IoT devices. 10. There is a constant increase in the number of IoT devices in households. This means that there is a direct corollary with the number or size of the data center needed to provide proper services to these devices. A serious challenge that needs to be addressed immediately is the standards and requirements for IoT platforms. ISO IEC Standard 31041 addresses the IoT and reference architecture. This standard helps smooth over a seamless connection with the intent of being safer. The framework that this standard is a good starting point, but the challenge is the implementation of the standard. It is not a requirement for companies to use. ISO IEC 27400 family addresses IoT security and data privacy guidelines, but nothing is forcing a company to use or address these standards. Smart ecosystem, blockchain platform quality challenges. Blockchain platforms suffer from availability scalability challenges directly associated with the TRM model. All blockchain platforms can only process so many transactions per second. If the data the blockchain received are greater than the computational capabilities, then the computational ability of the platform slows down and gives the impression of being offline. Blockchains tend to be more secure than traditional computer systems because most systems are distributed. Many are based in the cloud. A distributed and cloud-based platform will always be directly affected by availability and scalability issues. Most blockchains have strong cryptographic principles, strengthening the TRM's assurance and integrity issues. The TRM's ease of use plays an important role in the challenges with blockchain. Many owners of blockchains become landlords to data mining infrastructure, facing challenges to cryptocurrencies and other dilemmas on how the information will be disseminated. The ease of use challenge is that while cryptocurrencies are relatively easy to use, their values fluctuate greatly, and people do not trust transactions based on fictional money. The different blockchain software packages do not always communicate well with each other, making transaction processing difficult at times. A challenge introduced by cryptocurrencies is the issue of auditing and transaction analysis. Individuals in charge of the blockchain can control what data are collected and what they will do with it. While this does not directly play into the ease of use, you must adhere to the owner's rules, and they can make it as easy or difficult as they wish for you to use their software. Blockchain platforms also face challenges in terms of adaptability and interoperability. Although the World Wide Web seems to have been around for an eternity, blockchain concepts predate it. Cryptographical secured chains were discussed in the early 1990s by Stuart Haber and W. Scott Stornetta. The idea is that cryptographic hashes could be broken up into blocks to be transmitted. Choosing the size of the block and communicating these blocks has always been a challenge. The argument of what form of cryptography, or the process of using codes to protect data and other information, is the best and what the best ways of transmitting the information remain challenging to all blockchains. These different modes of transmission and the different cryptography used challenge adaptability and interoperability. Smart ecosystems AI ML platform quality challenges. Artificial intelligence, AI, and machine learning, ML, provide a variety of platform and quality challenges. These two types of technology suffer from the same difficulties as the cloud big data analytics platforms discussed earlier, with the addition of TRM quality standpoints. The challenges of availability, assurance, and usability are still present, but this issue is how to ensure quality from an AI ML perspective. Generative AI can interact with a customer base, but that customer base usually wants to talk to a real person. When used in chatbots and other front-end interfacing devices, users can typically get their answers quickly, but they often lack depth or leave out important facts or features. The generative AI can only produce responses and information based on its calculating algorithms. The Turing model of AI is based on algorithms, while the Lovelace model of AI is based on spontaneous creation of material. We are not in a world where AI ML devices can think and create new content. The generative AI, for instance ChatGPT, uses a predictive text model to form its responses. The quality of responses from such devices is left in question because if the device cannot determine the correct answers, it often makes up the material. The use of cloud devices based on AI ML provides the challenge of communication and speed. The availability of data that is accessible and of the highest quality of analysis is always a risk. The need for secure communications and smart backups is also critical. This is a definite concern for compliance issues. The CIS critical controls can be used to evaluate procedures and test compliance levels against company policies. The problem is creating policies that handle all possible combinations of AI ML and their applications within a company. In higher education, colleges create ML models based on information collected in student datasets. They use these models to perform targeted marketing in an effort to increase the number of college applications. The challenge is that many of the datasets that are used to train ML models are culturally biased and do not consider all possible learners. They usually have a targeted demographic. Therefore, the new student enrollment plan could be flawed because of a population of students that is not included or represented. Industry spotlight. Challenges of healthcare information systems. According to LinkedIn, healthcare information systems struggle to provide accurate and complete data. Many fields within patient records are left blank, or the administrative assistant cannot read the patient's handwriting. If you have done any research, you will learn the phrase, "data is dirty." When you ask participants to fill in surveys or forms, you have no idea what kind of data they will be receiving. Therefore, patience, incomplete fields, or spelling mistakes all lead to dirty data. With the advancements of AI and ML, data records can be analyzed for completeness, and fields can be evaluated for proper responses. The use of AI in medical fields is growing rapidly. Tools like ChatGPT have had high success rates in properly diagnosing conditions already verified by doctors. 11 studies have shown that generative AI tools can be used by doctors to help with diagnostic evaluations of patients. These tools are not 100% accurate, and patients should be wary about only using computer-related devices for diagnosis. You should consult a physician if you feel something is wrong. If tools like ChatGPT can decrease medical professionals' research time, they can find a quicker place to start treatment and be able to treat more patients. Medical professionals should proceed with caution because the studies show there is about a 10% chance of wrongful diagnosis. Smart ecosystems, 3D/4D platform quality challenges. When discussing 3D/4D platform systems, there are two areas in which challenges can be analyzed. The first is 3D/4D printing, and the second is 3D immersive gaming. 3D/4D printing is a new exciting concept that allows the materials used in 3D printing to transition or transmute into other shapes or substances. The concept of 4D printing is an add-on to 3D printing with special features. The challenges with this are the materials needed to print in a 3D environment properly and the transitioning period for the print. There are typically special environmental conditions that will trigger the transmutation. The challenge with 3D printing is properly designing the model. Sometimes, these models need to be printed with supports and other features, which is a waste of filament. If that filament is meant for 4D printing, then that expense must be accounted for. The success rate of 3D printing is not 100%. Many conditions will cause the print to fail. One of the biggest issues is the filament absorbing moisture from the air. If the 4D model is based on moisture or water, the transition might be triggered during printing, which would not be the intended outcome. Many 3D models, if not designed properly, are frail and have many weak points. This is not always desirable if the 4D transition is going to depend on the strength of the material. 3D immersive gaming has all the same concerns as the AR/VR platforms discussed previously in the chapter. The 4D aspect of the AR is a condition that triggers an alternative sensory response. It goes beyond just the visual aspects of the Oculus, but it may incorporate sound or touch. This is common on immersive 4D rides found at amusement parks. Providing an experience beyond the 3D interaction has challenges based on environment and materials. Most 4D immersive experiences use air or mists of water to generate their effects, but some go as far as to incorporate pheromones. Metaverse smart ecosystems, platform quality challenges. The metaverse is a big World Wide Web, WWW, edition. The immersive AR/VR culture the platform intends to create is nothing short of a science fiction movie. The WWW and the Internet have had decades to develop and majorly influence modern life. The challenges that the metaverse presents are the issues of adaptability and interoperability and the usability and ease of use areas of the TRM. The metaverse prides itself on being platform independent. It is meant to be used on all IoT devices and all computer platforms. It is reasonable to assume that interoperability will significantly influence how smoothly the metaverse functions and how stable the environment is. The ability to travel seamlessly between virtual worlds and transition from one system to the next will only be as good as the resources introduced into the system. The amount of memory each computer has and cloud technologies will be challenging. The platform will want seamless integration of 3D modeling, and the adaptability of this has been previously discussed in the chapter. A second major concern is that the metaverse is not a traditional medium. It is different than current movies or films produced for large screens. These screens can be as small as a watch face or as large as a city skyscraper. All images in the metaverse are digital. There will be no print media from it. Individuals with disabilities will have to adapt to the new culture, and the level of detail within the models may not meet expectations. The platform will be expensive, and in a world where we struggle to ensure everyone has access to the internet and www, making sure everyone has access to the metaverse is a further stretch. Individuals will hesitate to provide all the information needed to have a metaverse account, and therefore, a lot of unauthentic information will be provided. Alias will be used, and sometimes wrong data will be provided just to gain access. The rate at which the software is being created for metaverse is a definite area of concern in the TRM. Software engineering skills in web technologies, networking, quality assurance, security, and overall software usability need to be increased. Developing these skills is not the biggest challenge. With the advent of the internet, the modern personal computer, and all of the IoT devices, where does the innovation come into play with the metaverse? It will be years before the current world and experiences in it are fully brought into the metaverse, but we need people who are going to look beyond the metaverse to see where it is going. If people get immersed in the metaverse, looking past it for newer technology won't be easy. Link to learning. Read more about the metaverse and how to get started in the immersive culture. This website details how technology will be used to access the metaverse and what steps individuals need to take to move forward with the meta experience. Industry 5.0 Super Society Solutions Era. Industry 5.0 is a new and emerging phase of industrialization that sees humans working alongside technology and AI-powered robots. It also relates to a transformation of industries from production-based to value-based, focusing on social and environmental benefits, i.e. Society 5.0 as well as profit-making. Industry 5.0 aims to enhance workplace processes, increase efficiency, and improve resilience and sustainability. Industry 5.0 relies on various super society solutions that typically operate in a hybrid cloud environment. Therefore, they rely on the application foundations set forth by the OWP for web mobile applications, as well as services that are made available by multi-cloud platforms and smart ecosystem solutions. The concept of a super society is a technologically rich environment. The individuals who live in these societies choose to immerse themselves in technology. The household would often be completely reliant on the IoT and cloud environment software. As we prepare for super societies, think about the science fiction movies we have seen where a computer runs and maintains the entire household. While we are not there yet, the members of super societies work toward this concept. The infusion of cloud-based software applications and the idea of being fully connected to the internet plays a significant role in utilizing or being a member of a super society. Super society autonomous systems, platform quality challenges. The challenges we face with an autonomous system, which is a system that can operate with limited human control, are ever-changing. The theory is that if every car in the world was autonomous, there would be no more accidents. This is a myth because, as we know, computers are prone to failure. Individuals who wish to hack autonomous vehicles will do so to possibly cause harm. Many people cannot manage the sense of not being in control of a vehicle while it is driving, even when they are behind the wheel. Humans, by nature, prefer to be in control of their environments. Autonomous vehicles rely on sensory data to function. This data provides perception, decision-making, and execution of real-time data analysis. The vehicles rely on cloud mapping services for navigation and other cloud data for weather and environmental issues. If any of these channels are interrupted, the vehicle must function based on the last known data. This information may be insufficient, or erroneous data may be used for decision-making. This will change the perception of the vehicle and may lead to the system's inability to make safe decisions. The vehicles are expensive to manufacture. Autonomous vehicles can also refer to drones and smart homes. Any device that could work independently of humans is at risk for false data. With smart homes, there is also the challenge of power outages. While these platforms are in constant development, and many companies are contributing to the enhancement and evolution of these devices, as a society, we need to analyze how we will integrate them into our lives. Theoretically, as the autonomous machinery increases, it should seamlessly fit within the metaverse. The TRM's interoperability and adaptability will be challenged, and data mining and decision-making through more developed AI mediums will continue to challenge the functionality of immersive technology. The great hope for autonomous vehicles, and in reality it is most true, is that autonomous machinery will be faster than human interactive computing and will provide humans the opportunities to repurpose themselves so they do not have to do the tasks these autonomous entities can provide. The issue is that we need more computer scientists studying AI ML and a greater devotion to nanotechnology. All companies must enhance their quality assurance protocols, and the world cannot be the testbed for software. The ISO 22737 2021 Intelligent Transport Systems and ISO 39003 2023 Road Traffic Safety must continue to evolve to handle the newest technology. Standards cannot be an afterthought for autonomous platforms. Super Society Advanced Robotics Platform Quality Challenges. As previously discussed in the chapter, there are two bases of AI in the world: Turing and Lovelace forms of AI. Robotic platforms cannot exist without implementing one of the two types of AI. Since robotics has not been proven to create thoughts spontaneously, the Lovelace form of AI does not seem to be implantable. Therefore, we can assume that AI based on algorithmic analysis will be the current resolution for robotics, with machines working toward the Lovelace form of AI. If we consider humanoid robotics, much can be done with predictive AI and the advancements in neurosciences. The Human Brain Project seeks to find disorders in human consciousness. Although this project is currently on hold because of its ambitious goals, we can still learn from the foundations they established. Henry Markram, creator of the Human Brain Project, spent many years trying to reverse engineer the brain to understand brain disorders like autism. In a 2009 TED Talk, Markram said that he would be able to figure out the brain and create simulations in the form of holograms that will be able to think and talk with you. His foundation did not meet its goals, but it did advance brain model research in previously analyzed areas. This will help with the creation of robotic brains that can think. The challenge is that the neurological community cannot agree on one concise development course. This has led to the delay and dissension of scientists leaving the project. The TRM's quality assurance and software engineering are challenged every step of the way with robotics. An ethical dilemma also comes with all robotics. Do we need a robot that can function the same way as a human? If that is the case when they are developed, will humans become obsolete? Science fiction movies have warned about robots taking over the world. If the quality assurance and software engineering skills increase to a point where a robot is created that can truly think, the world will experience a new set of challenges. Super Society Nanotechnology Platform Quality Challenges. There are many challenges to nanotechnology, NT, platforms and their introduction into society. Nanotechnologies are small, 1/1000th of a meter, devices introduced into technology to help the device function in a modified way, hopefully for the betterment of the technology. The process required to develop such technologies is costly, and many different chemicals are involved. What to do with these chemicals once the manufacturing is done is a constant challenge for the NT companies. The NT contradicts the TRM's thought process about extensibility. NT is created to perform a specific task. It often cannot adapt to new conditions or environments. The NT has a series of functional requirements that it is meant to carry out. Once the NT is introduced into the system, it is difficult to remove the technology. NT developments are under the supervision of universities and private companies. Since there is competition to advance these technologies, there is not a lot of information sharing between the entities involved. The duplication of effort with the advancement of technologies and the fact that many employees are required to sign a non-disclosure agreement when working for these companies. The industry does not see as much of a turnaround of employees moving from one company to the next because most technology is proprietary. There are other ethical challenges with NT that the world does not have answers for. NT can be used to create biological weapons and other powerful weapons. Although these weapons can be developed, the question is, should they be, or why do they need to be? The fear of atomic warfare has shaped the current military forces. Still, the thought of cybersecurity and NT advancing the attack surfaces is scary and challenging to society. The use of NT to enhance human abilities is also in question. Should NT be used to improve the human brain or muscle system? Can we use NT to enhance beasts of burden to work harder and longer during the day? This would create a divide between wealthy people who could afford the NT implants and those who could not. The technology divide between classes would grow even more. The NT's most significant challenge is the simplest of questions. Is it needed? Super Society Supercompute Platform Quality challenges super societies cannot exist without advanced technology. This means that data warehousing and communications must be at the performance scale's extreme top end. Supercomputers, often called clusters or parallel computers, are made to share resources and interconnect processing CPUs. The CPUs are grouped in nodes, where the communication mediums between the nodes are of high quality and have the fastest speeds. The power and speed of a supercomputer is based on the number of nodes the computer possesses. Researchers have tried to enhance the supercomputers through NT and mimic the human nervous system. The neuromorphic systems try to emulate the nervous system and the way the brain works to deliver information. In this area, IBM has done extensive research, creating the IBM True North chip and the Intel Loihi 2 chip. These will eventually replace IBM's Eagle quantum computer, one of today's top supercomputers. The TRM challenges introduced through the supercomputer are availability and quality. Most families do not have supercomputers in their homes and do not have access to them. Therefore, unless you are a research scientist working for these organizations, you will probably never have the opportunity to interface with this type of computer. The second challenge of quality is a difficult challenge to measure. Quality with supercomputers comes in different forms. The first is based on speed and efficiency. If the computer is doing what it needs to do and the outcome is accurate, it is usually okay with the users. The second challenge is correlated with speed, which is information accuracy. Many supercomputers produce data at an alarming rate, and it is difficult to check that data in real time before it can be used in other calculations. Implementing algorithms needs to be unit tested, and quality assurance is a must. Quality has many meanings to different people, and a computer that can perform tasks as fast as a supercomputer can also be used for malicious purposes. Since the cost of these computers is at the extremely high end of the industry, they are mostly found in government agencies and defense agencies. Using a supercomputer to perform hacking techniques could either ensure success because of the raw computer power, or it could be used to supply the ultimate denial of service attacks. Supercomputers are ideal for analyzing big data. Using these computers to perform calculations on data sets that are generally not manageable by regular computers could advance technology and industries in ways that were not previously thought about. The U.S. government, through NASA, has been analyzing the data captured from telescopes to evaluate different areas of the universe. This is scary to some people because they feel the government could use the computers to analyze privacy issues and to spy on people. It will take a visionary in the computer industry to truly utilize the processing power of these computers. As visionaries, we need people to think about capabilities beyond how computers are currently being used and consider how these devices could be used in the future. This is a challenge because most of the industry is extending or adapting the current technology to perform new tasks, not thinking outside the box on what could be possible with the speeds of modern supercomputers. Super Society Autonomous Supersystems Platform Quality challenges the challenges of autonomous supersystems platforms, combine all the previous difficulties and significant complications. Since we have not seen a truly autonomous platform that combines robotics and supercomputers, we are left to think about what-ifs. What can we expect from a system that can think for itself, regulate itself, fix any issues that might arise, and do it faster than humanly comprehensible? Our only hope as a society is the concept that Dell introduced, the responsible computing framework. The ethical implications are endless if we have autonomous supersystems. However, if these systems are built with the proper series of checks and balances, and the technology used to develop the systems is constantly tested for flaws, our only concern is the human factor of implementation. At some point in time, humans will create autonomous supersystems. We can only hope that they are of the highest ethical standards and that introducing these systems is socially acceptable. Suppose individuals adhere to the responsible computing framework and always consider an information security policy when implementing the systems. In that case, we can only hope that the systems will do their needed jobs and do them with the highest ethical standards. Concepts and practice industry certificates combined with degree programs, professional skills are always needed within the industry, and industry certifications seem to be in demand. Cloud technology companies seem to be thriving, but the engineers who will support them do not appear to be growing at the rate of demand. Several companies have openings in roles related to cloud technology. Let's look at what Microsoft offers for different certificates pertaining to the Azure Cloud Services. Microsoft offers a variety of certifications for particular areas when working with its Azure platform. The first recommended certificate is the Azure Fundamentals. This certificate focuses on the learner's skills in cloud concepts, including the benefits of cloud computing and IaaS, PaaS, and SaaS. After this certification, there are a variety of options. The learner can take the Microsoft Azure Data Fundamentals or the Azure Monitoring, Troubleshooting, and Optimizing. There are certificates for storage solutions, subscriptions and resources, third-party connectivity, and virtual machines. Microsoft is not the only company offering skill-based certificates for its technologies. Companies like Google and IBM offer options, and external entities offer programming, software engineering, and security certifications. These certificates are exceptional add-ons to a college education. They help you focus your skill set for the job at hand. The education you receive from a college or university should provide foundational knowledge to build upon. Learning objectives. By the end of this section, you will be able to understand the meaning of cybersecurity, learn how to secure information and communication, learn how cybersecurity can be used to protect software solutions, learn how cybersecurity can be used to protect internet mobile web applications, understand how cybersecurity can be used to protect cloud-centric solutions, relate to cybersecurity as it applies to Industry 4.0 metaverse smart ecosystems, relate to cybersecurity as it applies to Industry 5.0 super society solutions, as discussed in the previous section. Broad-scale adoption of cyber resources brings challenges as it seeks to ensure TRM qualities such as security, performance, and reliability. This section focuses on enforcing cybersecurity assurance, which is the confidence that every effort is made to protect IT solutions against undesirable use. Cybersecurity assurance is an in-depth topic, and due to lack of space, this section will provide only a brief overview. What is cybersecurity? The field of cybersecurity includes the policies, procedures, technology, and other tools, including people, on which organizations rely to protect their computer systems and information systems environments from digital threats. Cybersecurity focuses on 5 categories of security: network, application, critical infrastructure, IoT, and cloud. To assess an organization's cyber risks and develop cybersecurity assurance, you should ask the following questions. What is the threat model? Who are the attackers, and what are their capabilities, motivations, and access? What are the risks, vulnerabilities, and likeliness of breach per risk assessment? What are the technical and non-technical countermeasures, and how much will the countermeasures cost, including both direct and indirect costs? Non-technical countermeasures include laws, policies, procedures, training, auditing, and incentives. Indirect costs can be reputation or future business. What assets do you seek to protect? This question relates to security policies that address confidentiality, integrity, service availability, privacy, and authenticity. Who and what do you trust to help maintain cybersecurity? Cybersecurity threats include behaviors such as breaching privacy by revealing confidential information such as corporate secrets, private data, or personally identifiable information, PII. Damaging integrity, authenticity by destroying records, altering data, or installing unwanted software, e.g. spambot, spyware, and denying access to a service through activities such as crashing a website for political reasons, causing a denial of service attack, or allowing only certain individuals to have access to services. In 2001, the Open Web Application Security Project, OWASP, was launched with the purpose of securing web applications. This model was only concerned with actionable controls and possible risks. The controls were focused on securing the risks involved with the development and deployment of the applications, Table 14. 3. Rank risk: 1. Broken access control, 2. Cryptographic failures, 3. Injections, 4. Insecure design, 5. Security misconfigurations, 6. Vulnerable and outdated components, 7. Identification and authentication, flaws, 8. Software and data integrity failures, 9. Security logging and monitoring, flaws, 10. Server-side request forgery, Table 14. 3. Open Web Application Security Project Top 10 Source, Indusface, OWASP Top 10 Vulnerabilities in 2021, How to Mitigate Them, February 24, 2022, https://www.indusface.com/learning/what are the OWASP Top 10 Risks 2021/link to learning to achieve security. We must eliminate defects and design flaws in systems and make them harder for hackers to exploit. This includes developing a foundation for deeply understanding the networked information systems we use and build. We also must be aware that no system is completely secure. To learn more, read this article about the security mindset from the Journal of Cybersecurity. Why is cybersecurity important? In 2023, the average cost of a data breach was $4.45 million globally, which in just 3 years was a 15% increase over 2020. 12 these costs cover expenses incurred to discover and respond to breaches, lost revenue from downtime, and long-term damages to the business reputation and brand. Cybersecurity Ventures recently shared its top 10 cybersecurity predictions and statistics for 2024, unveiling the alarming fact that global cybercrime financial damage will likely reach $10.5 trillion by 2025. Based on this total, if cybersecurity is regarded as a country, it would rank third, trailing only the United States and China as the world's largest economy. 13 Personally identifiable information, PII, is generally the target of cybercriminals. They collect information, such as names, addresses, identification numbers, and credit card information, and sell them in the dark web or other underground marketplaces. This results in several consequences for these organizations, including regulatory fines, legal action, and the loss of customer trust. Cybersecurity is increasingly important as the cost of breaches increases. However, a comprehensive cybersecurity strategy based on best practices and using machine learning, advanced analytics, and artificial intelligence, AI, can effectively combat cyber threats and reduce the impacts of breaches. Concepts in practice: think like a hacker. To implement effective cybersecurity policies and procedures, cybersecurity experts need to understand hackers, including how they think and how they are likely to target an organization. What does it mean to think like a hacker? Skilled hackers tend to be inquisitive, with an in-depth understanding of technology and its capabilities. They stay abreast of technological advances, including cybersecurity measures. They tend to be creative thinkers with excellent analytical skills, which makes them capable of finding innovative ways to circumvent cybersecurity features and hack into a system. They also tend to understand human nature, including our weaknesses and vulnerabilities. To think like a hacker, you must develop these skills and learn to use them with a hacker mindset, constantly reviewing your system and recognizing how it can be hacked. This includes prioritizing security and remaining aware that hackers constantly look for weaknesses that enable them to exploit a system. As part of this, learn about ethical hacking, which includes penetration testing, and use ethical hacking practices to ensure your system is up to date and ready to withstand cyber attacks. Domains of cybersecurity and associated cryptography techniques. Cybersecurity includes various domains that comprise overall cybersecurity. Common cybersecurity domains include the following: protection of computer systems and networks that ensure security at a national scale, economic health and public safety, called infrastructure security. The National Institute of Standards and Technology, NIST cybersecurity framework is meant to help organizations in this area. Additional guidance is provided by the U.S. Department of Homeland Security, DHS. Protection of wired and wireless Wi-Fi computer networks from intrusions, called network security. The designs for operating systems, virtual machines, and monitors must include protections against unauthorized use. Protection of applications on-premise and in the cloud, with security integrated during the design phase for data handling and user authentication, called application security. The process of authentication confirms the identity and authorization of people and devices that use a system. Many resources support these efforts, including books and online materials on security engineering, robust programming, and secure programming for specific operating systems. Protection of the data, digital files, and other information a system maintains, called information security. For example, database systems must protect against SQL injection by ensuring that queries issued to the database do not somehow contain malignant code that could compromise the security of the database and its infrastructure. Information security requires data protection measures, such as the General Data Protection Regulation, GDPR, that secure sensitive data from unauthorized access, exposure, or theft. These domains function cooperatively to create a cybersecurity risk management plan, Figure 14. 7. Illustration of components of a cybersecurity risk management plan. Identification, evaluation, mitigation, monitoring, Figure 14. 7. Cybersecurity should be based on a comprehensive risk management plan that identifies and evaluates cybersecurity risks, designs and implements practices to mitigate those risks, and monitors the system and identifies areas that need to be updated. Attribution, copyright Rice University, OpenStax, under CC by 40 license. An important pillar of cybersecurity assurance is non-repudiation, which provides proof of data's origin, authenticity, and integrity. Non-repudiation is achieved through cryptography using, for example, digital signatures, which are used in online transactions to ensure that a party cannot later deny placing an order or denying its signature's authenticity. In addition to digital signatures, non-repudiation is also used in digital contracts and emails. Email non-repudiation involves methods such as email tracking to assure senders that messages are delivered and also provides recipients with proof of the sender's identity. This ensures neither party can deny that a message was sent, received, and processed. Beyond basic securing of information systems, cybersecurity requires creating and governance of processes that protect organizations and individuals against costly breaches. End-user education is a critical part of this process. Organizations must promote security awareness to enhance endpoint security. For example, training users to delete suspicious email attachments and avoid using unknown USB devices can help. Disaster recovery and business continuity planning are also essential to minimize disruption to key operations. This requires tools and procedures to respond to cybersecurity incidents, natural disasters, and power outages. Data storage is another critical area. Protection measures that promote data resilience with safeguards include encryption and immutable and isolated data copies that can quickly be restored to recover data and minimize the impact of a cyber attack. Evolvability is an important cyber quality, but the evolution of platforms on which information systems may be deployed creates a need for new security measures. For example, mobile solutions security requires specific protection measures to protect applications, containers, and mobile mail. Furthermore, when using the cloud, organizations must ensure confidential computing by encrypting data at rest, i.e., while data are stored in the cloud, during transfer, and during processing. This ensures that processes meet business requirements and regulatory compliance standards and supports customer privacy. Cybersecurity misconceptions. Because of the constant evolution of technology, there are also several misconceptions surrounding cybersecurity risks. Threats only come from outside the organization. Instead, breaches can involve people within the organization working maliciously with external hackers or organized groups. Risks are known and can be predicted. In reality, the attack surface is constantly expanding with new vulnerabilities, and human error by negligent employees or contractors can also increase the risk of data breaches. Attack vectors are limited. Cybercriminals constantly discover new attack vectors through various environments. The industry is safe. Every industry faces cybersecurity risks, and adversaries exploit communication networks across the governments and private sector. Ransomware attacks are expanding to nonprofits and local governments, and threats are increasing in other areas. 14. Supply chain and security issues. After the COVID-19 pandemic, companies still struggle to get necessary goods and services. Many products are still in ports and warehouses waiting to be delivered because there are not enough truck drivers in the workforce. In the wake of the chip manufacturing plant shortage, the automobile industry started to recover in 2023. For many months, car dealership lots were empty of new cars. There is a constant strain on workers to get goods and materials to the customers quicker. Amazon has set a precedence for the delivery rate of goods that the rest of the world is struggling to keep up with. The world has seen increased cyber threats because more businesses are being conducted online. If you go to any sports stadium or concert event, most of them involve cashless transactions. All transactions must be done with credit or debit cards. This means there are many more chances for your information to be leaked because of the number of companies with which you are interfacing. Granted, it is your choice to use these businesses, but remember, security is only as strong as its weakest link. As our culture demands we go to cashless transactions, the number of available attack surfaces for hackers increases. If we implement the concepts of super societies and immerse ourselves in this technology, then if a security vulnerability compromises us, it may do irreparable harm to our lifestyle. Common cyber threats are constantly evolving, and there are various common cyber threats of which programmers should be aware. Malicious software variants such as viruses, worms, trojans, spyware, and botnets that allow for unauthorized access or can damage computers is called malware. Modern malware attacks often bypass traditional detection methods, such as antivirus scans for malicious files, by being fileless. Types of malware include the following. Viruses contain code that propagates or replicates across systems by arranging to have itself eventually executed, creating additional, new instances of itself. It generally infects by altering stored documents or code, e.g., boot sector or memory resident code, typically with the help of a user. Worms contain code that replicates itself across a network, infecting connected computers without user intervention. Rootkits modify the operating system, e.g., modify system exploration utilities, replace the target OS with a virtual machine monitor that can attack systems to hide their existence. A backdoor is a concealed feature or command within a program that enables users to execute actions they normally would not be permitted to do, sometimes called a trapdoor, e.g., Easter egg in DVDs and software. A Trojan horse is software that seems to serve a beneficial purpose, but is designed to execute covert malicious activities. An example is spyware, which can be installed by seemingly legitimate programs and then provides remote access to the computer for activities such as keylogging or sending back documents. Botnets involve a network of compromised machines, bots, under unified control of an attacker botmaster. Once the botmaster has control, the attacker has access to the devices in their system, enabling the attacker to steal data, execute scams, and perform other malicious tasks. The scenarios that enable malware to run include a vulnerable client, such as a browser, connecting to a remote system that delivers an attack, exploitation of a network-accessible service with buffer overflow vulnerability, malicious code introduced into a system component during manufacturing, through a compromised software provider, or via a man-in-the-middle (MIT-M) attack. Using the auto-run functionality, especially through the insertion of a USB device, deceiving a user using social engineering into running or installing malicious software. And an attacker with local access directly downloading or running malicious software, potentially using a local root exploit for elevated privileges. Some of the dangers that can occur as a result of malware include generating a pop-up message with a brag, exhort, or extort, trashing files, damaging hardware, launching external activity, stealing information, and keylogging via screen, audio, or camera capture or via file encryption, such as ransomware. Malware that encrypts data and demands a ransom to unlock or prevent data exposure is called ransomware. An insider threat is posed by current or former employees, partners, or contractors who misuse their access. It can also include vulnerabilities intentionally created by programmers, such as malware, the form of social engineering that tricks users into providing personal information through fake emails or text messages posing as legitimate companies is called phishing. Additional threats included a distributed denial of service (DDoS) attack, which overloads a server with traffic to crash a server, website, or network. Multiple coordinated systems often overwhelm enterprise networks by attacking devices such as modems, printers, and routers that use the Simple Network Management Protocol (SNMP). An advanced persistent threat (APT) is used by intruders to infiltrate systems to spy on business activities and steal sensitive data while remaining undetected and leaving the networks and systems intact. A man-in-the-middle attack is used by cybercriminals to eavesdrop on and intercept communications between two parties in order to steal data, most often on unsecured Wi-Fi. Global issues in technology skills gap. A big challenge in technology is the growing issue of the skills gap. There is a mismatch between what is needed in the industry and what students learn in colleges and universities and industry certificates. Many companies are advertising for software engineers with 3 to 5 years experience and not entry-level positions. The demand on companies forces them to look for workers who can hit the ground running with little supervision. The need for entry-level jobs is increasing, but the pay scale is not what people can afford to take after graduating from college. The amount of debt students are accruing to earn their degrees is increasing, and students are forced to take jobs they know they won't like, only to get the experience to jump to a better-paying job. The skill gap is increasing in the areas of cybersecurity and data analytics. The cybersecurity skills gap is framed from the perspective of individuals in the industry repurposing themselves. People who have been in the computer industry are retooling themselves to be part of the cybersecurity demands. If you are an IT professional with years of experience and have a certificate or degree in cybersecurity, it is hard to start over at the lower end of the job pool. These individuals want management or higher-end jobs, but they have only entry-level skills. This creates a divide because these individuals have the experience to be successful in the industry and don't need as much assistance as a pure entry-level employee. Key cybersecurity technologies and best practices. Key cybersecurity technology and associated best practices typically fall under 3 categories: identity and access management, a data security platform, and security information and event management. The technology used to manage users, roles, and access privileges is identity and access management, IAM. Approaches used to allow access to systems include single sign-on SSO, multi-factor authentication, privileged user accounts, and user lifecycle management. SSO keeps users from entering their credentials multiple times within the same session. Multi-factor authentication leverages multiple access credentials provided via different devices. Privileged user accounts are only accessible to specific users. User lifecycle management handles user credentials from initial registration to retirement. Cybersecurity professionals use IAM tools to investigate and respond to security issues remotely and contain breach damages. A data security platform is meant to automate the proactive protection of information via monitoring and detecting data vulnerabilities and risks across multiple environments, including hybrid and multi-cloud platforms. The protection provided by a data security platform simplifies compliance with data privacy regulations and supports backups and encryption to keep data safe. The practice of security information and event management, SIEM, focuses proactively on the automated detection and remediation of suspicious user activities based on the analysis of security events. SIEM solutions typically analyze user behavior and use artificial intelligence, AI, techniques to detect and remediate suspicious activities according to the organization's risk management guidelines. SIEM tools may be integrated with security orchestration, automation, and response (SOAR) platforms designed to fully automate the management of cybersecurity incidents without human intervention. Some organizations also choose to use a zero-trust strategy, which assumes the system is compromised and sets up controls to continuously validate every user, device, and connection in the system for authenticity and purpose. Linked to learning cybersecurity is big business, and many companies in the technology industry have developed cybersecurity solutions and services that they sell to other organizations. In particular, IBM provides a variety of such solutions and services to cover all aspects of cybersecurity, including AI and cloud security. Securing information and communication cryptography is an essential tool for securing information systems, which use codes to protect data and other information. With cryptography, information is encrypted and accessible only by those authorized to decrypt and use the information. Cryptography can help ensure properties such as confidentiality, i.e., secrecy, privacy, integrity, i.e., tamper resilience, authenticity, availability, and non-repudiability, or deniability. As shown in Figure 14, the components of cryptography include the following. Plaintext refers to the data that need protection encryption, handled by an algorithm, and creates ciphertext and an encryption key for plaintext ciphertext. Uses an encryption key to scramble plaintext decryption, also handled by an algorithm, and uses a decryption key to transform the ciphertext back into plaintext encryption key, value known to the sender of the data. By inputting the encryption key into the encryption algorithm, the sender converts the plaintext into ciphertext decryption key, value known to the receiver of the data. By inputting the decryption key into the decryption algorithm, the receiver converts the ciphertext back into plaintext illustration of cryptography components. Sender, plaintext, encryption algorithm, encryption keytext, ciphertext, interceptor, decryption algorithm, decryption keytext, plaintext receiver. Figure 14. Cryptography is a process that enables senders and receivers to secure digital data by using encryption and decryption algorithms. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit key icon. Modification of accessible by PH letter 1EA1M Than L letter 1ED9C/Wikimedia Commons, CC by 4. Cryptography can be used to create different types of ciphers, including the following. Substitution. Ciphertext is created by substituting plaintext characters, bits, or character blocks with alternate characters, bits, or character blocks. The substitution can be monoalphabetic, meaning that if the letter D is enciphered as P in one part of the ciphertext, D will be used for P throughout the message. The substitution can also be polyalphabetic, meaning that while D may be enciphered as P in one part of the message, in another part, D may be encoded as a different letter. Transposition. Instead of substituting the letters and characters, they are rearranged using a specific algorithm, such as writing a message vertically to produce a ciphertext that is read horizontally. Transposition ciphers are also known as permutation ciphers. Polygraphic. substitution is performed on two or more blocks of letters simultaneously. Cryptography can also be performed using asymmetric encryption, also known as public key cryptography, which uses private and public keys. With public key cryptography, the sender and receiver have a pre-shared secret key to handle encryption and decryption. In public key cryptography, the sender uses the receiver's public key to encrypt the message and then send that ciphertext to the receiver. Only the receiver has the private key that is needed to decrypt the message. Authentication and passwords authentication confirms the identity and authorization of people and devices that use a system. It is a vital two-step process to help ensure that only authorized users have access to a system. Authentication first requires identification, followed by verification to establish and confirm a user's unique credentials and ensure the user is authorized. A password is a secret string of characters used to gain entry into a system. It is a critical part of authentication. To function as a cybersecurity tool, passwords must be secure, which can be challenging. Attackers can steal passwords by guessing, installing a hardware or software keylogger, finding written passwords, obtaining them via social engineering phishing, intercepting the password over the network, or stealing them from a service or third party. To address these cyber threats, the DHS's Cybersecurity and Infrastructure Security Agency offers 3 tips for passwords. 15. Create long passwords with at least 16 characters. Make passwords random by following NIST's recommended password rules. Ensure that passwords are unique by using a different password for every access point in a system. Access control, a vital part of cybersecurity, is access control, which regulates the people and devices that can use a computer system's resources. The 3 most common access control designs include the following. Mandatory Access Control, MAC, is a strict system where security decisions are fully controlled by a central policy administrator, making it impossible for users to set permissions irrespective of ownership. Discretionary Access Control, DAC, is a system where users can set permissions for their files, including granting access rights to other users on the same system. DAC is the most common access control design approach in commercial operating systems. While generally less secure than mandatory control, DAC is easier to implement and more flexible. Role-based access control, RBAC, is a system in which access depends on an individual or group's role in an organization and the access they need to meet job requirements. Typically, roles with more responsibility and authority have greater access to the system. The typical attacks launched against cryptography generally involve the following: brute force, e.g. try all possible private keys; mathematical attacks, e.g. factoring timing attacks, e.g. based on knowledge of the time it takes to decrypt; hardware-based fault attack, e.g. take advantage of faulty hardware to generate digital signatures; chosen ciphertext attack, e.g. gather information by obtaining the decryptions of chosen ciphertexts and attempt to recover from this information the secret key used for decryption; architectural changes, e.g. use knowledge of vulnerabilities. Anonymity and privacy. Protecting anonymity and privacy is an important aspect of cybersecurity. Being able to interact on the internet, even publicly, while concealing your identity is considered anonymity. Anonymity is not the same as secrecy confidentiality. As discussed previously, confidentiality is about message contents, i.e., what was said. Anonymity is about identities, i.e., who said it and to whom, and must be preserved to ensure certain civil liberties such as autonomy, free association, free speech, and freedom from censorship and surveillance. There is a wide spectrum of anonymity, including linkable anonymity, e.g. loyalty cards, prepaid mobile phone, e.g. pen names on blogs; unlinkable anonymity, e.g. paying in cash; and veronymity, e.g. credit card numbers, driver licenses, addresses. By remaining anonymous, users make it difficult for hackers to steal their personal data, e.g. passwords, credit card information. It also allows users to preserve their civil liberties, e.g. free speech and association, on social media. Anonymity can also be important for people concerned about their safety and do not want to create safety risks because of their online activities. Keeping your actions online, such as messages intended only for certain individuals, concealed from the public, is called privacy. Privacy is regarded as a basic human right, while not explicit in the U.S. Constitution. Privacy rights are implied by the personal protections offered in the First, Third, Fourth, Fifth, and Ninth Amendments in the Bill of Rights, as Figure 14. 9 shows privacy is related to anonymity, but is a separate concept. Both anonymity and privacy are important to promote cybersecurity. Illustration shows overlapping circles. Privacy, keeping online actions concealed from the public, and anonymity, allowing online actions to be visible to the public but cannot be attributed to any individual. Figure 14. 9. Privacy and anonymity are related concepts that are important to promote cybersecurity. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. Internet anonymity is difficult, if not impossible, to achieve for average users, but it seems easy for unethical people. Anonymity is a state-of-the-art technique that relies on proxy intermediaries that relay internet traffic through trusted third parties. Generally, the process requires setting up an encrypted virtual private network, VPN, to the third party's site, and all your traffic goes through it. To understand how unethical people use proxies, assume a scenario depicted in Figure 14. 10. Where Alice wants to message M to Bob. Bob does not know that the message M is from Alice, and Eve is short for eavesdropper, cannot determine that Alice is communicating with Bob. HMA accepts messages encrypted for it, then extracts the corresponding destination addresses and forwards the message accordingly. Illustration shows Alice sends an encrypted message, M, to Bob. VPN HMA extracts destination addresses. Bob receives the message. Figure 14. 10. When Alice sends a message to Bob, HMA accepts encrypted messages, then extracts the corresponding destination addresses and forwards the messages accordingly. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Anonymity is meant to counter the type of surveillance that is mandated as part of the Patriot Act, Section 215, and National Security Letters or NSLs, and the FISA Amendment Act. An older Google Transparency Report, Table 14. 4, shows the number of NSLs that FBI agents issued without a judge's approval to obtain personal information. Reporting period. National Security Letters users. Accounts January to June 2016, 499, 500, 999. July to December 2015, 499, 500, 999. January to June 2015, 499, 500, 999. July to December 2014, 499, 500, 999. January to June 2014, 500, 999, 500, 999. July to December 2013, 500, 999. 10001. 499. January to June 2013, 499, 500, 999. July to December 2012, 499, 500, 999. January to June 2012, 500, 999. 10001. 499. July to December 2011, 499, 500, 999. January to June 2011, 499, 500, 999. July to December 2010, 499. 10001. 499. January to June 2010, 500, 999. 501. 999. July to December 2009, 499, 500, 999. January to June 2009, 500, 999. Table 14. 4. Google Transparency Report. Data from Google. NSLs cover everything except the contents of your communications, i.e., if, when, how much, who. These data are included in the exception because such metadata often provides privileged information that is essentially, according to the FTC, a proxy for content. In fact, the U.S. National Security Agency, NSA, collection of bulk call data was ruled illegal in 2015. Encryption tools such as Pretty Good Privacy, PGP, which was introduced earlier, can be used. NewPG is a free software recreation of PGP created by Phil Zimmerman, 1991. These tools allow users to encrypt emails to hide their content by creating a hash of the email's content and using digital signatures to sign the hash. Both the message text and the digital signature attached to the message are protected using hybrid encryption. Digital signatures require public key cryptography, which has separate public and private keys. Before sending a message, the message is signed with the signature key, and both the message and its signature are encrypted with the recipient's public encryption key. Once the message is received, it is decrypted with the private key to extract it and its signature. The sender's public verification key is then used to check the signature's authenticity. Fingerprints must be used to secure this process further. because Bob's public key can be obtained from his website, it needs to be verified via out-of-band communication of fingerprints. A fingerprint is a cryptographic hash of a key. To support this approach, you need key servers that store public keys to look up keys by name, email address, and verify them with fingerprints. If you do not know Bob personally, you can rely on the Web of Trust, WOT, or Friend of a Friend mechanism, i.e., Bob introduces Alice to Caro by signing Alice's key. There are drawbacks to just using encryption because Bob's private key may be compromised. In that case, the specifics of the keys may become known, and past messages may be decrypted and read. Because the sender's signature is available as part of the messages sent, it also becomes possible to prove the sender's identity, which defeats the security scheme. This attack exposes many incriminating records, including the key material that decrypts data sent over the public internet and signatures with proofs of who said what. There is nothing better than off-the-record conversations where Alice and Bob talk in a room and no one else can hear them. In that case, no one else knows what they say unless Alice or Bob tells them. Furthermore, no one can prove what was said, not Alice or Bob. Based on this, desirable communication properties are as follows. Deniability makes it plausible to deny having sent a message. Forward secrecy allows past messages to be safe even if key material if compromised. Mimic off-the-record conversations to facilitate deniable authentication. Make it possible to be confident of who you are talking to, but unable to prove to a third party what was said. One technique is to use off-the-record OTR messaging. Use authenticated Diffie-Hellman (DH) protocol to establish a short-lived session key. Diffie-Hellman is a security algorithm with only one symmetric private key that is shared by both participants, e.g. Alice and Bob. Alice and Bob agree on values for prime number p and a generator number g, or base, where 1g, p, and g is any number agreed upon by both parties that is a generator of p. The number g is a generator of p because, when raised to positive whole number powers less than p, it never produces the same result for any two such whole numbers. For ease of computation, g is usually chosen small, and the order of g should be prime and approximately p2. Alice and Bob pick private values x and y respectively, and they generate a key and exchange it publicly. So Alice selects x and generates public key, a equals gx modulo p, and Bob selects y and generates public key b equals j modulo p. For example, if p equals 23 and g equals 9, the private keys for Alice and Bob are respectively 4 and 3, and the secret keys for Alice and Bob are both 9. During the DH key signed exchange, the only pieces of information that are exposed to the public and susceptible to interception by malicious actors are X, Y, P, and G, none of which are sufficient to recover Alice and Bob's private keys. It is also not enough information to recover the shared, symmetric, secret SS cryptographic key. SS can then be used by Alice and Bob to send encrypted messages to each other safely, which is done using a secret key encryption algorithm, using a hash of SS as the encryption key EK to transmit ciphertext. The strength of the scheme comes from the fact that Gx modulo p equals Gx, y modulo p is a one-way function that takes an extremely long time to compute invert using any known algorithm, just from the knowledge of p, g, Gx modulo p, and J modulo p. Illustration of session key. One symmetric private key is shared by Alice and Bob. They agree on values for p and g, they pick private values x and y, and they generate a key and exchange it publicly. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Then Alice uses secret key encryption on message M and sends it across as EK-M, and authenticates the message using a message authentication code EK-M, where MK is computed as a hash of the EK, HEK, illustration of secret key on message M. Alice sends it across to Bob as EK-M and authenticates the message using a message authentication code MAC MK EK-M, where MK is computed as a hash of the EK, HEK. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Rekeying is performed using the DH protocol to exchange new private values x and y. Illustration of rekeying using DH protocol to exchange new private values x and y between Alice and Bob. Attribution. Copyright Rice University, OpenStax, under CC by 40 license publishing the old MK. Illustration of Alice publishing the old MK. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Note that OTR is more applicable to interactive communication than email. It provides message authentication, confidentiality, deniability, and forward secrecy. However, there are no practical examples of deniability. OTR is built into Adium and Pigeon. In that case, some defaults apply. In particular, logging is enabled by default, and etiquette dictates you should disable this, as do past instances where people's activities were discovered using those logs. E.g., Chelsea Manning, who leaked classified information, was discovered after the Army reviewed access logs. It is very different from Google Hangouts' OTR feature, which does not allow the conversation to be logged. An interesting anonymity solution is the protocol behind the Signal app, iPhone, Android, which uses the double ratchet algorithm set forth by Trevor Perrin and Moxie Marlinspike. It provides forward secrecy, i.e., today's messages are secret, even if the key is compromised tomorrow. Future secrecy, i.e., tomorrow's messages are secret, even if the key is compromised today. Deniability, no permanent transferable evidence of what was said. And usability, i.e., tolerates out-of-order message delivery. Another interesting idea for anonymity is achieved via plausibly deniable storage. In this case, the goal is to encrypt data stored on your hard drive. Someone can be compelled to decrypt it. The idea is to have a decoy volume with benign information, e.g., Vera crypt. Note that it may be worthwhile to differentiate sender from receiver anonymity. An interesting example of a protocol that achieves sender anonymity is described by David Chaum as the dining cryptographer's problem. 16 in this case, 3 cryptographers dining together are told that payment will be made anonymously by either one of them or the agency that employs them. As they respect each other's right to make an anonymous payment, but wonder if their agency will be paying, they carry out the protocol described to achieve sender anonymity. A naive solution to achieve anonymity for browsing is to use VPNs. Organizations providing these may receive court orders asking for information relating to an account, and they will cooperate with law enforcement if they receive a court order. A better approach is to use Tor by downloading the Tor browser bundle or becoming a volunteer in the Tor network. Tor is built on a modified version of Firefox and is a low-latency anonymous communication system that hides metadata, i.e., who is communicating. As noted earlier, you may get in trouble when an encrypted message you are sending is intercepted and the included metadata are exposed. To avoid this, Tor completely hides the existence of communication, e.g., web connections. Tor operates at the transport layer and makes it possible to establish transmission control protocol, TCP connections, without revealing your IP address. The Tor network relies on many nodes, i.e., onion routers, operated by volunteers and located worldwide. The Tor approach becomes useful if Alice wants to connect to a web server without revealing her IP address. Simply speaking, onion routing figure 14. 11 generalizes to an arbitrary number of intermediaries, mixes, or mixnets. Alice ultimately wants to talk to Bob with the help of HMA, Dan, and Charlie, and as long as any of the mixes is honest, no one can link Alice with Bob. Illustration of Tor approach. Tor network relies on many nodes, onion routers, operated by volunteers. Alice sends message to Bob with the help of HMA, Dan, and Charlie, figure 14. 11 users can achieve anonymity by using Tor. This is what the industrial-strength Tor anonymity service uses. It also provides bidirectional communication. The key concept here is that no one really knows both you and the destination. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Tor end-to-end paths are called circuits, and Tor almost always uses 3 hop circuits, i.e. k equals 3. Tor balances anonymity, i.e., k not too small so as to be traceable, and latency, i.e., k not too large. The last node in a Tor circuit is called an exit node. To the outside world, the Tor exit node is initiating connections to destinations. Every peer in the Tor network gets to decide whether to be an exit node or to just relay between other Tor nodes. Tor exit nodes also determine what IP addresses websites to exit. Tor clients learn about other Tor peers by downloading a list of them. 17. The list provides information for each one of the Tor routers, such as IP address and hostname, the country where it resides, the uptime, the average throughput, websites it is willing to be an exit node for, and the node's public key. Tor's attack model is more relaxed than the models used by typical mixnets. In particular, Tor does not assume a global, passive attacker. It does assume that a limited subset of the Tor nodes are malicious, and that there may be some level of eavesdropping on small portions of the links, but not a global view of all traffic. This relaxed attack model, which assumes a less powerful adversary, makes it possible for Tor to achieve better performance. That said, there are a few aspects that Tor does not cover as compared to typical mixnets. Tor does not batch or delay packets. If only one client were to communicate over Tor, there would be no anonymity. The philosophy behind the Tor relaxed attack model is to assume that if the performance is reasonable enough, users will be more likely to adopt it. The more users adopt it, the more cover traffic there will be, making it harder for an attacker to map packets to any one sender. Figure 14.12 summarizes how Tor works at a high level. Illustration of multi-step Tor process. Step 1. Alice's Tor client requests and receives Tor nodes from the directory server. Step 2. Alice's Tor client uses a random path to the target server. Step 3. If user visits another site, Alice's Tor client selects another random path to target server. Figure 14.12 Tor is a multi-step process that enables users to achieve anonymity online. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit key icon. Modification of accessible by PH1EA1M Than L1ED9C/Wikimedia Commons, CC by 40. Credit, reproduced with permission from Dave Levin. Tor implements the following trust protocol. Entry node knows that Alice is using Tor and also knows the identity of the middle node, but does not know the identity of the destination. Exit node knows that some Tor user is connecting to the destination, but does not know which user. Destination knows a Tor user is connecting to it via the exit node. It should be noted that Tor does not provide encryption, e.g., use HTTPS between the exit node and the destination. We discussed earlier how senders can hide their identities. Similar to that, Tor is also a means of allowing destinations to hide their identities. An example was the Silk Road, an eBay-like online store where users could purchase illicit and illegal goods and pay for them using bitcoins. Running such a website requires a certain degree of anonymity. Therefore, it was run as what is known as a Tor hidden service. Hidden services have since been renamed to onion services. 18. Interestingly, onion services can achieve receiver anonymity using techniques that achieve sender anonymity. Figure 14. 19 illustration showing how Tor hidden services, or onion services, achieve receiver anonymity using techniques that achieve sender anonymity. Figure 14. Tor hidden services, also known as onion services, achieve receiver anonymity using techniques that achieve sender anonymity. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Note that there are various known onion routing attacks and other issues as follows. Attacks. Rubber hose cryptanalysis of mix operators. As a defense, use mix servers in different countries. Adversary operates all of the mixes. As a defense, has lots of mix servers. Adversary observes when Alice sends and when Bob receives and links the two together. Side channel attack exploits timing information. As a defense, pad messages or introduce significant delays. Tor does the former, but note that it is not enough for defense. Issues include impaired performance, i.e., messages may bounce around a lot, and traffic leakage. Suppose all of your HTTPS traffic goes through Tor, but the rest of your traffic does not. Concerning the traffic leakage problem, Tor's solution is to inspect the logs of their DNS server to see who looked up sensitive com just before your connection to their web server arrived. The hard general problem is that anonymity is often at risk when an adversary can correlate separate sources of information. To summarize, Tor hides metadata, i.e., the what or message content via TLS-PGP OTR signal, and also hides the who via the onion routing protocol. It also provides a messaging system called POND, figure 14. 14, which hides the when and how much parts is illustrated. Note that POND is not an email. Rather, it is a forward, secure, asynchronous messaging system. POND seeks to protect the possibility of leaking traffic info against all but a global passive adversary, i.e., forward secure, no spam allowed, and messages expire automatically after a week. Illustration of forward, secure, asynchronous messaging system, POND, which hides when and how much parts. Figure 14. 14 POND is a forward, secure, asynchronous messaging system that seeks to protect against leaking traffic information. Attribution, Copyright Rice University, OpenStax, under CC by 40 license. Credit, reproduced with permission from Dave Levin. Zero Knowledge Proofs. A zero knowledge proof, ZKP, is a cryptographic system that functions as a useful tool to protect privacy. With ZKPs, users rely on cryptographic algorithms to verify information without accessing the supporting data. Digital signatures based on PKI, i.e., RSA algorithm or ECC, are examples of ZKPs. In these cases, the person holding the private key can convince any public key holder that they know the private key without revealing it. Properties of ZKPs include completeness. A statement is true if an honest prover can convince an honest verifier. Soundness. If the prover is dishonest, he cannot fool the verifier. Zero knowledge. No private information is revealed to the verifier. To understand ZKPs, it is important to know about the PCP theorem, which states that every decision problem in the NP complexity class has probabilistically checkable proofs of constant query complexity and logarithmic randomness complexity. For an error probability of 2k, 3k bit positions must be verified. For example, the soundness error probability of 240 approximately 1012 with 120-bit verification. Computational integrity proofs are probabilistic proof systems based on the PCP theorem, allowing a prover to convince a verifier of the correctness of an arbitrary computation with an exponentially faster efficiency than naive checking of the computation. Computational integrity proofs exhibit the following properties. Completeness. A statement is true if an honest prover can convince an honest verifier. Soundness. If the prover is dishonest, they can't fool the verifier. Succinctness. There is exponentially faster verification than naive checking of the computation. Zero knowledge. Bonus. No information is revealed to the verifier. ZKPs rely on a transcript of the original computation expanded into a proof using an error-correcting code, e.g. a Reed-Solomon code, polynomial commitment, which spreads any errors within the proof. A low number of e.g. 3 of stochastic queries by the verifier is sufficient to prove the correctness of the computation with high probability, figure 14. 15. Computational problems. Problems need to be first converted into the right form. The form is called a quadratic arithmetic program, QAP, and transforming the code of a function into a QAP is highly non-trivial. It requires turning the computation into an algebraic circuit and transforming it into a rank 1 constraint system, R1CS, that can then be converted into a QAP. In addition to the process for converting the code of a function into a QAP, another process may run alongside in such a way that if you have an input to the code, you can create a corresponding solution, sometimes called witness, to the QAP. Once this is done, another fairly intricate process must be followed to create the actual zero-knowledge proof for the witness and a separate process for verifying proof that someone else passes along to you. The full machinery between ZK-SNARK is illustrated in Figure 14. 16. Illustration of full machinery between ZK-SNARK includes computation, algebraic circuit, R1CS, QAP, linear PCP, linear interactive proof, ZK-SNARK. Figure 14. 16 ZK-SNARK full machinery includes computation, algebraic circuit, R1CS, QAP, linear PCP, and linear interactive proof. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Credit, reproduced with permission from Dave Levin. ZK-SNARKs are not transparent and require a so-called trusted setup to secure the randomness of the parameters determining the selection of queries in the verification procedure. The random parameters are, for example, generated using a hash function. However, the knowledge of the original values fed into the hash function, toxic waste, must be kept secret. Otherwise, retrieving the random parameters and manipulating the selection of verification queries would be possible. A trusted setup is a multi-party computation, MPC, ceremony which recursively generates random parameters. If at least one party is honest and forgets its input values, the randomness of the trusted setup is safe. Universal trusted setups can be generated once and can be reused for other applications as well. Non-universal ones are tied to the specific circuit. The difficult part is to generate a ZK-SNARK with reasonable resources for real-world applications. Zero-knowledge scalable transparent argument of knowledge, ZK-SNARK, is a type of ZKP where one party can prove to another that a given statement is true without revealing any other information other than the fact that the statement is true. Attributes of the ZK-SNARK concept are as follows. Zero-knowledge refers to privacy preservation. Scalability indicates that verification time is substantially less than the time taken for naive computations. Transparency reflects the lack of a trusted setup requirement. Argument and knowledge related to the security and robustness of the cryptographic scheme. Zero-knowledge STARKs work by leveraging linear cryptography, specifically collision-resistant hash functions, to validate the truth of a statement without sharing the details behind it. Unlike zk-SNARK, zero-knowledge succinct non-interactive argument of knowledge, which rely on an initial trusted setup and are theoretically vulnerable to quantum computer attacks, zk-SNARK eliminate these issues. That said, it is important to note that this leaner approach results in a significant disadvantage. Specifically, zk-SNARK generate proofs that are typically 10 to 100 times larger than those created by zk-SNARK, thus making them more expensive and potentially less practical for certain applications. The trade-offs between different properties of different non-interactive and transparent proof systems amount to a difference in verification time between 2 ms to 250 ms, prover time 1s to 100s, and proof size between 200B to 250 KB. The cryptographic primitives used by ZKPs include the following cryptographic primitives: collision-resistant hash function, quantum secure, Stark, fractal, elliptic curve cryptography, bulletproofs halo, knowledge of exponent pairing groups, Groth 16, sonic Marlin Plunk, groups of unknown order, supersonic, lattice-based cryptography, quantum secure. Under development, there are myriads of recent applications of ZKPs to blockchain technology for privacy and scalability improvements. A related topic is verifiable delay functions, VDFs, which emerged in June 2018. A verifiable delay function, VDF, is a function f, x right arrow y that takes a prescribed minimum time to compute, even on a parallel computer. However, once computed, anyone can quickly verify the output. They can prevent fraud or front-running on exchanges, online auctions, games, or prediction markets. Another related topic is multi-party computations, MPCs, which are methods for parties to jointly compute a function over their inputs while keeping those inputs private. MPCs are different from traditional cryptographic tasks that use cryptography to ensure the security and integrity of communication or storage, and assume that the adversary is outside the system of participants. In MPC, cryptography protects participants' privacy from each other. An example of an application is that of a trusted setup ceremony, which is a secure MPC. An important related topic is fully homomorphic encryption, FHE, the holy grail of cryptography. FHE allows arbitrary mathematical operations on encrypted data, i.e., for every f. Y equals fx, encrypted y equals fx, open problems in cryptography. The ongoing attacks and the need to defend crypto schemes require staying on top of best practices. Ideally, developers should write code that can be changed easily. Also, remember not to develop your own cryptographic mechanisms. Go through peer review and apply Kirchhoff's principle. Do not even implement the underlying crypto, and do not misuse existing crypto. Information about a particular implementation could leak, e.g., power consumption, electromagnetic radiation, timing, errors. Attacks based on this are referred to as side-channel attacks. As an example, simple power analysis (SPA) may be used to interpret power traces during a cryptographic operation. Simple power analysis, figure 14. 17 can reveal the sequence of instructions that have been executed. Graph shows simple power analysis revealing specific instructions, jump taken, no jump taken, figure 14. 17 simple power analysis can reveal specific instructions such as those shown here. Attribution, copyright Rice University, OpenStax, under CC by 40 license, credit. Reproduced with permission from Dave Levin. Assuming the program execution path depends on the inputs, i.e., key data, SPA can be used to reveal the keys. Different from SPA, which visually inspects a single-run differential power analysis, DPA, can operate interactively and reactively across multiple samples. Using this approach, DPA can produce new plain text messages that can be passed as inputs repeatedly. In order to counter these types of attacks, it is necessary to hide information by making sure that the execution paths do not depend heavily on the inputs. This may require dropping optimizations that depend on specific bit values in keys. In the past, Chinese remainder theorem, CRT, optimizations allowed remote timed attacks on secure socket layer, SSL, servers. In general, cryptosystems should be designed to resist information leaks. A different type of side-channel attack happens when keys are safely stored in memory and attackers do not have access to a machine. In that case, if the attacker can access the physical machine and reboot it into an OS they control, it becomes possible for the attacker to look at the memory contents. While memory loses its state without content, it does so much more slowly at very cold temperatures. Therefore, an attacker could cool down the memory, shut down the machine, move the memory to a different machine, and boot it into a different OS. All that is left to do then is to scan the memory image for keys, which is difficult but feasible, assuming the keys have a format that is easy to detect. A couple of techniques can be used to counter these types of attacks. One solution is to encrypt all the memory, which requires additional CPU power. Another solution, which is used on Xbox, requires a Trusted Platform Module (TPM) to store hardware keys, making installing them very difficult. Some TPM self-destruct when tampered with or keep keys in memory for a limited time, e.g., the keys are removed from memory when going to sleep mode. There are new mechanisms to permit new types of interactions. A style of interaction that has been getting a lot of attention is the following. Alice has proprietary data. Bob has proprietary code or computational resources. The goal is for Bob to run his code on Alice's data without learning her input or the output. There are problems introduced earlier that still require usable solutions, secure multi-party computation. For example, Alice and Bob both have data and want to know the output of a function over their private data without having to reveal their data to each other, e.g., which of us has more money, without having to reveal exactly how much either has. 20 Communication overhead and vulnerability to attacks from colluding parties are the main challenges. While there are techniques to solve these problems, they usually come with higher computational costs. Fully homomorphic encryption. Homomorphic encryption, HE, can perform computations on encrypted data without first decrypting it with a secret key. It then encrypts the computation results, and only the owner or the private key can decrypt them. 21 partial HE systems have been around since the 1970s, and a fully HE scheme that makes it possible to apply mathematical operations to encrypted data was first developed by Craig Gentry in 2009. However, fully homomorphic encryption in its current form is impractically slow. Traditional software solutions security. To protect systems, software solutions architects and software developers must consider security as a property of the systems they build. The way software safeguards system resources, including data, to provide access to only authorized users is through software security. Security should be part of the software design process to take a proactive approach to cyber threats and risks. This includes prioritizing security in software requirements, programming, testing, implementation, and maintenance. Practices that should be part of software security include threat modeling and vulnerability management. Generally, to implement security in the software development process, software architects and developers should follow these steps. Make software security a priority and focus of the development process. Identify security risks that should be addressed with software. Identify vulnerabilities. Use the appropriate standards, best practices, and frameworks to guide the development process. Review and analyze the code extensively with an emphasis on cybersecurity. Implement penetration testing, which includes the following steps. Planning process to gather information about the system and define testing goals. Scan the system with tools to learn how the system responds to threats. Execute attacks and make every effort to gain access to the system, revealing its weaknesses. If access is gained, make every effort to maintain that access without detection. Analyze test results and make system changes before testing again. Repeat this process over and over to identify system weaknesses. Software security. Software solutions architects and developers must consider security as a property of the systems they build. Many attacks begin by exploiting a vulnerability. In this case, a vulnerability is a software defect that yields an undesired behavior, i.e., the code does not behave correctly. Software defects arise due to flaws in the design or bugs in the implementation. Unfortunately, software can't be completely bug-free, and fixing every known bug may be too expensive. In general, the focus is to fix what is likely to affect normal users and not focus on bugs that normal users never see or avoid. Because attackers are not normal users, they look for bugs and flaws and try to exploit them. Therefore, to achieve software security, it is necessary to eliminate bugs and design flaws and/or make them harder to exploit. Doing so requires thinking like attackers and developing a foundation for deeply understanding the systems built and used. Most interesting software takes inputs from various sources, and any of these inputs may be malicious, such as the following: direct user interaction, e.g., user interfaces with software via command line interface or opens a document. Third-party libraries that are linked to the software. Future code updates. Securing software in this context should result in correct operation despite malicious inputs. In order to study how to secure software, we will focus on what should be done to secure software written using the C programming language and investigate program control, flow, hijacking via buffer overflows, code injection, and other memory safety vulnerabilities. This is motivated by the fact that the C language is consistently used widely, and many mission-critical systems are written in C, e.g., most operating systems kernels such as Linux, high-performance servers such as Microsoft SQL Server, many embedded systems such as Mars rover. Furthermore, the same techniques apply more broadly: buffer overflow attacks and defenses. Many buffer overflow attacks were perpetrated over the years against software programs written in C. Buffer overflows are prevalent and constitute a significant percentage of all vulnerabilities. 22 in 1988, for example, Robert Morris sent a special string via buffer overflow attack to the fingered daemon on a computer running the VAX operating system and caused it to execute code that created a worm copy that propagated over the network and affected Sun machines running the BSD operating systems. This resulted in $100 worth of damages, as well as probation and community services. Robert Morris subsequently became a professor at MIT. In 2001, the code Redworm leveraged a buffer overflow error in the MSIIS server. As a result, 300,000 machines were infected within 14 hours. In 2003, the SQL Slammer worm leveraged a similar buffer overflow error in the MS SQL server. As a result, 75,000 machines were infected within 10 minutes. In 2008-2009, the Configure worm exploited a buffer overflow in Windows RPC, which infected more than 10 million machines. In 2009-2010, Stuxnet exploited several buffer overflows in the Windows Print Spooler service, LNK shortcut display, task scheduler, and the same RPC buffer overflow as Configure, which led to legitimate cyber warfare. Between 2010 and 2012, Flame exploited the same print spooler and LNK buffer overflows as Stuxnet, which resulted in a cyber espionage virus. On January 8, 2014, a 23-year-old discovered an X11 server security stack buffer overflow vulnerability, i.e., SCANF used when loading early 1990s BDF bitmap fonts from 1991. The Ghost Glibc vulnerability was introduced in 2000, but was only discovered many years later. One last example is the syslog logging infrastructure daemon bug in macOS and iOS, which relied on the fact that running programs would issue log messages and syslog would handle storing and disseminating them. The problem was that syslog used a buffer to propagate these messages, which was not large enough and would sometimes write beyond the end of the buffer. Based on this, understanding how C programs' buffer overflow attacks work and how to defend against them is critical and requires knowledge. Refer to Chapter 4 Linguistic Realization of Algorithms. Low-level programming languages and Chapter 5 Hardware Realizations of Algorithms. Computer systems design of the C software compiler, the operating system on which the program is run, and the computer system architecture on which the operating system runs, in other words, a whole system's view. As a refresher, the stack layout on a 32-bit Intel IA32 computer when calling a sample C function, figure 14. 18 is shown. Note that in this case, there are two 4B values between the arguments and the local variables. Illustration showing stack layout on a 32-bit Intel IA32 computer when calling a sample C function. Local variables pushed in the same order as they appear in code. Arguments pushed in reverse order of code. Figure 14. 18 local function variables are pushed on the stack in the order they appear in the code, while function arguments are pushed in the reverse order or their appearance in the code. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Credit, reproduced with permission from Dave Levin. The function func can access variable lock2 using the stack frame pointer %eb, figure 14. 19. Note that the same would apply on a 64-bit computer by using a 64-bit memory layout and changing the names of the registers accordingly, e.g., %RBP vs %eb. Illustration showing stack frame pointer. Location of lock2 variable in stack frame is always 8 bytes before the address contained in %eb, figure 14. 19. The location of the lock2 variable in the stack frame is always 8b before the address contained in %eb. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Credit. Reproduced with permission from Dave Levin. Figure 14. 20 illustrates how to properly return from a call to the function func. Illustration showing how to return from a call to the function func. Set %eb at return, push next %ip before call. Figure 14. 20. This figure shows how to properly return from a call to the function func. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit, reproduced with permission from Dave Levin. In summary, the steps to follow in order to call and return from a function are as follows. Calling function, push arguments onto the stack in reverse. Push return address onto the stack, i.e., the address of the instruction that needs to be run once control returns to the calling program, %ip plus something. Jump to the function's address. Called function, push old frame pointer onto the stack, %eb, set frame pointer %eb to where the end of the stack is right at this time, %esp, push local variables onto the stack. Access them as offsets from %eb, returning function, reset previous stack frame, %eb equals %eb, copy it off first, jump back to return address. %ip equals 4, %eb, use the copy. Let us investigate a buffer overflow example based on understanding the stack memory layout when calling and returning from functions. Buffers are commonly used in C to store sets of values of a given data type. For example, strings are buffers of characters in C. A buffer overflow occurs when more values are put into the buffer than it can hold. Let us consider this buffer overflow example, figure 14. 21, and right before the strcpy, buffer, arg1, statement is executed in the function func. Illustration of buffer overflow that occurs when more values put into buffer than it can hold, right before the strcpy, buffer, arg1, statement is executed in the function func. Figure 14. 21. The strcpy statement executed in the function func overflows the size of the buffer specified. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Once the strcpy, buffer, arg1, statement is executed in the function func, figure 14. 22. It overwrites the stack memory location where %eb was stored, which causes a segmentation violation when the function returns. Illustration of segmentation violation when the function returns. The strcpy, buffer, arg1, statement is executed in the function func and overwrites the stack memory location where %eb was stored. Figure 14. 22. The strcpy statement executed in the function func sets %eb to the wrong address upon return due to the buffer overflow. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit, reproduced with permission from Dave Levin. Using the GNU debugger, IEs. GDB is useful to debug programs that run into buffer overflows. It enables users to show information about the current frame and registers, examine bytes of memory starting at a given address, set a breakpoint at a given function address, and step through a call to it. A safe version of the function func will never cause a buffer overflow. It will simply limit the number of characters read from the command line and could be easily adapted to replace the function func. Void Nuverflow. Char bufflimit 100, fgets bufflimit. Sizeoff bufflimit. Note that strcpy lets you write as many characters as you want until it reads an end-of-string character, i.e. null character \0 in a C string. Therefore, the problem could get worse than just overwriting %eb. Figure 14. 23 illustrates a different type of buffer overflow that would occur if the function func were to execute the code provided. In that case, the input writes from low to high addresses. Illustration of buffer overflow that occurs if function func executes code provided. Input writes from low to high addresses. Figure 14. 23. The execution of the code shown is such that the input writes from low to high addresses. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Code injection attacks and defenses. The example of buffer overflow shown earlier uses a string provided by the program itself, but, in general, inputs could come from different sources, e.g. text input, network packets, environment variables, file inputs. Therefore, the existence of a buffer overflow bug in a program can lead to a code injection attack, figure 14, 24. Illustration of buffer overflow bug leading to code injection attack, which can be staged by loading code into memory and get %ip to point to it, figure 14. 24. A code injection attack can be staged by loading code into memory and point %ip to it. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. reproduced with permission from Dave Levin. Pulling off this type of attack requires overcoming a few challenges, which we will discuss in detail. In general, making it really hard to overcome the various challenges is key to defending programs against code injection attacks. The challenges are as follows. Loading the code into memory. The code that is loaded into memory must be machine code that is ready to run. It should not contain any all 0 bytes. Alternatively, some library functions, e.g. sprintf, gets, scanf, will stop copying. The loader cannot be used because the code is injected. Finally, the code injected cannot use the stack because it is designed to smash it. The best type of code for this is full-purpose shellcode that can be launched as a shell, figure 14. 25. There are many examples of such code, and there is a lot of competition to write the smallest amount of code. Also, a way to ensure that the injected code will work most effectively is to attempt privilege escalation and go from guest or non-user to root. Illustration of full-purpose shellcode for code injection that can be launched as a shell. Figure 14. 25. The best type of code for code injection is full-purpose shellcode that can be launched as a shell. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Concerning privileged escalation, the idea is to exploit knowledge of permissions on the targeted operating system. In the case of Linux, files have read, write, execute permissions owner, group, and others. Permissions are defined for userid and groupid, and the root userid is p. The command passwd may be used as part of an attack by making it possible for any user to execute that command rather than just its owner, i.e. root. The idea is to have a root-owned process run setuid 0 or setuid 0 in order to get root permissions. While root owns passwd, users can run it, and getuid will return the userid of the person who ran it. Executing setuid 0 next will set the effective userid to root, which is allowed because root is the process owner. Getting injected code to run. Because it is only possible to write forward into a memory buffer, the running code must already be used to jump to the injected code. The typical approach is to hijack the saved %ip and change it to point to the address of the injected code, figure 14. 26. Illustration of hijacking saved %ip and changing it to point to the address of injected code. Figure 14. 26. Code injection is performed by hijacking the saved %ip and changing it to point to the address of the injected code. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. However, getting to know the address of the saved %ip is a challenge. Furthermore, if the %ip is wrong and points to data, the CPU will panic when it attempts to execute an invalid instruction. Finding the return address. Because the code cannot be accessed, there is no way to know where the buffer starts based on the saved %ip. One possibility is to try a lot of different values, and the worst-case situation for a 64-bit memory space involves computing 264 possible answers. If address space layout randomization, ASLR, is disabled, which you cannot count on today, the stack always starts from the same fixed address and then grows. Still, it does not usually grow very deeply unless the code is heavily recursive. Another approach consists of using NOP sleds. Because NOP is a single-byte instruction, it makes it possible to move to the next instruction, thereby improving chances to hit the address of %ip, figure 14. 27. Illustration of using NOP single-byte instructions to improve the chances to hit the address of %ip, figure 14. 27. Introducing single-byte NOP instructions improves the chances to hit the address of %ip. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Finally, putting it all together, the recipe for code injection is to achieve that shown in figure 14. 28. Illustration of the recipe for code injection, which is to guess the stack return address and use NOP sleds to improve chances to hit the address of %ip, figure 14. 28. The recipe for code injection is to guess the stack return address and use NOP sleds to improve the chances to hit the address of %ip. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. A typical way to protect a program against code injection is to prevent data execution by marking memory pages as non-executable, or make it impossible to put code into the memory by detecting overflows with canaries. Using a canary amounts to placing a known string of characters in memory at the end of the buffer, and aborts the program execution if the expected value at that location is changed. Figure 14, 29. Illustration of using a canary or placing a known string of characters at the end of the buffer to detect if the content at the end of the buffer has been changed. Program aborts if the expected value is changed. Figure 14. 29. Placing a canary at the end of the buffer makes it possible to detect whether the content at the end of the buffer has been changed. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0 license, credit, reproduced with permission from Dave Levin. There are a few possibilities for canary values as indicated. Terminator canaries, e.g., CR, LF null -1, leverage that scanf and other similar functions do not allow these values. Random canaries write a new random value when each process starts and saves the real value somewhere in memory. It is necessary to write protect the stored value in that case. Random XOR canaries work the same way as random canaries, but store canary XOR some control info instead. Computational problems. Problems need to be first converted into the right form. The form is called a quadratic arithmetic program, QAP, and transforming the code of a function into a QAP is highly non-trivial. It requires turning the computation into an algebraic circuit and transforming it into a rank 1 constraint system, R1CS, that can then be converted into a QAP. In addition to the process for converting the code of a function into a QAP, another process may run alongside in such a way that if you have an input to the code, you can create a corresponding solution, sometimes called witness, to the QAP. Once this is done, another fairly intricate process must be followed to create the actual zero-knowledge proof for the witness and a separate process for verifying proof that someone else passes along to you. The full machinery between zk-snark is illustrated in Figure 14. 16. Illustration of full machinery between zk-snark includes computation, algebraic circuit, R1CS, QAP, linear PCP, linear interactive proof, zk-snark. Figure 14. 16. zk-snark full machinery includes computation, algebraic circuit, R1CS, QAP, linear PCP, and linear interactive proof. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit, reproduced with permission from Dave Levin. zk-snarks are not transparent and require a so-called trusted setup to secure the randomness of the parameters determining the selection of queries in the verification procedure. The random parameters are, for example, generated using a hash function. However, the knowledge of the original values fed into the hash function, toxic waste, must be kept secret. Otherwise, retrieving the random parameters and manipulating the selection of verification queries would be possible. A trusted setup is a multi-party computation, MPC, ceremony which recursively generates random parameters. If at least one party is honest and forgets its input values, the randomness of the trusted setup is safe. Universal trusted setups can be generated once and can be reused for other applications as well. Non-universal ones are tied to the specific circuit. The difficult part is to generate a zk-snark with reasonable resources for real-world applications. Zero-knowledge scalable transparent argument of knowledge, zk-snark, is a type of ZKP where one party can prove to another that a given statement is true without revealing any other information other than the fact that the statement is true. Attributes of the zk-snark concept are as follows. Zero-knowledge refers to privacy preservation. Scalability indicates that verification time is substantially less than the time taken for naive computations. Transparency reflects the lack of a trusted setup requirement. Argument and knowledge related to the security and robustness of the cryptographic scheme. Zero-knowledge Snarks work by leveraging linear cryptography, specifically collision-resistant hash functions, to validate the truth of a statement without sharing the details behind it. Unlike zk-snark, zero-knowledge succinct non-interactive argument of knowledge, which rely on an initial trusted setup and are theoretically vulnerable to quantum computer attacks, zk-snark eliminate these issues. That said, it is important to note that this linear approach results in a significant disadvantage. Specifically, zk-snark generate proofs that are typically 10 to 100 times larger than those created by zk-snark, thus making them more expensive and potentially less practical for certain applications. The trade-offs between different properties of different non-interactive and transparent proof systems amount to a difference in verification time between 2 ms to 250 ms, prover time 1s to 100s, and proof size between 200B to 250 KB. The cryptographic primitives used by ZKPs include the following cryptographic primitives: collision-resistant hash function, quantum secure, Stark, fractal, elliptic curve cryptography, bulletproofs halo, knowledge of exponent pairing groups, Groth 16, sonic, Marlin Plunk, groups of unknown order, supersonic, lattice-based cryptography, quantum secure. Under development, there are myriads of recent applications of ZKPs to blockchain technology for privacy and scalability improvements. A related topic is verifiable delay functions, VDFs, which emerged in June 2018. A verifiable delay function, VDF, is a function f, x right arrow y that takes a prescribed minimum time to compute, even on a parallel computer. However, once computed, anyone can quickly verify the output. They can prevent fraud or front-running on exchanges, online auctions, games, or prediction markets. Another related topic is multi-party computations, MPCs, which are methods for parties to jointly compute a function over their inputs while keeping those inputs private. MPCs are different from traditional cryptographic tasks that use cryptography to ensure the security and integrity of communication or storage, and assume that the adversary is outside the system of participants. In MPC, cryptography protects participants' privacy from each other. An example of an application is that of a trusted setup ceremony, which is a secure MPC. An important related topic is fully homomorphic encryption, FHE, the holy grail of cryptography. FHE allows arbitrary mathematical operations on encrypted data, i.e., for every f. Y equals fx, encrypted y equals fx, open problems in cryptography. The ongoing attacks and the need to defend crypto schemes require staying on top of best practices. Ideally, developers should write code that can be changed easily. Also, remember not to develop your own cryptographic mechanisms. Go through peer review and apply Kirchhoff's principle. Do not even implement the underlying crypto, and do not misuse existing crypto. Information about a particular implementation could leak, e.g., power consumption, electromagnetic radiation, timing, errors. Attacks based on this are referred to as side-channel attacks. As an example, simple power analysis (SPA) may be used to interpret power traces during a cryptographic operation. Simple power analysis, Figure 14. 17 can reveal the sequence of instructions that have been executed. Graph shows simple power analysis revealing specific instructions, jump taken, no jump taken, Figure 14. 17 simple power analysis can reveal specific instructions such as those shown here. Attribution, copyright Rice University, OpenStax, under CC by 40 license, credit. Reproduced with permission from Dave Levin. Assuming the program execution path depends on the inputs, i.e., key data, SPA can be used to reveal the keys. Different from SPA, which visually inspects a single-run differential power analysis, DPA, can operate interactively and reactively across multiple samples. Using this approach, DPA can produce new plain text messages that can be passed as inputs repeatedly. In order to counter these types of attacks, it is necessary to hide information by making sure that the execution paths do not depend heavily on the inputs. This may require dropping optimizations that depend on specific bit values in keys. In the past, Chinese remainder theorem, CRT, optimizations allowed remote timed attacks on secure socket layer, SSL, servers. In general, cryptosystems should be designed to resist information leaks. A different type of side-channel attack happens when keys are safely stored in memory and attackers do not have access to a machine. In that case, if the attacker can access the physical machine and reboot it into an OS they control, it becomes possible for the attacker to look at the memory contents. While memory loses its state without content, it does so much more slowly at very cold temperatures. Therefore, an attacker could cool down the memory, shut down the machine, move the memory to a different machine, and boot it into a different OS. All that is left to do then is to scan the memory image for keys, which is difficult but feasible, assuming the keys have a format that is easy to detect. A couple of techniques can be used to counter these types of attacks. One solution is to encrypt all the memory, which requires additional CPU power. Another solution, which is used on Xbox, requires a Trusted Platform Module, TPM, to store hardware keys, making installing them very difficult. Some TPM self-destruct when tampered with or keep keys in memory for a limited time, e.g., the keys are removed from memory when going to sleep mode. there are new mechanisms to permit new types of interactions. A style of interaction that has been getting a lot of attention is the following. Alice has proprietary data. Bob has proprietary code or computational resources. The goal is for Bob to run his code on Alice's data without learning her input or the output. There are problems introduced earlier that still require usable solutions, secure multi-party computation. For example, Alice and Bob both have data and want to know the output of a function over their private data without having to reveal their data to each other, e.g., which of us has more money, without having to reveal exactly how much either has. 20 Communication overhead and vulnerability to attacks from colluding parties are the main challenges. While there are techniques to solve these problems, they usually come with higher computational costs. Fully homomorphic encryption. Homomorphic encryption, HE, can perform computations on encrypted data without first decrypting it with a secret key. It then encrypts the computation results, and only the owner or the private key can decrypt them. 21 partial HE systems have been around since the 1970s, and a fully HE scheme that makes it possible to apply mathematical operations to encrypted data was first developed by Craig Gentry in 2009. However, fully homomorphic encryption in its current form is impractically slow. Traditional software solutions security. To protect systems, software solutions architects and software developers must consider security as a property of the systems they build. The way software safeguards system resources, including data, to provide access to only authorized users is through software security. Security should be part of the software design process to take a proactive approach to cyber threats and risks. This includes prioritizing security in software requirements, programming, testing, implementation, and maintenance. Practices that should be part of software security include threat modeling and vulnerability management. Generally, to implement security in the software development process, software architects and developers should follow these steps. Make software security a priority and focus of the development process. Identify security risks that should be addressed with software. Identify vulnerabilities. Use the appropriate standards, best practices, and frameworks to guide the development process. Review and analyze the code extensively with an emphasis on cybersecurity. Implement penetration testing, which includes the following steps. Planning process to gather information about the system and define testing goals. Scan the system with tools to learn how the system responds to threats. Execute attacks and make every effort to gain access to the system, revealing its weaknesses. If access is gained, make every effort to maintain that access without detection. Analyze test results and make system changes before testing again. Repeat this process over and over to identify system weaknesses. Software security. Software solutions architects and developers must consider security as a property of the systems they build. Many attacks begin by exploiting a vulnerability. In this case, a vulnerability is a software defect that yields an undesired behavior, i.e., the code does not behave correctly. Software defects arise due to flaws in the design or bugs in the implementation. Unfortunately, software can't be completely bug-free, and fixing every known bug may be too expensive. In general, the focus is to fix what is likely to affect normal users and not focus on bugs that normal users never see or avoid. Because attackers are not normal users, they look for bugs and flaws and try to exploit them. Therefore, to achieve software security, it is necessary to eliminate bugs and design flaws and/or make them harder to exploit. Doing so requires thinking like attackers and developing a foundation for deeply understanding the systems built and used. Most interesting software takes inputs from various sources, and any of these inputs may be malicious, such as the following: direct user interaction, e.g., user interfaces with software via command line interface or opens a document. Third-party libraries that are linked to the software. Future code updates. Securing software in this context should result in correct operation despite malicious inputs. In order to study how to secure software, we will focus on what should be done to secure software written using the C programming language and investigate program control, flow, hijacking via buffer overflows, code injection, and other memory safety vulnerabilities. This is motivated by the fact that the C language is consistently used widely, and many mission-critical systems are written in C, e.g., most operating systems kernels such as Linux, high-performance servers such as Microsoft SQL Server, many embedded systems such as Mars rover. Furthermore, the same techniques apply more broadly: buffer overflow attacks and defenses. Many buffer overflow attacks were perpetrated over the years against software programs written in C. Buffer overflows are prevalent and constitute a significant percentage of all vulnerabilities. 22 in 1988, for example, Robert Morris sent a special string via buffer overflow attack to the fingered daemon on a computer running the VAX operating system and caused it to execute code that created a worm copy that propagated over the network and affected Sun machines running the BSD operating systems. This resulted in $100 worth of damages, as well as probation and community services. Robert Morris subsequently became a professor at MIT. In 2001, the code Redworm leveraged a buffer overflow error in the MSIIS server. As a result, 300,000 machines were infected within 14 hours. In 2003, the SQL Slammer worm leveraged a similar buffer overflow error in the MS SQL server. As a result, 75,000 machines were infected within 10 minutes. In 2008-2009, the Configure worm exploited a buffer overflow in Windows RPC, which infected more than 10 million machines. In 2009-2010, Stuxnet exploited several buffer overflows in the Windows Print Spooler service, LNK shortcut display, task scheduler, and the same RPC buffer overflow as Configure, which led to legitimate cyber warfare. Between 2010 and 2012, Flame exploited the same print spooler and LNK buffer overflows as Stuxnet, which resulted in a cyberespionage virus. On January 8, 2014, a 23-year-old discovered an X11 server security stack buffer overflow vulnerability, i.e., scanf used when loading early 1990s BDF bitmap fonts from 1991. The Ghost glib vulnerability was introduced in 2000, but was only discovered many years later. One last example is the syslog logging infrastructure daemon bug in macOS and iOS, which relied on the fact that running programs would issue log messages and syslog would handle storing and disseminating them. The problem was that syslog used a buffer to propagate these messages, which was not large enough and would sometimes write beyond the end of the buffer. Based on this, understanding how C programs' buffer overflow attacks work and how to defend against them is critical and requires knowledge. Refer to Chapter 4 Linguistic Realization of Algorithms. Low-level programming languages and Chapter 5 Hardware Realizations of Algorithms. Computer systems design of the C software compiler, the operating system on which the program is run, and the computer system architecture on which the operating system runs, in other words, a whole systems view. As a refresher, the stack layout on a 32-bit Intel IA32 computer when calling a sample C function, figure 14.18, is shown. Note that in this case, there are two 4B values between the arguments and the local variables. Illustration showing stack layout on a 32-bit Intel IA32 computer when calling a sample C function. Local variables pushed in the same order as they appear in code. Arguments pushed in reverse order of code. Figure 14.18 local function variables are pushed on the stack in the order they appear in the code, while function arguments are pushed in the reverse order or their appearance in the code. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license, credit, reproduced with permission from Dave Levin. The function func can access variable lock2 using the stack frame pointer %eb, figure 14.19. Note that the same would apply on a 64-bit computer by using a 64-bit memory layout and changing the names of the registers accordingly, e.g., %RBPVs %eb. Illustration showing stack frame pointer. Location of lock2 variable in stack frame is always 8 bytes before the address contained in %eb, figure 14.19. The location of the lock2 variable in the stack frame is always 8b before the address contained in %eb. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license, credit. Reproduced with permission from Dave Levin. Figure 14.20 illustrates how to properly return from a call to the function func. Illustration showing how to return from a call to the function func. Set %ebbit return, push next %ip before call. Figure 14.20. This figure shows how to properly return from a call to the function func. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license, credit, reproduced with permission from Dave Levin. In summary, the steps to follow in order to call and return from a function are as follows. Calling function, push arguments onto the stack in reverse. Push return address onto the stack, i.e., the address of the instruction that needs to be run once control returns to the calling program, %ip plus something. Jump to the function's address. Called function. Push old frame pointer onto the stack. %eb. Set frame pointer %eb to where the end of the stack is right at this time. %esp. Push local variables onto the stack. Access them as offsets from %eb. Returning function. Reset previous stack frame. %eb equals %eb. Copy it off first. Jump back to return address. %ip equals 4. %eb. Use the copy. Let us investigate a buffer overflow example based on understanding the stack memory layout when calling and returning from functions. Buffers are commonly used in C to store sets of values of a given data type. For example, strings are buffers of characters in C. A buffer overflow occurs when more values are put into the buffer than it can hold. Let us consider this buffer overflow example, figure 14, 21, and right before the strcpy buffer arg1 statement is executed in the function func. Illustration of buffer overflow that occurs when more values put into buffer than it can hold. Right before the strcpy buffer arg1 statement is executed in the function func. Figure 14. 21. The strcpy statement executed in the function func overflows the size of the buffer specified. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Once the strcpy buffer arg1 statement is executed in the function func, figure 14. 22, it overwrites the stack memory location where %eb was stored, which causes a segmentation violation when the function returns. Illustration of segmentation violation when the function returns. The strcpy buffer arg1 statement is executed in the function func and overwrites the stack memory location where %eb was stored. Figure 14. 22. The strcpy statement executed in the function func sets %eb to the wrong address upon return due to the buffer overflow. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Using the GNU debugger, i.e. GDB is useful to debug programs that run into buffer overflows. It enables users to show information about the current frame and registers, examine bytes of memory starting at a given address, set a breakpoint at a given function address, and step through a call to it. A safe version of the function func will never cause a buffer overflow. It will simply limit the number of characters read from the command line and could be easily adapted to replace the function func. Void Nuverflow. Char bufflimit 100, fgets bufflimit, sizeoff bufflimit. Note that strcpy lets you write as many characters as you want until it reads an end-of-string character, i.e. null character \0 in a C string. Therefore, the problem could get worse than just overwriting %eb. Figure 14. 23 illustrates a different type of buffer overflow that would occur if the function func were to execute the code provided. In that case, the input writes from low to high addresses. Illustration of buffer overflow that occurs if function func executes code provided. Input writes from low to high addresses. Figure 14. 23. The execution of the code shown is such that the input writes from low to high addresses. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Code injection attacks and defenses. The example of buffer overflow shown earlier uses a string provided by the program itself, but, in general, inputs could come from different sources, e.g. text input, network packets, environment variables, file inputs. Therefore, the existence of a buffer overflow bug in a program can lead to a code injection attack, figure 14, 24. Illustration of buffer overflow bug leading to code injection attack, which can be staged by loading code into memory and get %ip to point to it, figure 14. 24. A code injection attack can be staged by loading code into memory and point %ip to it. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Pulling off this type of attack requires overcoming a few challenges, which we will discuss in detail. In general, making it really hard to overcome the various challenges is key to defending programs against code injection attacks. The challenges are as follows. Loading the code into memory. The code that is loaded into memory must be machine code that is ready to run. It should not contain any all 0 bytes. Alternatively, some library functions, e.g. sprintf, gets, scanf, will stop copying. The loader cannot be used because the code is injected. Finally, the code injected cannot use the stack because it is designed to smash it. The best type of code for this is full-purpose shellcode that can be launched as a shell, figure 14. 25. There are many examples of such code, and there is a lot of competition to write the smallest amount of code. Also, a way to ensure that the injected code will work most effectively is to attempt privilege escalation and go from guest or non-user to root. Illustration of full-purpose shellcode for code injection that can be launched as a shell. Figure 14. 25. The best type of code for code injection is full-purpose shellcode that can be launched as a shell. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Concerning privileged escalation, the idea is to exploit knowledge of permissions on the targeted operating system. In the case of Linux, files have read, write, execute permissions owner, group, and others. Permissions are defined for userid and groupid, and the root userid is p. The command passwd may be used as part of an attack by making it possible for any user to execute that command rather than just its owner, i.e. root. The idea is to have a rootone process run setuid 0 or setuid 0 in order to get root permissions. While root owns passwd, users can run it, and getuid will return the userid of the person who ran it. Executing setuid 0 next will set the effective userid to root, which is allowed because root is the process owner. Getting injected code to run. Because it is only possible to write forward into a memory buffer, the running code must already be used to jump to the injected code. The typical approach is to hijack the saved %ip and change it to point to the address of the injected code, figure 14. 26. Illustration of hijacking saved %ip and changing it to point to the address of injected code. Figure 14. 26. Code injection is performed by hijacking the saved %ip and changing it to point to the address of the injected code. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. However, getting to know the address of the saved %ip is a challenge. Furthermore, if the %ip is wrong and points to data, the CPU will panic when it attempts to execute an invalid instruction. Finding the return address. Because the code cannot be accessed, there is no way to know where the buffer starts based on the saved %ip. One possibility is to try a lot of different values, and the worst-case situation for a 64-bit memory space involves computing 264 possible answers. If address space layout randomization, ASLR, is disabled, which you cannot count on today, the stack always starts from the same fixed address and then grows. Still, it does not usually grow very deeply unless the code is heavily recursive. Another approach consists of using NOP sleds. Because NOP is a single-byte instruction, it makes it possible to move to the next instruction, thereby improving chances to hit the address of %ip, figure 14. 27. Illustration of using NOP single-byte instructions to improve the chances to hit the address of %ip, figure 14. 27. Introducing single-byte NOP instructions improves the chances to hit the address of %ip. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. Finally, putting it all together, the recipe for code injection is to achieve that shown in figure 14. 28. Illustration of the recipe for code injection, which is to guess the stack return address and use NOP sleds to improve chances to hit the address of %ip, figure 14. 28. The recipe for code injection is to guess the stack return address and use NOP sleds to improve the chances to hit the address of %ip. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. A typical way to protect a program against code injection is to prevent data execution by marking memory pages as non-executable or make it impossible to put code into the memory by detecting overflows with canaries. Using a canary amounts to placing a known string of characters in memory at the end of the buffer and aborts the program execution if the expected value at that location is changed, figure 14. 29. Illustration of using a canary or placing a known string of characters at the end of the buffer to detect if the content at the end of the buffer has been changed. Program aborts if the expected value is changed, figure 14. 29. Placing a canary at the end of the buffer makes it possible to detect whether the content at the end of the buffer has been changed. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit. Reproduced with permission from Dave Levin. There are few possibilities for canary values as indicated. Terminator canaries, e.g., CR, LF null -1, leverage that scanf and other similar functions do not allow these values. Random canaries write a new random value when each process starts and saves the real value somewhere in memory. It is necessary to write protect the stored value in that case. Random XOR canaries work the same way as random canaries, but store canary XOR some control info instead. Integer overflow attacks and defenses programmers have a tendency to think about integers as mathematical integers. It is therefore easy for them to write C code that causes integer overflows, e.g., assigning larger types to smaller types, arithmetic overflow. For example, the following multiplication using integers represented by the two complement notations causes an arithmetic overflow that yields a negative result. 15 million asterisk 500 equals -1,089,934,592. Knowing this, attackers may simply control the value of an integer and cause software to behave unexpectedly. Defending against integer overflow requires using appropriate types, e.g., using sizeit in the C language. Format string vulnerability and defenses, a format function, is a special kind of ANSI C function used as a conversion function to represent primitive C data types as human-readable strings. Format functions are used in most C programs to output information, print error messages, and process strings. A format string vulnerability occurs when an attacker can provide the format string to an ANSI C format function in part or as a whole. If the attacker can do so, the behavior of the format function is changed, and the attacker may get control over the target application. For example, by calling the following function using a command line parameter. Int func char user, print user. An attacker can get control over the entire ASCII string of the print function, i.e., the part that contains text and format parameters. To avoid this problem, the function should be written as follows: int func char user, print %s, user. This kind of vulnerability is more dangerous than the common buffer overflow vulnerability. 23 Heap control data vulnerability. The heap is managed by the malloc function, which requests pages of memory from the operating system, manages free chunks, and allocates memory for programs. Attackers can use the malloc function to overwrite heap metadata and abuse it to exploit buffer overflows by injecting control data in malloc space. 24 Code reuse attacks and return-oriented programming, ROP. We have discussed earlier ways to prevent an attacker from executing any injected code using canaries. While attackers may attempt to bypass stack canaries last time, they may also simply focus on bypassing data execution prevention, DEP, measures by executing existing code such as the program code itself, dynamic libraries, or libc. In particular, libc contains valuable functions such as system, runs a shell command, or protect, changes the memory protection on a region of code. Rather than returning to shellcode, an attacker may decide to return to a standard library function like system and cause a system to crash to exit. Another alternative is to return to protect, inject code, and make it executable. An attacker may also chain two functions together. In fact, attackers may not need to limit themselves to functions and clean up code. An alternative is to encode arbitrary computation, including conditionals and loops, by returning to sequences of code ending in ret. This last approach is referred to as return-oriented programming, ROP25, and relies on the following steps. Disassemble code, i.e., library or program. Identify useful code sequences, e.g., code sequences usually ending in ret. Assemble useful sequences into reusable gadgets. Assemble gadgets into desired shellcode. Time of check, time of use problem, figure 14. 30 illustrates the time of check to time of use, TOCTOU problem. Illustration of time of check / time of use, TOCTOU problem. Check whether the real user who executed said UID program is normally allowed to read the file, so access checks real UID instead of the effective userid UID. Figure 14. 30 access is intended to check whether the real user who executed the said UID program would normally be allowed to read the file, so access checks the real UID instead of the effective userid UID. Attribution, copyright Rice University, OpenStax under CC by 40 license. Credit, reproduced with permission from Dave Levin. The code should be modified as in figure 14. 31 to avoid the TOCTOU problem. Illustration of modifying code to avoid TOCTOU problem by switching the UID that executed the said UID command to the UID. Figure 14. 31 The code is modified to switch the user UID that executed the setUID command to the effective user, UID, to ensure that proper permissions are used when accessing the document. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit, reproduced with permission from Dave Levin, playing cat and mouse to secure software. The following illustrates how securing software is like playing cat and mouse. Defense, make stack or heap non-executable to prevent code injection. Attack response, return to libc. Defense, hide the address of the desired lib code or return the address using ASLR. Attack response. Perform a brute force search for 32 and 64-bit systems, or information leak, i.e., format string vulnerability. Defense, avoid using lib code entirely and use code in the program text instead. Attack response, construct needed functionality using return-oriented programming, ROP. Common cyber threat defenses. Common cyber threats were introduced earlier along with various examples of malware. Protection against malware involves the use of an intrusion detection system, IDS, as well as an intrusion prevention system, IPS. An IDS may be host or network-based, i.e., HIDS or NIDS. In this case, detection happens after the attack, i.e., the memory is already corrupted due to a buffer overflow attack. A preventive measure must stop the attack before it reaches the system, i.e., the shield does packet filtering. Some tools support both IDS and IPS, e.g., snort. Malware detection methods in general. Some types of malware may rely on some delay based on a trigger to run, e.g., time bomb, logic bomb, and they may include a backdoor to serve as ransom. Other types of malware piggyback on other pieces of code. For example, viruses run when users initiate a task, e.g., run a program, open an attachment, boot the machine. Worms run while another program is running and do not require user intervention. Therefore, a virus propagates by ensuring it is eventually executed, assuming user intervention. Once executed, the virus creates a new separate instance of itself and typically infects by altering stored code. A worm self-propagates by making sure it is immediately executed without user intervention. Once executed, the worm creates a new separate instance of itself, and it typically infects by altering the running code. There is a fine line between viruses and worms. Some malware uses both types. Detecting self-propagating malware, e.g., viruses or worms, is challenging. While antivirus software attempts to detect viruses, virus writers strive to evade human response and avoid detection for as long as possible. In the case of worms, the virus writer wants to spread the worm and hit many machines as quickly as possible to outpace the human response. Viruses have been around since the 1970s. They are opportunistic and eventually run as a result of a user action. Two orthogonal aspects define a virus: the way it propagates and what it does, i.e., the payload. A general infection strategy consists of altering existing code to incorporate the virus, share it, and expect users to unwittingly reshare it. Viruses infect other programs by taking over their entry point, so the viruses run when executing these programs. They infect documents, boot sectors, or run as memory-resident code. They increase their chances of running by attaching malicious code to a program a user is likely to run, e.g., email attachments. Once viruses run, they also look for an opportunity to infect other systems, e.g., proactive creation of emails. An obvious method for detecting viruses is to use signature-based detection, which consists of looking for bytes corresponding to injected virus code and protecting other systems by installing a recognizer for a known virus within them. This approach requires fast scanning algorithms and has resulted in creating a multi-billion-dollar antivirus market. Adding recognized signatures to that market enables marketing and leads to competition. To combat this detection method, virus writers give viruses harder signatures to match by creating polymorphic viruses. In this case, the virus generates a semantically different version of the code every time it propagates. While the higher-level semantics of the virus remain the same, the actual execution code differs, e.g., machine code instructions are different. Different algorithms are used to achieve the same purpose. The code makes use of different registers, or different constants are used. This can be accomplished by including a code rewriter with a virus, or adding some complex code that never runs to evade detection attempts. Instead of appending the program to the virus, virus writers surround the program with virus code, or overwrite uncommonly used parts of the program in order to confuse virus scanners. They also change the virus code so scanners cannot pin down a signature. Code changes can be mechanized so that the code looks different every time it is injected. To do so, they use public key encryption and the fact that it is non-deterministic to generate different virus code each time they encrypt the virus. At the same time, decryption always produces the same virus code, figure 14. 32. Virus writers also iteratively obfuscate the code, i.e., encrypt plus JMP plus, using different encryption algorithms until the obfuscated code is fully undetectable. Illustration of how decryption always produces the same virus code, but each time you encrypt it looks different. Figure 14. 32 virus writers generate a different virus code each time they encrypt the virus, while decryption always produces the same virus code. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Credit, reproduced with permission from Dave Levin. Scanning is insufficient to detect metamorphic viruses, and proper detection requires analysis of the code execution behavior. Two general approaches can be applied to facilitate detection, and both need to be conducted in a safe environment, e.g., GDB or a virtual machine. One of the approaches used by antivirus companies focuses on analyzing a new virus to locate its behavioral signature. Another approach focuses on suspicious code analysis to see if it matches the signature. In general, attackers have the upper hand because antivirus systems share signatures, which provides insight that attackers may use to react. Attackers change viruses slowly to make it hard to create a matching behavioral signature, or they can start acting differently to avoid detection. In order to detect polymorphic viruses, antivirus writers can record narrow signatures used by virus writers to catch the associated decryptors. Because these signatures are often very small, this approach can result in many false positives. To counter this approach, attackers may spread small decryptor code around and use a JMP instruction to get to the virus code. Another approach to detecting polymorphic viruses is executing or statically analyzing the suspicious code to see if it decrypts. The issue with this last approach is that it is hard to differentiate an encrypted virus from a valid common Packers program that does something similar, e.g., decompression. It also depends on how long the code can be executed without any side effects. Virus writers can combat these approaches by changing the decryptor. For example, oligomorphic viruses change from one of a fixed set of decryptors, and true polymorphic viruses can generate an endless number of decryptors, e.g., brute force key break. While this approach leads to inefficiencies, it makes it extremely difficult for antivirus software to detect viruses. Today, malware detection is a technological arms race between detection and avoidance. Initially, only a few very clever people were capable of creating viruses. Viruses are now commoditized, and anyone can launch one. The creation of viruses remains hard. Still, it is no longer an academic interest focus, but is rather driven by economic pursuits, e.g., zero-day markets and cyberwarfare. Infection cleanup, cleaning up after an infection, highly depends on the extent of the damage. It may be necessary to restore and/or repair files. Numerous antivirus companies provide this type of service. In some cases, when a virus runs with root privileges, it may be necessary to rebuild the entire system. In this case, recompiling the system may not be sufficient. The malware may have infected the compiler and created a backdoor, such that recompiling will simply reintroduce the malware into the compiler. In that case, it may be necessary to resort to original media and data backups. Software solutions, assurance methodologies, as discussed earlier, software security can be compromised as a result of memory safety attacks that include the following. Buffer overflows, which may be used to read-write data on stack heap or to inject code, ultimately via a root shell. Format string errors, used to read-write stack data. Integer overflow errors, used to change programs' control flow. And TOC/TOU problems, used to raise privileges. Various methodologies and associated approaches that may be used as part of the software development lifecycle to prevent these attacks are described in the following sections. Defensive programming. If you think of defensive driving as an analogy, it is about avoiding dependence on anyone but yourself. Minimizing trust makes it possible to better react to unexpected events, e.g., avoid a crash or worse. Defensive programming pretty much works in the same way. Each software module is responsible for checking the validity of all inputs it receives and throwing exceptions or exiting, rather than running malicious code and/or trusting inputs, even when they come from callers you know. Defensive programming requires code reviews. While real or imagined, these reviews force programmers to organize their code and focus on code correctness to address issues that could raise flags. One approach to defensive programming is to provide developers with better languages and libraries that render code less prone to mistakes. For example, Java runtime checks bounds automatically, and C++ comes with a safe STD. String class secure coding relies on practices and rules, as illustrated in the following code. Practice. Analyze all inputs, whatever they are 26. Char digit to char int I, char convert equals 123,456,789. Return convert I. Think about all potential inputs, no matter how peculiar 27. Char digit to char int I, char convert equals 123,456,789. If I0, I9, return convert I. Enforce rule compliance at runtime. Rule, make use of safe string functions or libraries. String library routines typically included in libraries assume target buffers have sufficient length 28. Char str4, char buff10 equals good, strcpy str, hello, overflows strcat buff, day to you, overflows buff safe versions. Check the destination length 29, char str4, char buff10 equals good, strcpy str, hello, sizeoff str, fails strcat buff, day to you, sizeoff buff. Fails again, you must know your system, S and languages semantics. Note that strncpy/strncat do not null terminate if they run up against the size limit. Therefore, it is better to use strlcpy/strlcat. These functions are not insecure, but they are commonly misused. It is actually even better to use safe string libraries, as they are designed to ensure that strings are used safely. The following code illustrates the use of the very secure FTP, VSFTP, string library 30, impl hidden void str alloc text, struct Mr *p str, const char *p src. Void str append str, struct Mr *p str, const struct Mr *p other. Int str equal, const struct Mr *p strl, const strct Mr *p str2. Int str contains space, const struct Mr *p str, struct Mr, / impl hidden void str alloc text, struct Mr *p str, const char *p src. Void str append str, struct Mr *p str, const struct Mr *p other. Int str equal, const struct Mr *p strl, const strct Mr *p str2. Int str contains space, const struct Mr *p str, rule, understand pointer arithmetic, illustration of pointer arithmetic, attribution. Copyright Rice University, OpenStax under CC by 40 license, credit, reproduced with permission from Dave Levin. The command sizeoff returns a number of bytes, but pointer arithmetic multiplies by the size of the type 31. Int size sizeoff int buff size equals, int asterisk buff ptr equals buff, while done, and in buff ptr, buff plus sizeoff buff ptr plus plus equals get next. Will overflow, so use the right units, while done, and in buff ptr buff plus size, buff ptr plus plus equals get next, stays in bounds practice. Defend against dangling pointers, illustration of defending against dangling pointers. Attribution, Copyright Rice University, OpenStax, under CC by 40 license, credit. Reproduced with permission from Dave Levin, rule, use null after free illustration of using null after free. Attribution, Copyright Rice University, OpenStax, under CC by 40 license, credit. Reproduced with permission from Dave Levin, practice, manage memory properly. Some programmers commonly use go-to chains in C to avoid duplicating or missing code. This approach is similar to using a try-finally clause in Java. A good coding practice is to always review and confirm the logic correctness 32. Int foo, int arg1, int arg2, struct foo pf1, asterisk pf2. Int rec equals pf1 equals malloc, sizeoff struct foo, if isoc arg1, go to done, pf2 equals malloc, sizeoff struct foo, if isoc arg2, go to fail arg2. Rec equals 0, fail arg2, free pf2, fall through done, free pf1, return rec, rule, always use a safe allocator. ASLR makes the base address of libraries unpredictable to defeat exploits. Using the same thinking and at the cost of reduced performance, addresses returned by calls to malloc should be made unpredictable to avoid heap-based overflows. Rule, favor safe libraries. Libraries encapsulate well-thought-out design, so take advantage of them. For example, smart pointers libraries, part of C++11 standard limit pointers to only safe operations and manage lifetimes appropriately. Networking libraries such as Google Protocol buffers and Apache Thrift are good for dealing with network-transmitted data. They are both efficient and also ensure inputs are handled securely, e.g., validation, parsing. Secure software implementation. The trusted computer base, TCB, of every system may include the monitor, compiler, OS, CPU, memory, keyboard, and other peripherals. Basic security assumes a correct, complete, and secure TCB. A good TCB is small and separates privileges. Using a small and simple TCB ensures that fewer components must work correctly to ensure security and are less susceptible to compromises. As security software in the TCB grows and becomes more complex, e.g., operating systems kernels used to enforce security often include a large amount of code, it becomes vulnerable and may be bypassed. Rather than compromising a device driver's security, it is best to reduce the size of the operating system kernel by creating microkernels that leverage device drivers located outside the kernel. The least privilege, a privilege separation approach, should also be applied to keep privileged operations modules as small as possible. It is important to only give the right level of privilege to a task. There is no reason to give more privileges than needed to a task. For example, it is not necessary for a web server daemon to allow root to bind to port 80. Doing so will enable the web server to run as root. Similarly, email editors should not make it possible to access a shell. You need to remember that trust is transitive. Trusting something means that you trust what it trusts, which can lead to trouble. Thinking about code safety is critical to ensure code safety and correctness. Code modularity is important as it helps to gain confidence in code function by function and module by module. It is necessary to verify that pre- and post conditions hold before and after a function is called, respectively. This helps define contracts for using modules, e.g. A given statement's post-condition needs to correspond to another statement's precondition. Pre- and post-conditions help document code and facilitate reasoning about code. Invariants help set conditions that are always true within parts of a function. All the aforementioned defensive programming techniques make it possible to verify functions based on code and associated annotations every time the code is invoked. Defensive programming allows reasoning about functions, safety each time they are called, and preconditions act as constraints that users must follow each time they use functions. The following code illustrates the preconditions that are required to ensure safety. The approach consists of identifying each memory access and annotating them with the preconditions they require and propagate the requirements up. Code showing the preconditions required to ensure safety. Identify each memory access and annotate them with the preconditions they require. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0 license, credit, reproduced with permission from Dave Levin. In this example, the memory access led to the following annotations 33. Requires. A equals null slash asterisk requires. O stroke lesser equal I slash requires. I size. A. The second annotation is taken care of by size ti, which ensures that 0 lesser equal I always holds. The two other annotations were not guaranteed by this function code, so they were moved up as preconditions to ensure that n lesser equal size. A. Here is another example of the pre- and post-condition checks that are needed when using or creating pointer respectively to ensure safety 34. Requires p equals null and p is a valid pointer, / ensures. Retval is the first 4 bytes p pointed to asterisk / int deref int asterisk p, return p. Ensures retval equals null and a valid pointer / void asterisk malloc, size tn void p equals malloc n, if p pair malloc, exit 1, return p. Testing. The goal of testing software quality is to ensure that the specification and implementation of programs match. Furthermore, testing assumes that the specification is correct, but it does not necessarily assume that implementation is correct. Developers should not be end-to-end testers. A developer should focus on the implementation and unit testing, while a tester focuses on the specification, which avoids related mistakes at both levels. Testing approaches may be classified as illustrated in Figure 14.33, a quadrant graph with 2 axes. The vertical axis is labeled manual to automated, and the horizontal axis is labeled black box to white box. Each quadrant is implied to represent a different combination of manual automated and black box white box testing approaches. Figure 14.33 testing approaches can be either manual or automated and test software using black box or white box techniques. Attribution, copyright Rice University, OpenStax, under CC by 40 license. As illustrated, there are various ways to conduct testing. Automated testing involves writing scripts or using testing frameworks to simulate user interactions with a software application. E.g., clicking buttons, entering data, and verifying outcomes. It enhances efficiency by automating repetitive testing tasks, which results in saving valuable time and resources. Automated testing also improves accuracy by minimizing human errors, and it enhances test coverage by enabling regression testing and continuous testing and delivery via CI/CD pipelines. Manual testing assumes the creation of efficient test suites to provide optimal test coverage and may struggle to achieve comprehensive coverage and scalability due to time and resource constraints. Black box testing does not require analyzing code, which works well for code that cannot be modified or is in a format that makes it difficult to analyze, e.g., obfuscated, managed, or binary code. White box testing assumes an efficient test suite to provide the detailed tests evaluating the source code. Test suites must be sized properly. Small numbers of tests cannot identify all the defects, and large numbers of tests will slow down testing and make it harder to maintain tests due to bloating and redundancy. For example, the SQLite library, version 3.20, included approximately 4,000 source lines of code, KSLOC, as compared to a project using it that had 730 times as much test code and scripts, i.e. 91,616, 0 KSLOC. It should be noted that KSLOC lines of code exclude blank lines and comments. Code coverage is a metric used to quantify the extent of program code testing when using a given test suite. Function testing coverage focuses on which functions are called. Statement testing coverage focuses on which statements are executed, and branch testing coverage focuses on which branches are executed. Testing coverage is computed as a percentage of a program's testing aspects covered by a given test suite. Practically, testing 100% of the code in a program is impossible. Cyclomatic complexity refers to the number of paths that exist in a program and should, in theory, be tested. That said, some code may not be accessible, and even if full testing were possible, it could take an infinite amount of time. Safety-critical applications do require 100% coverage. SQLite, as an example, has 100% branch coverage. In manual white box testing, tests are written by hand using full knowledge of the source code deployment infrastructure. They can be automated, e.g., run on all saves or commits. In manual black box testing, the tester interacts with the system in a black box fashion and crafts ill-formed inputs, tests them, and records how the system reacts. Automated testing techniques include code analysis static. Evaluating the source code can identify many of the bugs we have discussed. Dynamic, run in a VM and look for invalid writes, valgrind. Fuzz testing, generate many random inputs and see if the program fails. Typically, it involves many inputs. There are various possible kinds of fuzzing. Black box, the tool knows nothing about the program or its input. It is easy to use and get started, but it will explore only shallow states unless it gets lucky. Grammar-based, the tool generates input informed by grammar. More work is required to use it and to produce the grammar, but it can go deeper into the state space. White box, the tool generates new inputs at least partially informed by the code of the program being fuzzed. It is often easy to use but computationally expensive. Fuzzing inputs may be provided in different ways. Mutation. Take a legal input and mutate it, using that as input. The legal input might be human-produced or automated, e.g., from a grammar or SMT solver query. Mutation might also be forced to adhere to grammar. Generational, generate input from scratch, e.g., from a grammar. Combinations, generate initial input, mutate, generate new inputs, and generate mutations according to grammar. File-based fuzzing mutates or generates inputs, and then runs the target program with them to see what happens. An example is RAIDMSA 35, a mutation-based black box fuzzer, which mutates inputs that are given and passes them along 36. %echo 1 plus 2 plus 3 plus 4, RAIDMSA seed 12N45. Plus 3 plus minus 5, 1 plus 3 plus 41,907,596,644. 1 plus minus 4 plus 3 plus 4, 1 plus 2 plus 3 plus 4% echo, RAIDMSA seed 12N4 BC. Another example is BLAB, which generates inputs according to grammar, i.e. it is grammar-based, specified as regexps and CFGs 37. %blab e, WRSTP I12, 1432510, SODI YPC to 0 to PADU network-based fuzzing can act as half of a communicating pair. Inputs could be produced by replaying previously recorded interaction and altering it or producing it from scratch, e.g., from a protocol grammar. It can also act as a man-in-the-middle by mutating inputs exchanged between parties, perhaps informed by grammar. There are many fuzzers out there, such as American Fuzzy Lop, mutation-based whitebox buzzer, Spike Library for creating network-based fuzzers, Burp Intruder, automates customized attacks against web apps, BFF, and Sully. Fuzzers help find the root cause of a crash by answering questions such as, is there a smaller input that crashes in the same spot, makes it easier to understand? Are there multiple crashes that point back to the same bug? Can you determine if a crash represents an exploitable vulnerability? In particular, is there a buffer overrun? Fuzzing may help find memory errors. First, compile the program with address sanitizer ASAN, which instruments accesses to arrays to check for overflows, and use after-free errors, then fuzz it and check if the program crashed with an ASAN signaled error. If that is the case, worry about exploitability. Similarly, you can compile with other sorts of error checkers for testing, e.g., Valgrind memcheck. Automated black box testing uses fuzzing components as explained to generate test cases, execute the applications, and perform detection and logging. In automated white box testing, tests are created automatically dynamically. Tools exist to perform this type of testing and may record a trace of the tested program on well-formed inputs and perform symbolic execution to capture constraints on inputs. Automated testing may then negate a constraint or use a constraint solver to derive a new input and run on that input. When using American Fuzzy Lop, compile time instrumentation is provided, and the instrumentation guides genetic algorithms. Penetration testing. Another testing technique is penetration, pen testing. Fuzz testing is a form of pen testing. Pen testing assesses security by actively trying to find exploitable vulnerabilities, which is useful for both attackers and defenders. Pen testing is useful at many different levels, e.g., for testing programs, testing applications, testing a network, testing a server. Reverse engineering. Reverse engineering, RE, is the process of discovering the technological principles of a program through analysis of its structure, function, and operation. It corresponds to the solution development lifecycle run backward. Reverse engineering is useful for malware analysis, vulnerability or exploit research, copyright patent violations check, interoperability assessment, e.g. understanding a file or protocol format, and copy protection removal. The legality of RE is a gray area and usually breaches the End-User License Agreement, EULA software contract. Additionally, the Digital Millennium Contract Act, DMCA, governs reverse engineering in the United States. You may circumvent a technological measure solely for the purpose of enabling interoperability of an independently created computer program. There are two techniques used for RE, and a combination of the two works best in general. Static code analysis focuses on the code structure and uses a disassembler. Dynamic code analysis focuses on the code operation and uses tracing, hooking, and debuggers. Disassembling code is difficult and often imperfect due to benign optimizations, e.g. constant folding, dead code elimination, inline expansion, and intentional obfuscation, e.g. packing no-op instructions. Malware uses a lot of packing. Overall, 90% of the code is packed. Dynamic analysis takes advantage of debuggers features, e.g., trace every instruction a program executes via single stepping. Let the program execute normally until an exception. At every step or exception, observe modify instructions, stack heap register set, inject exceptions at arbitrary code locations, use int3 instruction to generate a breakpoint exception. Debugging has many benefits, as it is sometimes easier to see what the code does or allow unpacking to let the code unpack itself and debug as normal. Most debuggers have built-in disassemblers anyway. It is always possible to combine static and dynamic analysis. However, it is possible to run into difficulties with debugging when executing potentially malicious code using an isolated virtual machine. The attacker may have used anti-debugging methods to detect the debugger and change the program behavior so that it runs differently than when not being debugged, e.g. used isDebugger present, int3 scanning, timing, VM detection, pop SS trick. Anti-debugging can be tedious. A common way of evasion is to detect evidence of monitoring systems, e.g. fingerprint a machine, look for fingerprints, or hide real malicious intents if necessary as follows. IFVM present, or debugger present. Terminate hide real intents. Else, malicious behavior, real intent. The general taxonomy of malware evasion is illustrated in Table 14. 5. Difficulty layer of abstraction examples. Easiest application installation, execution. Easy hardware device name, driver. Somewhat difficult environment memory, execution artifacts. More difficult behavior timing. Table 14. 5. Malware evasion taxonomy. In general, there is a prevalence of evasion, and 40% of malware samples exhibit fewer malicious events with a debugger attached. Internet solutions, cybersecurity. The Internet is a network of networks, which is an interconnected set of nodes. Nodes at the edge of the network are called end hosts, while nodes within the core of the network are routers. The network uses IP addresses to name the nodes, while humans use more easily memorable host names that point to the corresponding IP addresses. The Dynamic Host Configuration Protocol, DHCP, can create IP addresses and associate them with hosts as they connect to the network. The Domain Name Service, DNS, maps domain names to corresponding routable IP addresses, Figure 14. 34. Illustration of how DHCP can create IP addresses and associate them with hosts as they connect to the network. DNS maps domains names to corresponding routable IP addresses. DHCP client, switch 1, router 1. Cloud, router 2, switch 2, server, Figure 14. 34 users obtain IP addresses from the DHCP server when they boot up a system. This process helps ensure that only authorized users can access the Internet. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Web Infrastructure Assurance. The World Wide Web, the web, is an organizational system for information that is accessible by using the Internet. In other words, the web infrastructure is provided by the TCP/IP network stack. In particular, review the roles of the various layers of the Internet TCP/IP network stack, the protocols associated to each layer, and how packets are created and exchanged over the Internet. It is important to know what each layer is responsible for and what the predominant protocols are at each layer. Finally, experimenting with existing network protocol analyzers, e.g. Wireshark to study packets and communication is recommended. The overall design principles of the TCP/IP network stack have been critical to making an Internet that can evolve with changing needs, at least for the most part, but the details really matter. In the following, we will dig into specific protocols to understand the kinds of attacks that can happen at the networking layer and how to protect against them. As noted earlier, the DHCP protocol can create IP addresses dynamically and associate them to hosts as they connect on the network. The DNS maps domains names to corresponding routable IP addresses, Figure 14. 35. Illustration of how DHCP protocol creates IP addresses dynamically and associates them to hosts as they connect on the network. Host doesn't have IP address yet, DHCP discover, DHCP server offer. Host doesn't know who to ask for one, DHCP request asks for the offered IP address, DHCP server DHCP ACK. Solution, discover one on the local subnet, Figure 14. 35. The DHCP protocol creates IP addresses dynamically and associates them to hosts as they connect on the network. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Credit, reproduced with permission from Dave Levin. Because DHCP requests are broadcasted to all nodes neighboring nodes initially, attackers on the same subnet can hear a new host request and can race the actual DHCP server to replace the DNS server. Redirect any of a host's lookups such as, what IP address should I use when trying to connect to Google.com, to a machine of the attacker's choice, or the gateway, where the host sends all of its outgoing traffic so that the host does not have to figure out routes by itself. By making a machine of the attacker's choice the gateway, the attacker would be able to act as the MIT-M and gain access to all of the traffic to and from the user's machine. So, how can a user detect such an attack? The DNS service divides the domain name namespace into zones for administrative reasons. Subdomains do not need to be in the same zone, which allows the owner of one zone, e.g., NAU edu, to delegate responsibility to another, e.g., CS, NAU edu. The name server is the piece of code that answers queries of the form, what is the IP address for CS, NAU edu. Every zone must run at least 2 name servers. Caching is central to the success of the DNS service. Unfortunately, it is also central to attacks such as cache poisoning, which consists of filling a victim's cache with false information, figure 14. 36. Illustration of DNS cache poisoning, consisting of filling local nameserver DNS cache with false information. Will cache www bank com equals 6666 and ignore authorities' answer. Figure 14. 36. A DNS cache poisoning example consists of filling a local name server DNS cache with false information. Attribution: copyright Rice University, OpenStax, under CC by 4. 0. License. In the diagram, the recursive name server is the name server that does the heavy lifting and issues DNS queries on behalf of the client resolver, i.e., the host that asks DNS queries on behalf of the client until an authoritative answer returns. Because the local resolver has a lot of incoming-outgoing queries at any point in time, it determines which response maps to which queries by using a query ID, i.e., a 16-bit field in the DNS header shown as 16,322 as an example in the diagram. The requester sets the query ID to whatever it wants, and the responder must provide the same value in its response. For a cache poisoning attack to work, the attacker must guess the query ID, ask for it, and go from there. Note that a partial defense is to randomize query IDs, but this takes space, and the attacker can issue a lot of query IDs. Once the attacker has guessed the query ID, it must guess the source port number, which is typically constant for a given server, often always 53. Note that if the answer is already in the cache, the attacker will avoid issuing a query in the first place. The same cache poisoning approach may be used to poison more than one record, figure 14. 37. Illustration of using cache poisoning to poison more than one cached record. Will cache the person to ask for all bank com queries is 6666, figure 14. 37. The same cache poisoning approach may be used to poison more than one cached record. Attribution: copyright Rice University, OpenStax, under CC by 4. 0. License, credit, reproduced with permission from Dave Levin. Note that randomizing query ID is not sufficient in itself because there are only 16 bits of entropy. So the source port should be randomized as well because there is no reason for it to stay, and it is possible to obtain another 16 bits of entropy in this way. Another solution is to use Domain Name System Security Extensions, DNSSEC. If everyone has deployed it, and if you know the root's keys, then DNSSEC prevents spoofed responses. DNSSEC uses public key infrastructure, PKI, to secure communication between the DNS servers in the various zones, and the authoritative answer is signed. But unlike PKIs, if one or more named servers has not deployed DNSSEC, which is the case in incremental deployments, then DNSSEC is not very useful. While it is possible to ignore named server responses without DNSSEC, this would improve security, but it prevents the user from connecting to a number of hosts. Now let us focus on the networking protocols and study possible TCP/IP attacks and defenses. In particular, let us look at the inter-network layer, which works across different link technologies, bridges multiple subnets to provide end-to-end internet connectivity between nodes, and provides global addressing, IP addresses. Note that if the transport layer uses the TCP protocol, it will only result in best effort delivery of data, i.e., no retransmissions. The IP4 packet header used by the IP protocol is 20 B long, and one of the header fields is the source IP address. Nothing in the IP protocol enforces that the source IP address is yours. Furthermore, the IP protocol does not protect the payload or headers. Source spoofing exploits this, figure 14. 38. Illustration of how source spoofing exploits the fact that IP protocol does not protect the payload or headers. There is nothing in IP that enforces your source IP address is really yours. With eavesdrop tamper, IP provides no protection of the payload or header. Figure 14. 38. Source spoofing exploits the fact that the IP protocol does not protect the payload or headers. Attribution: copyright Rice University, OpenStax, under CC by 40 license, credit, reproduced with permission from Dave Levin. Source spoofing may be used to send many emails from one computer, i.e., email spamming. The recipient may, in return, block emails from a given source IP address, but the attacker could spoof the source IP address as a countermeasure. So, does a packet you receive have a spoofed source? Because the internet operates via destination-based routing, the response to a spoofed source message sent by an attacker goes to the spoofed source rather than the attacker, i.e., PKT spoofed source, destination. PKT spoofed source. Therefore, to know whether a packet you receive has a spoofed source, you can send a challenge packet to the possibly spoofed source, e.g., a difficult-to-guess random number used once non-C. If the recipient can answer the challenge, then it is likely that the source was not spoofed. The problem with this approach is that you have to do this for every packet, i.e., every packet should have something difficult to guess. This is analogous to the easily predicted query IDs in the DNS query poisoning attacks that facilitated Kaminsky's attack. Source spoofing may also be used for denial of service (DoS) attacks. The idea is to generate as much traffic as possible to congest the victim's network. An easy defense is to block all traffic from a given source near the edge of your network. An easy countermeasure is to spoof the source address. Challenges will not help here because the damage has been done by the time the packets reach the core of your network. So, ideally, you would need to detect such spoofing near the source, and egress filtering does exactly that. The point router switch at which traffic enters your network is the ingress point, and the point router switch at which traffic leaves your network is the egress point. While you do not know who owns all IP addresses worldwide, you do know who in your network gets what IP addresses. Therefore, your egress point can drop any packets whose source IP address does not match the IP address your network assigned to that machine. This egress filtering approach is not often deployed because your egress point bears the costs, but your network does not gain any benefit. The defense methods suggested earlier to counter eavesdropping tampering with IP headers are clearly not bulletproof. A better protection method against the fact that no security is built into IP is to deeply secure IP over IP. This is done by using a virtual private network, VPN. The goal of a VPN is to allow a client to connect to a trusted network from within an untrusted network. For example, you could use a VPN to connect to your company's network for payroll file access while visiting a competitor's office. In that case, a VPN client and server would create an end-to-end encrypted authenticated channel, as illustrated in Figure 14.39. A predominant way of achieving this is to use Internet Protocol Security, IPsec, to secure IP datagrams, instead of using TLS or Secure Shell at the application layer level. This was considered a good idea circa 1992-1993, as it would secure all traffic, not just TCP/UDP, and automatically secure applications, without requiring changes. It also provides built-in firewalling access control. Initial proposed standards were published in 1988, and a revision, i.e., Internet Key Exchange version 2, was approved in 2005. A diagram showing a trusted client, labeled C, connected to a server, labeled S, via an encrypted connection over an untrusted network. The server connects to other servers within a trusted network, with a note that this part is not necessarily encrypted. Figure 14.39. A VPN client and server can be used to create an end-to-end encrypted authenticated channel. Attribution: Copyright Rice University, OpenStax, under CC by 4. 0 license, credit, reproduced with permission from Dave Levin. The Internet Key Exchange addressed anonymity issues and DoS prevention. There have been many implementations of IPsec, and nearly all deployments are in VPN settings. People ended up switching over to SSL VPN, but that was not how SSL was intended to be used. IPsec is regarded today as a semi-failure as it is complex, hard to use, and exhibits design flaws. SEC did not get the usage model right, but SSL TLS and SSH, discussed later in this subsection, got it right. IPsec operates in a few different modes. Transport mode encrypts the payload but not the headers. Tunnel mode encrypts the payload and the headers. The corresponding packet formats are illustrated in Figure 14.40. Illustration of how ISEC uses corresponding packet formats for transport mode and tunnel mode. Transport mode, IP-HDR, ISEC HDR, TCP HDR data. Tunnel mode, IP-HDR, ISEC, IP-HDR, TCP HDR data. Figure 14.40. ISEC uses specific packet formats for transport mode and tunnel mode. Attribution: Copyright Rice University, OpenStax, under CC by 40 license, credit. Reproduced with permission from Dave Levin. For routing to work when tunnel mode encrypts the headers, IPsec encrypts the entire IP packet and makes it the payload of another IP packet. Figure 14.41 illustrates using IPsec in tunnel mode. In this case, the VPN server decrypts and then sends the payload, itself a full IP packet, as if it had just received it from the network. From the client-server's perspective, it looks like the client is physically connected to the network. A diagram showing a trusted client, labeled C, connected to a server, labeled S, via an encrypted connection over an untrusted network. The connection carries an encrypted packet labeled EP. The server then forwards the packet labeled P to other servers within a trusted network, which is not necessarily encrypted. Figure 14. 41 in ISEC tunnel mode, the VPN server decrypts and then sends the payload, itself a full IP packet, as if it had just received it from the network. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Credit, reproduced with permission from Dave Levin. Now let us focus on the transport layer of the TCP/IP stack and study possible TCP/IP attacks and defenses. The transport layers ensure end-to-end communication between processes. It provides different services, including UDP, unreliable datagrams, and TCP, reliable byte stream. Reliable means that it keeps track of the data appropriately received and retransmits packets as necessary. Given best effort delivery, the goal is to ensure reliability. All packets are delivered to applications in unmodified order, reasonably high probability, and TCP must robustly detect and retransmit corrupt or lost data. TCP's second job is flow and congestion control. The idea is to try to use as much of the network as is safe, not adversely affecting others, performance, and efficient, using network capacity. The TCP solution is to dynamically adapt how quickly it sends packets based on the network path's capacity. Furthermore, when an ACK doesn't return, the network may be beyond capacity and slow down. TCP is a connection-driven protocol, and there are various TCP flags in the TCP header that are used to manage connections as indicated. SYN, used for setting up a connection. OSK, acknowledgements for data and control packets. FIN, used for shutting down a connection two-way, using FIN and FIN plus ACK. RSD, used for shutting down notification, says, delete all your local state, because I do not know what you're talking about. Various attacks are known to take advantage of the transport layer vulnerability. For example, SYN flooding takes advantage of a vulnerability in TCP's connection, setup's three-way handshake, as illustrated in Figure 14. 42. A waterfall diagram representing a sequence of messages exchanged between two entities, labeled A and B, over time. The steps include SYN from A to B, SYN plus ACK from B to A, and ACK from A to B. After the SYN plus ACK is received by A, there is a second SYN plus ACKX, sent from B to A. A note on the right side indicates that at this point, B allocates state for the new connection, including IP, port, and maximum segment size. Figure 14. 42 SYN flooding takes advantage of a vulnerability in TCP's connection setup's three-way handshake. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Credit reproduced with permission from Dave Levin. If B does not receive an acknowledgement, it will hold on to this local state and retransmit SYN plus ACK until it hears back or times out up to 63S. It is easy to detect many incomplete handshakes from a single IP address and then spoof the source IP address as illustrated in Figure 14. 43. It is just a field and a header, as described earlier, that can be set to whatever the attacker C likes. A possible problem is that the host who owns that spoofed IP address may respond to the SYN plus ACK with a RSD, deleting the local state at the victim. Therefore, an attacker should spoof an IP address of a host that it knows will not respond. A diagram showing a series of SYN requests sent from A to B, eventually exhausting memory at B, the victim. Multiple blocks labeled IP port MSS accumulate at B, indicating that state is being allocated for each connection. The diagram shows that new connections will fail due to insufficient memory. An attempt from C to send a SYN request to B is blocked, indicated by a red X. Figure 14. 43. This IP address spoofing example illustrates how to detect many incomplete handshakes from a single IP address and then spoof the source IP address. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Credit reproduced with permission from Dave Levin. A defense against SYN flooding is to use SYN cookies, as illustrated in Figure 14. 44. A diagram showing a sequence between A and B. A sends SYN to B. B responds with SYN plus ACK, where the sequence number SECNO is a function of the data F data. a replies with ACKF data plus 1. On the right, it is noted that instead of storing the data, B sends it to the initiating host, A, and checks if the returned data is valid for the connection before allocating state. Figure 14. 44 using SYN cookies provides a defense against SYN flooding. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. Credit: reproduced with permission from Dave Levin. The SYN cookie format is illustrated in Figure 14. 45. A diagram showing a sequence where A sends SYN to B, B responds with SYN plus ACK, where the sequence number is calculated as a function of the data secno equals F data, and it replies with ACK F data plus 1. On the right, there is an explanation of the function F. For the 32-bit sequence number, which includes a slow-moving timestamp to prevent replay attacks, MSS, the information needed for the connection, and a secure hash, including IPs, ports, MSS, and timestamp. A note explains that the secure hash makes it difficult for an attacker to guess the correct ACK in case of spoofing. Figure 14. 45 SYN cookies use a specific format. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. Credit: reproduced with permission from Dave Levin. Injection attacks take advantage of having a node on the path between source and destination. In that case, injecting packets with the correct sequence number is trivial. If the node is not on the path, it would need to guess the sequence number, which is difficult. Initial sequence numbers used to be deterministic, and it was easy to wreak havoc by sending RSDs, injecting data packets into an existing connection, i.e. TCP veto attacks, or initiating and using an entire connection without ever hearing the other end. Figure 14. 46 illustrates one type of attack known as the Mitnick attack. A diagram illustrating an attack where an attacker spoofs a connection between an external server and a trusted server. The attacker sends a SYN flood to the trusted server, then spoofs the trusted server's IP address in a SYN request to the external. Due to the flood, the trusted server is too busy to respond with RSD reset. The attacker then sends an ACK with a guess sequence number secno. If successful, the external grants access to the attacker. Steps 1-6 are listed to explain the attack process, and a note states that any connection from the spoofed IP is granted access to the external server. Figure 14. 46. A Mitnick attack spoofs a trusted server's IP address to gain access to the external server to which it connects. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. Credit: reproduced with permission from Dave Levin. A typical defense is to ensure that the initial sequence number is difficult to predict. OpenStax attacks take advantage of the fact that TCP uses ACKs not only for reliability, but also for congestion control, i.e. the more ACKs come back, the faster it can send, as illustrated in Figure 14. 47. A diagram showing data transmission between A and B. A sends bytes 1500 to B, and B responds with ACK 1501, indicating it is expecting the next byte to be 1501. A then sends bytes 1501 2001 and bytes 222502, with B continuing to expect the next byte starting from 1501. Figure 14. 47. An OpenStax attack takes advantage of the fact that TCP uses ACKs not only for reliability, but also for congestion control. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. Credit: reproduced with permission from Dave Levin. An attacker can exploit this as illustrated in Figure 14. 48. A diagram showing ascending bytes 1500, bytes 1501 2001, and bytes 222502 to B, with B responding with ACK 1501. On the right, a note from B explains that normally B would need to receive data to send ACKs quickly, but it suggests that convincing it to send much faster could effectively cause it to perform a denial of service (DoS) attack on its own network. Figure 14. 48. An OpenStax exploit convinces TCP to send packets quickly, which results in a DoS attack on the network. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. Credit: reproduced with permission from Dave Levin. The actual attack scheme is illustrated in Figure 14. 49. A diagram showing ascending bytes 1500, bytes 1501 2001, and bytes 222502 to B, with B sending early ACK 1501, ACK 2001, and ACK 2502 optimistically. B predicts the sequence numbers and timing. A perceives this as a fast connection, but eventually, A's packets start to get dropped. B continues sending ACKs, making the dropped packets irrelevant as long as the ACKs are correct. Figure 14:49 The opt-ACK attack scheme results in packets getting dropped, while TCP is fooled into thinking that packets were acknowledged. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. The big deal with this attack is its amplification factor. An attacker sends many bytes of data, causing the victim to send many more in response. There are examples of such attacks on NTP and DNSSEC. The attack is amplified in TCP due to its support for cumulative ACKs, i.e., ACKX says, I've seen all bytes up to but not including X. Figure 14:50 illustrates the maximum number of bytes that can be sent by a victim per ACK. A formula showing the calculation for packets sent per ACK, represented by the maximum window size divided by the MSS, maximum segment size, multiplied by the bytes per packet, which includes the sum of Ethernet 14 bytes, TCP IP 40 bytes, and MSS. Figure 14:50 This illustration shows the maximum number of bytes per ACK. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Figure 14:51 shows the maximum number of ACKs that an attacker can send per second. Therefore, the amount of damage is the value of max window size and MSS, e.g., default max window size, 65,536 and default MSS, 536, in that case. Default amp factor, 65,536, 1536 plus 154, 1336x. Window scaling lets you increase this by a factor of 214. Window scaling amp factor, (1336 214, (22m), using a minimum MSS of 88, 32m. A challenge is to find a solution to defend against opt-ACK in a way that is still compatible with existing implementations of TCP. Also, note that an essential goal in networking is incremental deployment. Ideally, we should be able to benefit from a system modification when even a subset of hosts deploy it. Now let us focus on the application layer of the TCP IP stack and study possible TCP IP attacks and defenses. The Secure Socket Layer, SSL protocol, was originally a Netscape proprietary protocol that targeted e-commerce applications, i.e. what people thought the web was for in 1994. The objective was to address outcomes such as send my credit card to Amazon securely. The basic principle, circa 1994, was to authenticate the server via certificate and let the client access the server unauthenticated. SSL v1 was designed by Kip Hickman and had serious security flaws. He addressed some of the flaws in SSL v2, which still had security issues but was widely deployed. SSL v3 fixed these problems. The Transport Layer Security (TLS) 1.0 protocol was the first standardized version of SSL with some improvements for key derivation, referred to IETF, org RFC 2246. TLS 1.1, RFC 4346, addressed some security flaws, and TLS 1.2, RFC 5246, added more flexibility in using hash functions. TLS 1.3 brought significant changes, e.g., no RSA key exchange for forward secrecy, authenticated encryption modes, no RTT handshakes. As explained earlier, a trusted CA may vouch that a certain public key belongs to a particular site and issue a TLS certificate that abides by the X. 509 format. Web applications use HTTP over SSL TLS HTTPS, in which case the client knows that the server expects HTTPS because it is specified in the URL and supported on a separate port on the server. Furthermore, the server certificate has its domain name. HTTP is stateless, and the lifetime of an HTTP session is as follows. The client connects to the server. The client issues a request. The server responds. The client issues a request for something in the response. The interaction continues until client has received all the information it needs. The client disconnects. Because asymmetric private key operations are expensive and HTTPS tends to involve a lot of SSL TCP connections, caching pays off. Each handshake establishes a session, and clients can resume the session with the same keying material, skipping the key exchange. If the client and servers do not know each other's capabilities, they can discover them and automatically upgrade to TLS. This, however, may allow downgrade attacks. DoS attacks on SSL-TLS rely on the SSL-TLS connection, requiring TCP handshake, and TCP connections are easy attack with a DoS. Protection against these types of attacks needs to be at a lower layer and is provided by Datagram TLS, RFC 4347. DTLS is a slight modification of TLS that provides reliability for the handshake and ensures that data records are independent. Tatu Ilonen originally designed the Secure Shell (SSH) protocol, which is a replacement for RSH. It is now the standard tool for secure remote login, and it provides a lot of authentication mechanisms, such as remote X, file transfer, and port forwarding. The transport protocol used by SSH looks a lot like TLS. SSL does not use certificates. The server just has a raw public key, and it provides the key when the client connects. The client stores the server's key on the first connection. Any changes in the key result in an error. The key can be authenticated from the band, i.e., the server operator tells the client the key fingerprint hash over the phone. Only the most concerned people do this. The SSH leap of faith authentication was considered extreme initially, but is now considered clever. SSH client authentication first requires server authentication and then authenticates the client using various negotiated mechanisms, e.g. raw password, challenge response, public key, GSS API, Kerberos. SSH provides port forwarding tunneling features. SSH port forwarding redirects network traffic to a particular port IP address so that a remote host is made directly accessible by applications on the local host. The destination may be on the remote SSH server, or that server may be configured to forward to another remote host. SSH tunnels are powerful tools for IT administrators and malicious actors because they can transit an enterprise firewall undetected. As a result, tools are available to prevent unauthorized use of SSH tunnels through a corporate firewall. Figure 14.52 illustrates how an X11 remote connection can be established using SSH. A diagram showing an X server on the left connected to an SSH client, with communication happening through localhost 6000. On the right, an X client is connected to an SSH server, with communication through localhost. The diagram illustrates an X11 forwarding setup using SSH. Figure 14.52. With an X11 remote SSH connection, the server simply has to set and display localhost. XXXX and the applications just automatically work. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Finally, SSH is backward and compatible with RSH, so other applications can be securely remoted without port forwarding. This is also useful when applications need insecure remote access. The various application layer protocols we discussed are subject to a variety of attacks, including attack vectors, site design attacks, UI interface-based attacks, PKI attacks, implementation attacks, e.g. null termination attacks, go-to-fail, heartbleed, brsirc attack, logjam, cloudbleed, and client-side HTTP interception. Attack vectors are designed to attack the weakest certificate authority. They attack browser implementations. They may also find and exploit a key generation library bug that leads the attacker to discover all the private keys issued by that authority. They also attack the cryptographic primitives, although this was more difficult to achieve. SSL strip attacks are examples of attacks that go after site design by proxying through the content without HTTPS. The defense is to default to HTTPS for all websites. You can also use HSDS, Hypertext Strict Transport Security, which is enforced by browsers. The header states to always expect HTTPS. HTTPS everywhere can also be forced using a browser extension. Some site design attacks use mixed content attacks. In this case, a page loads over HTTPS but contains content over HTTP. e.g. JavaScript. An active attacker can tamper with HTTP content to hijack the session. The defense is to issue browser warnings, e.g., this page contains insecure content, but the use of these warnings is inconsistent and the warnings are often ignored. UI interface-based attacks exploit invalid certs, i.e., expired, misidentified URL, unknown CA such as a self-signed certificate. The defense is to issue browser warnings and require users to go through an anti-usability page to continue. Another type of UI interface-based attack is a picture-in-picture attack that spoofs the user interface, i.e., the attacker page draws a fake browser window with a lock icon. In this case, the defense is to create an individualized image. PKI attacks compromise CAs. there was an example of such an attack in 2011 against a Dutch CA named DigiNotar. It issued a Google.com certificate to an attacker that subsequently used it to orchestrate MIT-M attacks in Iran. Nobody noticed the attack until someone found the certificate in the wild. DigiNotar later admitted that dozens of fraudulent certificates were created. Google, Microsoft, Apple, and Mozilla all revoked the root DigiNotar certificate. The Dutch government took over DigiNotar, and the company subsequently went bankrupt and closed. In general, MD5 SHA-1 is known to break and can generate collisions. In 2008, researchers showed they could create a rogue CA certificate using an MD5 collision. The attack consisted of colliding messages, A and B, with the same MD5 hash as follows: A, site certificate. CN equals attack, pub key equals. B, delegated CA certificate, pub key equals, is allowed to sign certs for. Get CA to sign a signature is sign, MD5, message. Signature also valid for B, same hash. The attacker is now a CA. Make a cert for any site, browsers will accept it. MD5 CA certificates still exist, but CAs have stopped signing certificates with them. SHA-1 should not be used either. There are numerous other types of attacks. GoToFail Feb 2014 was an Apple SSL bug that resulted in skipping certificate check for almost a year. Heartbleed April 2014 was an OpenSSL bug that leaked data, possibly including private key. Mozilla BRCirc vulnerability, Oct 2014, was a bug in verifying certificate signatures that allowed spoofing certificates. Logjam, Oct 2016, took advantage of a TLS vulnerability to man-in-the-middle downgrade attacks. Cloudbleed, one of the most popular content delivery networks, acts as the SSL endpoint for many servers. A buffer overflow attack caused it to leak HTTPS data. Client-side HTTP interception leverages the fact that most antivirus software intercepts your HTTPS, generating poor implementations and introducing new vulnerabilities. Web mobile applications frameworks assurance. The most typical web mobile application frameworks are web servers and web browsers. Other web mobile application frameworks, e.g., application servers, business process management suites, operate using web browsers and extended web servers and use the same security mechanisms. This subsection will only focus on web servers and web browsers. Various types of attacks affect web information and interactions, including SQL injection, cross-site scripting XSS, path directory traversal, cross-site request forgery, remote file inclusion RFI, phishing, clickjacking, authentication authorization attack, buffer errors, web browser attack, information leak disclosure, and web server attack. Here are several security risks we try to protect web servers and web browsers against. Risk 1. We want data stored on a web server to be protected from unauthorized access. Risk 2. We do not want malicious or compromised sites to be able to trash files programs on user computers. Risk 3. We do not want a malicious site to be able to spy on or tamper with information or interactions with other websites. The Federal Communications Commission has identified cybersecurity tips to help organizations protect against cyber threats when using the internet. These include 38. Ensure employees are trained regarding cybersecurity, including the organization's security principles. Keep the system updated with the latest security software and frequently run antivirus software. Install and maintain a firewall, which is a collection of programs designed to prevent hackers and other unauthorized users from accessing a system. Ensure that mobile devices and laptops are included in the security plan and secure all such devices. Back up important files and data and store the backed up information separately. Ensure all employees have passwords and other credentials required to access the system and provide access on an as-needed basis. Ensure that Wi-Fi networks are hidden and secured through encryption. The following design and implementation guidelines can be accessed online through a browser search. OMG cybersecurity initiatives and related standards, guidelines, best practices, and other resources. NIST cybersecurity standards, in particular NIST SB 853, SB 80171, CSF, SB 1800 series. Other global IT security frameworks and standards. ISO 27000 series, COBIT, CIS controls, HITRUSD Common Security Framework, GDPR, COSO. Industry IT security standards. PCI HIPAA, PCI DSS, Sarbanes-Oxley SOX, GLBA, Cyborg, Safe Code, Open Source Security Testing Methodology Manual, OSSTMM. Open Web Application Security Project, OWASP. Web Application Security Consortium Threat Classification, WASCTC. Penetration Testing Execution Standard, PTES. Information System Security Assessment Framework, ISSAF. Cloud-centric solutions, cybersecurity. The need to reduce costs and make it more responsive to business changes are driving more and more internet solutions, e.g., web mobile information systems, to various cloud platforms. There are numerous obstacles that make it difficult for end-users organizations to adopt the cloud from a TRM assurance standpoint. Providing security for cloud environments that matches the levels found in commercial internal data centers is essential to helping modern organizations compete and to allowing cloud service providers, CSPs, to meet their end users' needs. Managing risk in the cloud requires that users fully consider exposure to threats and vulnerabilities, not only during procurement, but also as an ongoing process. Security in the cloud is a constant process, and cloud users should continually monitor their cloud resources and work to improve their security posture. Threat actors in the cloud may target the same types of weaknesses as the ones found in traditional system architectures. However, when organizations use the cloud, they face additional cyber threats, including the following: malicious CSP administrators. They can leverage privileged credentials or position to access, modify, or destroy information stored on the cloud platform. They can also leverage privileged credentials or positions to modify the cloud platform to gain access to networks connected to or consuming cloud resources. Cyber criminals and/or nation-state-sponsored actors. They can leverage a cloud architecture or configuration weakness to obtain sensitive data or consume cloud resources at the victim's expense. They may exploit weak cloud-based authentication mechanisms to obtain user credentials, e.g., password spray attacks. They may leverage compromised credentials or incorrect access privileges to access cloud resources. They may gain privileged access to the cloud environment to compromise tenant resources. They may leverage the trust relationship between an end user or organization's networks and cloud resources to pivot from clouds into protected networks or vice versa. Untrained or neglectful customer cloud administrators. They may expose sensitive data or cloud resources unintentionally. Cloud infrastructure assurance. To match the levels of security that end users experience on-premise, CSPs must make the proper investments in providing, proving, and assuring appropriate levels of security over time. This requires building security and trust architectures that can assure each end user's applications and data are isolated and secured from those of others. Before moving mission-critical information systems to the cloud, end users require robust cybersecurity, trustworthy cybersecurity assurance, and cloud governance as follows. Robust security requires moving beyond a traditional perimeter-based approach to a layered cloud security architecture and an approach that assures the proper isolation of data, even in a shared, multi-tenant cloud. This includes content protection at different layers in the cloud infrastructure, such as at the storage, hypervisor, virtual machine, and database. It also requires mechanisms to assure confidentiality and access control. These may include encryption, obfuscation, and key management, as well as isolation and containment, robust log management, and an audit infrastructure. The security architecture provides the isolation, confidentiality, and access control required to protect end users, data, and applications. Trustworthy cybersecurity assurance requires that the end users have confidence in the integrity of the complete cloud environment. This ranges from the physical data centers to the hardware and software, as well as the people and processes employed by the CSP. This requires establishing an evidence-based trust architecture and control of the cloud environment provided by the CSP. It requires that the CSP provide adequate monitoring and reporting capabilities to assure the end user of transparency around security vulnerabilities and events. This should include audit trails that help the end user meet internal or external demands for provable security. A CSP should also deliver automated notification and alerts that support the end user's existing problem or incident management protocols so they can manage their total security profile most easily. All of these collectively help assure the end user of the operational quality and security of the CSP. Cloud governance requires the CSP to offer utilities that allow the end user to monitor their environment for security and other key performance indicators. KPIs, such as performance and reliability, almost as well as they could in their own on-premises environment or data center. Think it through. Cybersecurity on the internet versus the cloud. Think about cybersecurity for systems that use the internet and compare that to cybersecurity for systems that access the cloud. Note that moving systems to the cloud requires robust cybersecurity, trustworthy cybersecurity assurance, and cloud governance as explained earlier in this section. Evaluate how these requirements differ from those set forth for systems that use the internet to determine whether cybersecurity on the cloud can be handled in the same way as security on the web. Cloud services assurance. Because end users leverage various service types such as infrastructure as a service IaaS versus platform as a service PaaS to create solutions in the cloud, CSPs and cloud end users share unique and overlapping responsibilities to ensure the security of services and sensitive data stored in public clouds. Shared responsibility considerations include threat detection, incident response, and patching updating. An example of a PaaS service provided by cloud platforms today is IoT PaaS. As noted earlier, there are lots of challenges faced by IoT cloud platforms that affects the TRM security and integrity privacy assurance quality. IoT devices and data are vulnerable to various threats, such as cyberattacks, data breaches, unauthorized access, and malicious manipulation. These threats can compromise the functionality, integrity, and confidentiality of IoT systems, as well as expose sensitive and personal information of customers and users. IoT cloud platforms also need to adhere to the evolving regulations and standards that govern the collection, storage, and use of IoT data, such as the General Data Protection Regulation, GDPR, and the California Consumer Privacy Act, CCPA. This is why it is important to have a cloud security and trust architectures, as well as cloud governance that provide robust security and privacy measures, such as encryption, authentication, authorization, monitoring, and compliance, that can protect IoT devices and data from end to end. Another example of a PaaS service provided by cloud platforms today is Big Data Analytics PaaS. As noted earlier, and from a TRM assurance security privacy quality standpoint, security is clearly one of the major concerns with big data analytics. Hacking and various attacks to cloud infrastructure do happen and may affect multiple clients, even if only one site is attacked. To optimize making sense from the big data, organizations need to integrate parts of their sensitive data into the bigger data. To do this, companies need to establish security policies, which are self-configurable. These policies must leverage existing trust relationships and promote data and resource sharing within the organizations, while ensuring that data analytics are optimized and not limited because of such policies. This is why it is important to have a cloud security and trust architectures, as well as cloud governance to mitigate risks using security applications, encrypted file systems, data loss software, and buying security hardware to track unusual behavior across servers. One last example of PaaS service provided by cloud platforms today is Cloud Robotics PaaS. From a security standpoint, when robots are connected to the cloud, they are susceptible to hacking and cyberattacks. This can pose a serious risk to both the safety of robots and the privacy of the data that they are collecting. This is again why it is important to have a cloud security and trust architectures, as well as cloud governance, to help companies develop cloud-connected robots and invest in robust cloud security measures. Cloud Applications Frameworks Assurance. Cloud application frameworks are fully managed by CSPs or designed to leverage IaaS/PaaS services on secure cloud platforms. A cloud server, e.g., AWS, GCP, Azure, IBM Cloud, can replace traditional application frameworks at the cost of migrating traditional applications that use these frameworks to the cloud, which is a costly and time-consuming proposition. For that reason, big tech application frameworks are now available on secure cloud platforms, e.g., IBM WebSphere Hybrid Edition, Oracle WebLogic Server for Oracle Cloud Infrastructure. Traditional database management systems frameworks are easier to migrate to the cloud. For example, traditional database management systems such as MySQL, PostgreSQL, or SQL Server can be migrated to Google Cloud SQL. Google also provides cloud-based NoSQL database systems, e.g. Firestone Document Database, Bigtable Key Value Database, Memoristore in-memory database. Similar cloud database systems frameworks are available on Microsoft Azure, e.g. Azure SQL Database, and other cloud platforms. Cloud support for application frameworks is not limited to database systems frameworks. For example, Azure App Service is a cloud platform framework that may be used to securely host web applications, REST APIs, and mobile applications. More recently, VMware developed a cloud application server called Tanzu, previously Cloud Foundry, that fully operates on the cloud and leverages the latest container management and cloud cybersecurity technology. IBM Bluemix is also derived from Cloud Foundry. Furthermore, all social media platforms, e.g., Facebook, Twitter, TikTok, can be considered as examples of secure cloud application frameworks. Because there are no standards for implementing secure application frameworks on the cloud, end users need to consult the various CSPs, websites, and stay up to date regarding the availability of such application frameworks. Cloud Applications Assurance. Cloud applications are typically implemented on cloud servers, and developers take full advantage of established cloud security trust architectures, as well as cloud governance processes. Big tech organizations typically provide security best practices, models, and patterns to facilitate the creation of secure cloud applications on their own platform. Cloud Information Assurance. In cloud computing, much of the large and critical databases are under the control of CSPs. These resources are located away from the end user's physical location, and often in physical locations unknown to the end user. The possibility, or even likelihood, of data being stored in other regions and countries also requires meeting those regions' legal and regulatory requirements for data protection. All this makes it more challenging to create trustworthy controls for the monitoring, governance, and auditing of the CSP environment. Therefore, as explained earlier, it is necessary to develop cloud security trust architectures, as well as cloud governance processes prior to developing information systems on the cloud or migrating traditional legacy information systems and their data to the cloud. Cloud Assurance Methodologies. Various organizations provide cloud security best practices and cloud cybersecurity assessment methodologies. In particular, the Cloud Security Alliance, CSA, and the European Union Agency for Cybersecurity, ENISA, promote best practices developed for providing security assurance within cloud computing. The CSA Security Guidance provides 14 domains of cloud security best practices. It is built on dedicated research and public participation, incorporating advances in cloud, security, and supporting technologies. The Security Assurance Methodology, SECAM, is a security assurance framework developed by the Third Generation Partnership Project, 3GPP, specifically for network products used in mobile communications. Big tech organizations typically provide risk assessment methodologies geared toward using their cloud platform. Microsoft, for example, publishes a risk assessment guide for Azure. Other CSPs provide similar. Think it through. Cloud computing versus privacy. You are a software engineer, and you work for a company that provides open access to a mapping software for realtors. Your company merges with a real estate company that provides online services, such as sales and appraisals, that your company did not previously do. As part of this new company, your boss wants you to take the customer database from the real estate company and add the personal information of homeowners in the local market to a private software package that lists all the houses in neighborhoods. As part of the new software, you are required to provide one-click access to this information from the mapping software. While creating these new features, you realize that the database of information contains fields such as social security number, mother's maiden name, and primary email addresses. The mapping software company will be stored in the cloud and shared with 10 offices. All employees in the company will have access to the new software. What are some of your concerns? What are some security concerns? What recommendations can you make to help ensure the security of the PII hardware crisis? In October 2020, a warehouse fire severely damaged the Asahi Kasei Microdevices (AKM) semiconductor plant in Miyazaki, Japan. At the time, this was one of 2 RAM manufacturers worldwide. The global crisis for computer memory soon commenced shortly after this disaster. Hardware manufacturers had to slow the production of computers because the memory was not available for production, and the cost of the existing memory escalated. Japan's other chip manufacturing plants could not meet worldwide demand. Today, 3 manufacturing plants account for more than 90% of the world's RAM production. It seems that the world has not learned its lesson and diversified the production of this precious resource. The other side of this story is that software advancements also stopped. New software packages are typically developed to incorporate newer technology features. If the newer computer manufacturing slowed down, the new innovative software packages also slowed down. This was not the same for cloud technologies. Because the resources are distributed and the hardware is not as essential, the cloud environment continues to thrive, and there has only been an increase in cloud usage since 2020. Industry 4: Metaverse, Smart Ecosystems, Cybersecurity. While the Metaverse and Web3 offer organizations new frontiers for customer engagement and business growth, these also create the potential for new cybersecurity risks that could lead to financial losses, brand and reputational damage, and legal challenges. These threats include system outages and disruptions because of data overload and threats that apply to other areas of computing, including ransomware and bots. Smart Ecosystems Platforms Assurance. As noted earlier, Industry 4. Zero smart ecosystems combine various platform services, e.g., 3D modeling, AR/VR, edge computing, blockchain, AI/ML, and 3D/4D printing, and are typically deployed on top of a hybrid cloud blockchain environment today. For example, they may use AI/ML platform services to support the rendering and management of realistic models of a 3D world or digital twins. The various platforms services operate within secure cloud blockchain platforms that are managed using established cloud blockchain security trust architectures, as well as cloud governance processes. Because the platform services can be assembled as mashups by combining offerings from multiple cloud platforms, it is necessary to consider the cybersecurity mechanisms discussed in Cloud Applications Frameworks Assurance in order to understand how to best secure cloud mashups. In this subsection, we briefly discuss the security vulnerability and defenses required when leveraging specific smart ecosystems platform services. As artificial intelligence and other advanced technologies become more prominent and create supersocieties, we also face additional cybersecurity threats. For example, cybercriminals can use AI to leverage more sophisticated cyberattacks. At the same time, AI can be a tool against cybercrime, providing organizations with sophisticated technology to handle security tasks, such as detecting suspicious activity in the system. In addition, AI can be used in testing, such as simulating system attacks to help cybersecurity professionals identify areas of risk and vulnerabilities that should be addressed. According to IBM, AI can help protect data in hybrid cloud environments with tools such as shadow data identification and monitoring for data abnormalities. AI can also create incident summaries and automate responses to these incidents, improving investigations and outcomes. AI's ability to analyze login attempts and verify users can reduce fraud costs by as much as 90%. 39. Technology in everyday life. Using AI in cybersecurity. AI creates new cyber threats, but also provides additional tools to improve cybersecurity. Think about how AI is used in everyday life and consider AI as both a threat and a tool in cybersecurity. Provide a few scenarios illustrating the benefits and drawbacks of AI-driven cybersecurity, e.g., monitoring and analyzing behavior patterns, preventing bad actions and outcomes, and explain your opinion. Metaverse Smart Ecosystems Platform Cybersecurity Assurance Methodologies. To protect against cybersecurity threats in the metaverse, organizations should use many of the same security measures to protect against cyber threats on the internet. They also need to address new cybersecurity risks that could lead to financial losses, brand and reputational damage, and legal challenges. Figure 14:53 illustrates the typical 4 layers of metaverse platforms, along with 8 major threats in virtual world of the metaverse. Diagram showing the metaverse with 4 layers of interaction: application, computing, network, and 8 categories of crypto and NFTs, AI and data management, ethics, privacy and compliance, IoT wearables and AR/VR, decentralized identity and apps, blockchain and smart contract, identity theft and cybercrime, phishing and social engineering. Figure 14:53 The metaverse has 4 platform layers that generally face 8 categories of cyber threats. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. Industry 5. Zero Super Society Solutions, Cybersecurity. In addition to the smart ecosystem services mentioned in the previous subsection, Industry 5.0 Super Society Solutions combine various platforms and technologies such as autonomous systems platforms, advanced robotics platforms, nanotechnology, supercompute, and autonomous super systems platforms. These solutions are typically deployed on top of a hybrid cloud blockchain environment today. Super Society platforms enable AI-powered robots and Super Society technologies, e.g., nanotechnology supercompute, make it possible to improve existing services to further enable smart ecosystem services. The various super society platforms operate on top of secure cloud blockchain platforms that are managed using established cloud blockchain security trust architectures, as well as cloud governance processes. In general, because the underlying services that are part of these platforms can be assembled as mashups by combining services from multiple cloud platforms, it is necessary to consider the cybersecurity mechanisms discussed in Cloud Applications Frameworks Assurance in order to understand how to best secure cloud mashups. In this subsection, we briefly discuss the security vulnerability and defenses required when leveraging specific super society platforms and technologies. Super Society Autonomous Systems Platform Assurance. Autonomous systems platforms are an essential component of the future of artificial intelligence. They provide the tools and frameworks for building, testing, and deploying autonomous systems, e.g., self-driving cars, drones, that can operate in a variety of environments. However, there are various data security privacy, regulatory challenges, and ethical concerns associated with autonomous systems platforms. The fact that autonomous systems rely on large amounts of data raises concerns around data security and privacy. As was the case for smart ecosystems, AI/ML platforms discussed earlier, which face the same type of issues, it may not always be possible to simply rely on the establishment of cloud security trust architectures and cloud governance processes. Using third-party tools to address the lack of scalability of a CSP's cloud platform may introduce vulnerabilities and requires additional defense mechanisms. The deployment of autonomous systems is also subject to various regulations and standards that are not typically covered by cloud security trust architectures and governance processes. Therefore, additional security architecture components and processes will need to be researched and provided based on the domain of application of the autonomous platform. Finally, autonomous systems raise ethical concerns around issues such as accountability, transparency, and bias. These aspects should be covered in the cloud security trust architectures and cloud governance processes. Super Society Advanced Robotics Platform Assurance. Super Society Advanced Robotics Platforms provide the tools and frameworks for building, testing, and deploying AI-powered robots, e.g., cyborg swarmbots that can work alongside humans. The technical challenges associated with securing advanced robotics platforms are analogous to those of securing autonomous systems platforms, which were covered in Super Society Autonomous Systems Platform Assurance. Refer to that discussion to review the security challenges and associated defenses that must be put in place. In addition to these technical challenges, there are also allied social, legal, and ethical issues for seamless integration of humanoids into our societies. There is a lot of research focused on this aspect today. One question is whether there should be special laws to govern robots. Super Society Nanotechnology Platform Assurance. Nanotechnology is one of the super society technologies that make it possible to improve existing services to further enable smart ecosystem services and support super society platforms. The emergence of nanotechnology presents an entirely new set of potential risks, as well as potential solutions to cybersecurity. Because nanotechnology involves the manipulation of matter on an atomic or molecular scale, it is not too far-fetched to think that it could enable the development of smart materials that could detect and react to malicious software or threats. Nanotechnology could also enable the creation of tiny sensors that could detect unauthorized access to networks or data. The use of nanotechnology in cybersecurity could provide users with a greater level of privacy and security. For example, nanomaterials could be used to create encryption keys that are much more difficult to crack than current methods. In addition, the use of nanotechnology could make it easier to detect and prevent data breaches. However, the use of nanotechnology also presents some potential risks. For example, the use of nanomaterials could create new vulnerabilities that could be exploited by malicious actors. Additionally, the use of nanotechnology could lead to the creation of devices or systems that are too complex for humans to understand or control. One of the most promising applications of advanced materials in cybersecurity today is the use of graphene. This two-dimensional material, which is composed of a single layer of carbon atoms, has many properties that make it ideal for security applications. It is highly conductive, strong, and lightweight, and is impermeable to many substances. Graphene has already been used in a variety of devices, including computer chips, touchscreens, and RFID tags, and its potential for cybersecurity applications is vast. Another application of advanced materials in cybersecurity is the use of nanomaterials. Nanomaterials, such as nanotubes and nanowires, are incredibly small, making them difficult to detect. This makes them ideal for use in encryption and authentication systems, where the smallest of details can make all the difference. Additionally, nanomaterials can be used to develop new types of sensors that can detect intrusions and unauthorized access attempts. Overall, nanotechnology has the potential to revolutionize the world of cybersecurity, both in terms of the solutions it offers and the risks it creates. As this technology continues to develop, it is important that the security industry works to ensure that the benefits of nanotechnology are maximized while minimizing the risks. This appears to be the only way to implement Super Society Nanotechnology Platform's assurance. Super Society Supercompute Platform Assurance. Supercompute is yet another super society technology that makes it possible to improve existing services to further enable smart ecosystem services and support super society platforms. It is also a technology that has the potential to revolutionize the world of cybersecurity, both in terms of the solutions it offers and the risks it creates. With respect to risks, the vastly increased processing speed associated with the use of quantum or neuromorphic computers will definitely have an impact on some of the cryptography algorithms that are in use today. In particular, while symmetric key encryption and collision-resistant hash functions are considered to be relatively secure against attacks by quantum computers, signature schemes based on the integer factorization problem, the discrete logarithm problem, or the elliptic curve discrete logarithm problem can be solved with Shor's algorithm with a quantum computer that is powerful enough. On the positive side, non-interactive ZKPs that only collision-resistant hash functions are plausibly post-quantum secure and can be used to replace traditional signature schemes based on public key cryptography that are not quantum-resistant. Supercompute will also improve the speed of cryptographic computations that are needed to operate secure platforms such as blockchain and further optimize the verification of the transactions. Again, as this technology continues to develop, it is important that the security industry works to ensure that the benefits of supercompute from a cybersecurity standpoint are maximized while minimizing the risks. This appears to be the only way to implement Super Society Supercompute Platform Assurance, Super Society Autonomous Supersystems Platform Assurance. The technical challenges associated with securing autonomous supersystems are analogous to those of securing autonomous systems platforms, which were covered in Super Society Supercompute Platform Assurance. Refer to that discussion to review the security challenges and associated defenses that must be put in place. The only difference is the fact that supersystems will make use of new super society technologies that are emerging, such as nanotechnology and supercompute. Given the ethical and social usability challenges, from a TRM quality standpoint, there are growing concerns that the combined use of the various super society technologies described earlier to power autonomous supersystems could cause threats to humanity and future civilizations. It will therefore be important for the security industry to ensure that the benefits of these technologies are maximized while minimizing the risks. This appears to be the only way to implement Super Society Autonomous Supersystem Platform Assurance.